This video combines 5 different machine learning and deep learning projects into a single one. And out of those 5, 4 are from very well-known Kaggle competitions, which are Microsoft Malware Detection, Santander Bank Customer Value Prediction, Gravitational Waves Detection, DC GAN on Celeb A dataset, and the 5th one is Bitcoin Price Prediction with LSTM. Now, for each of these projects, I have separate video in my channel, but I just thought if I could put all of them together in a single video, that could be beneficial to some. Alright, let's start and enjoy. Hello everyone, welcome to my YouTube channel. Today I'll be doing Microsoft Malware Classification Kaggle competition. This competition first came into Kaggle in the year 2015, and since then it has been one of the most famous in this area. The dataset of this competition is almost half a terabyte, 500 GB, and to my knowledge it's one of the largest publicly available dataset on malware classification. So the problem here is a multi-class classification problem, that we are given a set of 9 different malware families and then a huge set of files, and the job here is to classify if one of those files belongs to one of the malware families. So of course I will get into the detail. Before that, a quick word on my YouTube channel, that I plan to publish and upload videos quite frequently, 2 to 3 times each week. So if you have not subscribed yet, please do subscribe, and if you like the video at the end, please don't forget to hit the like button. Alright, with that intro, let's get into the challenge. And so here is the main competition page in Kaggle, Microsoft Malware Classification Big 2015. Remember, there are couple of malware classification challenge in Kaggle, but I am talking about this one, which was hosted in 2015 and with the prize money of $16,000. All right, so let's it's an overview page here. Of course, you should read about this one. And now let's go to the data tab, and here is our data. This 37.8 GB, it's a compressed file, and if you uncompress it, it will become almost 500 GB. And as you can see at the top, they are giving indeed a warning that this dataset is almost half a terabyte uncompressed. So when handling this competition, you really have to be patient. You really need a powerful computer, either locally or in the cloud. So I will tell in a second that how I handle this data for my training. So let's first understand this data and what the main challenge here it is. So you are provided with a set of known malware files representing a mix of 9 different families. Each malware file has an ID, a 20-character hash value, uniquely identifying the file. So this 20-character hash value uniquely identifying a file, they are talking about this one, train label.csv. So each of these files, this is a unique hash character, and these represent each file, and those files are in this folder, train. So this train.7z, this file is 18.8 compressed, and if you uncompress it, it will become around 200 plus GB. And each of the file has a name, and those unique names are here, and the class represent one of the 9 classes. Right now here we can only see one. That's because it's a long list, and if we go down, we will definitely see some other class names here. Okay, I cannot yet see because there are really long number of, so total we have something like 10,800 plus files. So anyway, if you go down, you will see other classes here, and actually you have to download these data, so you will see it there. All right, so that's our train label and train 7z. Now let's understand what these malware classes are. So these are the 9 classes that they're talking about: Ramneet, Lollipop, etc., Wundo, Simda. For each file, the raw data contains a hexadecimal representation of the file's binary content without the PE header. So that's these files are within this train.7z folder. And when you uncompress it, you will see two types of files. One is .asm and another one is .bytes file. We will know in detail what they are, but for now just know that the .asm file is pretty much their assembly language uh, code files, and .byte files are like hexadecimal file representing the hexadecimal code of those files. And our job is to classify these files to one of these malware for the test dataset. That's the whole challenge. Now, when I say classify, what it means is that I drew a quick image of the xi and yi is here. So in this challenge, the xi is your files. So each of this file is your xi, and the yi is this vector of 9 different elements. So 1 2 3 4 5 6 7 8 9, these are the classes, and that's your yi vector. And ultimately the challenge is to assign these probability estimates to each of these class for this file. So for a particular file, at the end of running, say for example random forest or XGBoost, I will come up with a probability estimate that this file xi belongs to class 1 with a probability estimate of 0.2, and the same file belongs to class 2 with a probability estimate of 0.8, and then the probability estimates for all other classes, for example 0000. So of course this number will vary based on different files, and so that's the whole purpose of this challenge, to assign probability estimate to each of the classes out of this 9 for each of the files. And so this is my notebook that I have uploaded to GitHub, and it's also there in Kaggle, and of course I will give the link in the description section of this video. So this is the notebook. It's really a quite long one, so you have to be patient while running it, and I will tell what are the challenges I faced and how you can run this notebook. So initially so ultimately at the end of this notebook I achieved a log loss of 0.007 with XGBoost. That was my best performing model. I tried with various model. I tried with random forest, logistic regression, and quite a few other, and I did some featureization as well. We will get into those details in a second. So this was the best result I had. That's a test log loss. And remember, what was the evaluation criteria for this challenge? That was let's go to overview and evaluation. So this is a multi-class classification problem, so they are using log loss as the evaluation criteria for this challenge, and that's what I applied as well in my notebook. Okay, so I have mentioned all the details in my notebook as well. I also have mentioned all these data and some of the details on the malware that was given. I definitely recommend you go through this notebook. Okay, now coming to my first challenge, running it in Google Colab. So when I extracted the train.7z file, it became almost 250 GB of file after uncompressing it, and that much file I could not really manage even with Google Colab Pro. First I uploaded all this data into a Google Drive of mine, and then of course that's a paid drive space, because normally Google Drive will give you 15 GB. So I have a pro connection, pro subscription of Google Drive, so I get much more space in there. So I uploaded the whole file and then launched a Colab Pro, but Colab Pro could not handle this much of data being pulled from Google Drive. And even in Kaggle I could not run the notebook because I got out of disk space within the first 5 to 7 minutes when I started unzipping the data with these commands. So my final approach to handle the whole training and these full training dataset was this. So I only extracted the train.7z files, which is around 200 GB. after extraction in my local machine, and then split that data to train, test, and CV, and that is cross validation. And I ran the whole training only on these 200 GB of data. That is both my training data and test data and cross validation data were created from this train.7z for this notebook. Of course, for submitting to Kaggle, finally you have to run your whole training on these whole training data set and then submit to be submit your results, submit your submission.csv file to be tested against against Kaggle's own test data. But for the purpose of this notebook, I ran the entire notebook on this dataset because that's the maximum I could manage with my local machine. And then the next part was training all the data in my machine for all the featureization part, which is mostly CPU based. That is during all the featureization calculation from the files and moving the files and taking the hexadecimal codes out of the files. All these are purely CPU intensive work. That is, they don't make much use of GPU. So all these I ran in local machine. So for these, my entire thing, I only took 50 samples. That is, out of 10,800 train files, I only took 50 .asm files and 50 .byte files and did all my calculations on those 50 files. And only after I saw that all my calculations are working properly with the parameters and etc. Of course, it will not give you any reasonable prediction result because you are taking only 50 samples, which are absolutely nothing. But at least you can make sure that your calculation and mathematical operations is running properly on those 50 files. And that's what I did. And those 50 files, even some of the operations, some of the featureization I did on the 50 files, they took sometimes something like 15 minutes or 20 minutes to run. But anyway, so that was my strategy. I did all the calculations on all the featureizations only on 50 files, and only when I saw that the full code is running, the full notebook is running with 50 files, then I finally ran the whole notebook with the 10,800 total number of byte files and ASM files. And then this was the first strategy. And the next second strategy to complete the training session is was something like this, that I created featureization. So this is the featureization I used for this training. We will get into the details of each of these gradually when we go down the notebook. So all these featureization I calculated on the training files, and then combining them, that is the top 2000 bytegram features, top 500 bytegram of opcodes of ASM files, etc., etc. After getting all the individual featureization, and then I merged them and got a merged data frame. And that data frame I exported as a .csv file from my local machine. And then I just upload the .csv file to Google Colab to run the final XGBoost with using the GPU of Colab Pro. So I got a GPU in Colab Pro of Tesla V100, which is pretty powerful with the 16 GB of VRAM capacity. So the final random search CV and XGBoost was run on these combined featureization on the whole data of training in Google Colab. And that final step was quite easy because quite fast and easy both, because it took the full advantage of Tesla V100 GPU on Google Colab. So yeah, that was my overall strategy. And now we will get into the actual implementation of handling the code and getting the data pre-processed properly, all those details. So just want to quickly run you through the overall approach of this notebook and overall structure and flow of this notebook, so that when you refer my source code either in GitHub or in Kaggle, it becomes much more easier to go through it. So here our input data is just the files. So unlike many other Kaggle competition or many other machine learning problem where we have the input given as in a tabular form or as a data frame, or it given as for unsupervised learning, we are given a set of probably a set of images or a set of text files. But here our input data itself are the files itself. That means we have to structure and get all our features from those files itself. And how many files we are given? We are given 10,868 ASM files and 10,868 byte files. So together almost 21,000 plus files for both of them. So these files itself are our inputs. So we have to get all our features from these files, and that's what is a final featureization that I will build. And these are those features that I build throughout this notebook. And how many features are here? Actually, 1 2 3 4 5 6 7 8, total 8 features that I will build from those files data. And that's what I will go throughout the notebook, the details of which how I build them. But ultimately this is our final featureization, and on this featureization I run the final XGBoost for the final training to get my LogLoss information. So that was my overall approach for this notebook, and now I quickly will go over the structure of the notebook so that while referring the source code back in Kaggle or GitHub, it becomes much more easier. So in my GitHub, I have given a clear index at the beginning of the notebook, which will make these reading of this notebook easier. So now what I want to mention is about the flow, that I train a few of the classic machine learning models on first on the byte files only, and then I do the same, that is training some of the classic machine learning model on the ASM files only. And after that, after those individual training separately on ASM file and separately on byte files, then I do the final training on the final featureization after merging all the new features that I build. So this is what you will see in the index as well. So after I do the train test split of the byte files only, I start training only the byte files for different models. So first I train a random model, and then a k-nearest neighbor, logistic regression, random forest, XGBoost, and finally I do the XGBoost classification with the best hyperparams. These all only on the byte file. So I have clearly mentioned that these are run only on the byte file. Similarly, I do the same sequence of training, that is k-nearest neighbor, logistic, random forest, and XGBoost only on the .asm file. So and then after the XGBoost training is done only on the .asm file, then this is where my final steps begin. So this is the final featureization steps for the final XGBoost model training, and this is where it becomes the final submission training and the most important part. And in this video I am covering these final featureization training steps, because I'm not separately talking about this individual training, because these are almost duplicate kind of thing. So only difference for this individual byte file and ASM file training is that your input data and your Y label is just a different data set. Otherwise everything is just the same. So but I'm mentioning it here because while you refer, if you refer the GitHub code, then while you see these extra codes, it should be easy for you to run through this notebook quickly. All right. And so again, as I mentioned earlier, for each of our xi here in this data set, we are given two sets of file, that is one .asm file and one .bytes file. And based on the analysis of both, we have to come up whether that file is one of the 9 classes of malware or not. So what are ASM files? So we have 10,868 .asm files, and these are mainly assembly language opcode file, and each of the ASM file contains address, segment, opcodes, registers, and function calls. And we will deal with these opcodes in a while, but before that, just remember these are the contents of an ASM files, and specifically these opcodes part is very important because they have codes like .move, .pos, etc. So if you want to take a deeper look of what are all the possible opcodes of an ASM file, you can take a look at this link. I will post the link to these in the description. So this link was also discussed in the discussion section of this Kaggle competition among the various top leaderboard members. So anyway, so these are the opcodes. Like you can see the push, pop, DEC, INC. These are all kind of assembly language instruction, and they are contained within our .asm files, and that's a very important part of analyzing if a file is a malware or not. All right, and now what are our byte files? So byte files are just the hexadecimal representation of files. So this is a kind of numbers you will see for each of the byte files. They're just hexadecimal representation of file. So this is also a very important part of analyzing and finding out patterns for malware files. Okay, so let's move on to our next section. Now I will start with some very basic EDA, exploratory data analysis, on the distribution of data and our distribution of classes, etc. And now the EDA, and as the first part, I'm importing all the important libraries that is required for this notebook. And just a quick note that for this notebook I am implementing mostly the three classic machine learning algorithms, which are random forest, logistic regressions, and XGBoost. So accordingly, I am importing all the relevant libraries, mostly sklearn, and also another point to note is this package multiprocessing import process. With this process, we can make use of multi-threading during one long, very CPU intensive process that we will come in a minute. So yeah, but other libraries are all the standard sklearn libraries, and along with that, we are also importing Dask. I think I am going to use Dask a little bit because it's a huge data set, and Dask will some CPU based operation can be performed relatively faster with Dask compared to Pandas. Okay, so that's it. And GC, these garbage collection package also will be important here because these being such a huge data set, and we are calculating so many huge variables during the process, so we cannot keep all those variables in the memory of this notebook as we go down deep in the notebook. So as and when one large variable, after calculation and after making use of that, if I do not need that variable anymore down in the notebook, then I'm going to delete that with the use of this garbage collection package. In that way, I will keep this notebook from crashing. Otherwise, I really faced huge problem in managing this notebook, because if I keep all the variables alive throughout the notebook, then during my later stage work, the notebook crashed. My Jupyter process could not support so much of CPU intensive work. All right, now another point to note that this Microsoft Malware is a very famous competition, so the lot of work has been done by data scientists, both professional and data science aspirants. So a lot of code is available indeed in public domain, and I have also referred many of them. I have taken inspiration from many of them, and I will give the source of the codes that I have used here. Some of my code of this notebook is indeed has been taken from some great codes available in GitHub or in Kaggle. So I will keep the reference and the source of those codes here as and when they are used. Okay, so the first point here in this cell I am doing is that separating my byte files and ASM files, because I will be processing them separately. Because they I'm going to do a lot of featureization from byte files first and then from ASM files, and so they need need to be separated. They cannot be in the same folder, because then I cannot manage them. It's anyway a huge data set of 200 GB. So this cell is pretty much separating them. First, I'm just with the os.path.isdir, if my destination one folder is there, I'm checking that if it's there, otherwise I'm creating it with makedirs. And then with this part of the code, this code block, I'm just separating the files of ASM to byte files to destination 1 folder, and ASM files to destination 2 folder with this shutil.move. It's pretty simple code. You can just take a look at this and you'll get it. And then the first EDA is the classic distribution of classes. So as we mentioned before, that this is a multi-class classification problem. So the first EDA is first EDA to check is whether this multi-class classification problem is a balanced dataset or unbalanced dataset. That is, whether the classes is distributed more or less equally, or if some classes are underrepresented in the distribution. So this code is just plotting a histogram. I am just it's a simple code. Only special thing I'm making use of, that I am including these percentage labels with ax.annotate. So the way that I'm calculating the percentage is with this part of the code, that is 100, and I'm getting the height and dividing it by the total. And what is my total? The total length of y. Remember, y is my class variable here. So when I plot these ax.y-axis.set ticks, yeah, I'm setting a ticks here with 11 ticks, and here also I am getting I'm adjusting the tick levels to represent the percentage. Okay, so this is the plot I'm getting, and the most important thing to look at here is that number 1, number 2, and number 3 is very well represented. Number 3 being the highest of with 27.1% of number 3 classification in the whole data set. But on the other hand, the lowest one are some of these, that is number 4, number 5, number 7. 5 is almost close to nil. It's only 0.5% of the overall samples are classified as number 5 malware. So this is very low. So overall looks like that this is not a balanced data set. You can say it's kind of unbalanced distribution of classes, where number 1, 2, 3 is well represented, whereas number 4, number 5, and number 7 classes are very sparsely represented. And next, I will be creating a box plot of the byte files against the file sizes of the byte files. So for that, I first need to extract the file sizes of each of the byte files. And this is very important, because file sizes is one of the important features we will be using in our final modeling. So we ultimately will extract the file sizes for both the byte files and .asm files as well. But for now, let's check out the code for extracting the size from byte files. This is the code. It is a simple implementation of the os.stat Python method. So what it's doing is, first I'm creating an array with the listdir, os.listdir of my byte files. And remember, my byte files, this folder has been defined here, and this is destination 1, and this contains all my byte files. So, and then I am also making a variable class y. This is this is from the data frame y class, and then I'm converting it to list. And remember, what is our y? Our y is the full train label. So we have defined y here. Yes, this code. So y is just the train level.csv. After doing it, pandas.read csv. And remember, what is our train csv? This is the data given in the Kaggle competition. This is our train level.csv, which contains sorry, all the unique hash codes and all the class labels. Okay, so yeah, so these code for extracting the file sizes make use of this os.stat, and where quickly check out the documentation of os.stat, because I will be using it quite a few times in this notebook. Python method stat performs a stat system call on the given path. It returns all these values. st underscore mode is a protection bead. st underscore inode is an inode number. I don't need that. What I need is st underscore size, the size of the file in bytes. Okay, so coming back to our code. So this is just looping through all the files in the byte files directory, and then getting the stat info.st underscore size, this value, and appending it to an array. And I am dividing this stat size by this number because I need this. This will give me the file sizes in megabytes. So that's why I'm dividing it by 1024 into 1024. Yeah, and so finally I'm making this data frame, which has the ID as a unique hash ID of the file, and then I'm adding this new size column, which is very important, and my class level was already there for each of the file. So okay, with this I can make the box plot now. It's just a simple implementation of sns.boxplot. Here in the X, I'm giving all the classes. I have 9 classes, and Y, all the sizes. So this is my blocks plot. But the important point to note here is there's nothing too much decisive to take from this plot. For example, many of these classes are kind of overlapping, like 1, 4, number 6, number 9, they are kind of overlapping. They take the same space in terms of the file size. All right, so that was my box plot, and now the famous plot tsne, or T distributed stochastic neighbor embedding. I'll be using it only on the byte files in this plot, and I'll be using two perplexity, one with 30 and another with 40. Quickly check what the documentation says about the perplexity in tsne. So tsne is a tool to visualize high dimensional data, which is what our current challenge is. It's an extremely high dimensional. You will see that when you will be done with all the featureization of ASM files and byte files, my total dimension extends to almost more than 1600. So all right, coming back to tsne, it converts similarities between data points to joint probabilities and tries to minimize the callback labeler divergence between the joint probabilities of the low dimensional embedding and the high dimensional data. Okay, that's quite a bit of mathematical explanation, but leave that apart. It mainly for multidimensional plotting and multidimensional analysis, tsne is very important. It will color code the dimensions and plot beautifully and show that if there is distances, decisive distances between the features in the data set. And the perplexity is the most important parameter that tsne takes, and what this means is that perplexity is related to the number of nearest neighbors that is used in other manifold learning algorithms. So this is just the number of nearest neighbor that I want to define, and based on that it will do the whole analysis. So if I take a large number, it will take a larger region of nearest neighbors to analyze the data. So what it says is larger dataset usually require a larger perplexity. Consider selecting a value between 5 and 50. Different values can result in significantly different results, and that's very important. So while plotting tsne, you have to kind of experiment with different perplexity values and check whether the resultant plot brings up any conclusive dimension of the data. So sometime when you plot a tsne with just number of the perplexity being 5, you will not see any conclusion from the plot. But if you increase the number of this number, you will suddenly see some conclusion coming up from the plot. So anyway, let's check if our case gives any conclusion. So the first plot here, I am just using the sklearn tsne and giving the argument as perplexity equal to 50, and ultimately I'm using these matplotlib.scatter to plot it. So this is the plot I'm getting. This is not too much of conclusive. Only one thing we can figure out from this plot, that this color, that is this blue color, which represent the class 3 here, that is kind of separable from the other colors, but the others are almost like overlapping. So this was with perplexity of 50. Let's do another plot with perplexity of 30. And this is a plot, but here as well I can see only the number 3 class is separable, but others are kind of overlapping. So for our case in this competition, or for this data set, there is no conclusion that much really from Disney plotting. All right, now we did some bit of analysis on the bytes file and did some basic idea on the bytes file. Let's now look at .asm files. And like I said before, that in these train folder we have 10,868 bytes file and 10,868 .asm files. And the .asm files is almost 150 GB out of the 200 GB of train files. And what they contain, these files are again, these files are just assembly language code. I recommend you read a little bit about what exactly is .asm files, because there's a bit of theories out there on this file. Basically, this file contains the address, segments, opcodes, registers, and function calls. Out of these, we will be using the address and opcodes part. Especially the opcodes we'll be using quite a bit to build our features. So what exactly are opcodes? So opcode is a short for operational code. These are the bytes stored in memory that the computer actually runs under the assembly language. So I already mentioned these link here. This is exhaustive list of all the opcodes under the x86 assembler instruction. So like DEC, ADC, POP, MOV, etc. All these are opcodes, and that's exactly what we have in our opcodes files. So we will see that all opcodes that a processor supports in that list, but an assembler basically takes text and does relatively simple conversion of it into a file of opcodes that the computer can read and run directly. Most assemble translate very directly to opcodes, and often the 3 to 5 character assembler names for the opcodes are called opcodes actually. So very technically, the opcodes are the binary numbers stored in memory. The names for them in assembler are the opcode names. Also, not all the binary number stores are opcodes. Opcodes tell the CPU what to do. So just read a little bit. I will specially mention this particular research paper. I have already put the link of these in my notebook here, and I also mentioned it in the video description. That let's zoom in. So this research paper mainly says why why the opcode analysis is so important while malware detection. So let's quickly read through it. At least the synopsis. What it says is, to identify malware, most antivirus scanner use combination of signature matching and heuristic based detection. Signature matching compares only to previously known files, while heuristic based detection looks for known system artifacts and previously known bad code pattern in a file. The obvious problem with this is that only known and partially known samples will be recognized. So in this thesis, we use reverse engineering to extract assembly instruction from a given executable file. So this is the most important part that they proposed in this research paper, that they reverse engineered the assembly instruction hidden in the opcodes or of the executable files. We chose to use only the opcodes, which are the part of the instruction that specifies the operation to be performed. For example, MOV. By performing statistical analysis on the dataset, a significant difference between the opcodes in malware and benign files was found. This is the most important key point of this research paper, that opcode is really an important parameter to analyze, to classify if a file is a benign or good file, or if it's an infected or malware file. So that's what they found, that by performing statistical analysis, they found significant difference between the opcodes in malware and benign file. Due to these supervised and unsupervised machine learning approaches like artificial neural networks, support vector machines, BaseNet, random forest, KNN, and self-organizing map was used to look at the sequence of this instruction. Yeah, so the sequence of this instruction, that's what opcode will capture. The unknown files were classified as either malware or benign depending on the presence of and number of occurrences of different sequences. We show that by using only opcode without operands, the rest of the instruction, malware can be distinguished from benign files by using a sequence length of up to 4 opcodes. A classification accuracy of 95.58% was achieved. This is a great metric, that they used only the opcodes without operands, and with that they could detect and they could classify malware with an accuracy of 95.58%. Our work contributes to the research field by proving that. Okay, this is some more information. Anyway, I do recommend go through this blog and in this notebook as well. That's why we work with opcodes and we build features by extracting the opcodes from these .asm files, and so that's very important part of these models that I use, because the final model will have a very important feature that was built with after extracting the opcodes. Okay, now I will build a bag of word feature from the ASM files. And before that, let's quickly understand one concept that I will be using quite a bit here, which is unigram, bigram of text analysis, or NLP. So basically, unigram and bigram are very common technique used in text analysis. And to understand conceptually, I will refer to this Quora answer. It mentions it very clearly and very simply that what exactly a bigram and trigram etc. are, or the unigram. So what they say is that we keep in mind that sometimes word groups provide more benefits than only one word when explaining the meaning. So while doing natural language processing or text analysis, we use word groups rather than the whole sentence or rather than the individual word, because they bring out extra meaning that is valuable for our machine learning model. So for example, here is our sentence: I read a book about the history of America, and the machine wants to get the meaning of the sentence by separating it into small pieces. How should we do it that? How should it do that? It can regard words by one, which is unigram. So each word is a gram. So I read a book. Each of these separate words, they are just unigram because they take a single word from this sentence. Now bigram. So bigram would be I read a book. So they are taking each sequence of two words combination. I read is one sequence, that's one bigram. Then read a is another sequence, which is the next bigram. Then a book is the next bigram, and so on. And similarly, the trigram would be I read a book about, etc. So in this model here, in this notebook for analyzing the byte files and the ASM files, I will also be building unigram and bigram features from the files given from the file information, and we will get into that part in a second. And also quickly, to get the number of n-grams in a sentence, we can use this formula here. This is part of my notebook. Currently, I'm looking at it in VS Code. I will update this in GitHub, so you can check it out in the notebook as well. That if x equal to number of words in a given sentence, the number of n-grams for a sentence would be n-gram equal to x minus n minus 1 in bracket. So for example, if my x equal to 6, that is number of words in a sentence is 6, and I'm I want to calculate the unigram. So the n-gram, number of n-grams would be x minus n minus 1, which is 6 minus 1 minus 1 equal to 6. That is, unigram is equal to the number of words in a sentence, which is obvious conceptually. And now for bigram, for the same sentence which has 6 words, and I want to calculate the bigram, which is 2. That means the number of bigram possible is 6 minus 2 minus 1, which is 5. All right, and now a very important portion of the whole project, which is a bag of words feature on the ASM files. So what I want to do at the end is I take all the ASM files and I want to create a data frame like this. So to explain this data frame, so these are individual files denoted by or identified by this unique hash ID, and all these features that you see on the top, header.text, .pav, .idata, these are all keywords or opcodes taken from the ASM files, and they are all features, and all these numbers are the frequency that this feature is occurring, that many numbers. So for example, for the first file, the word header occurred 19 times. Similarly, this particular string .text colon, it occurred 744 times. This code .idata occurred 127 times. So this just gives all these codes and how many times they occurred in each file. So as you can imagine, this is just a plain simple count vectorizer function of scikit-learn. And what does the count vectorizer do? That it just gives a count frequency of a particular text in a sentence or in a text corpus. So that's what I want to do. But the problem here is that I cannot run count vectorizer on 150 GB of data. Our .asm file total is around 150 GB, and a count vectorizer cannot handle that much of data in it. I have tried running that and it did not run properly. It failed the execution. So that's what my target is. And why this is important, because this is going to become one of the very important feature for our final model, that each of the opcodes and how many times they occur. And remember, we already discussed that how opcodes and their occurrences and their sequences are super important for classifying if a file is benign or it's a malware. So to do that, we need to create these data frame where I can get all the frequencies of each of these codes occurring. And how do I get this each of these feature name? Let's come to that. So all right, so these features now comes under okay, first of all, this code, this particular code, this is I have taken from this GitHub repository. You can check it out. You should check it out indeed. It's a very beautiful, intelligent piece of code applying multi-threading to develop these data frame that I want to do, that is count vectorizer, custom implementation of count vectorizer for our 150 GB of ASM data files. All right, coming back to our point, that how do I decide the 52 features that I just shown here, that these total number of features, I took 52 of them, and that is that after from this code itself, and this code refers to a lot of blogs and research papers, and they found out that this particular set of 52 keywords denoted within the or captured within the .asm files, they are like the most important in terms of malware classification or in terms of file classification indeed. So you can read about them. A lot of links are given here. So you can read about them in more detail, what these codes are and how they are important, and what are the research papers that were referred. So these 52 codes are divided among four different variables. One is prefix, then opcodes, keywords, and registers. And what this register is and what this opcodes is, that's already, this link will mention it in detail. For example, are actually part of this data segment, this Wikipedia link mentions in detail that in computing a data segment, often denoted as .data, is a portion of object file or corresponding address space of a program that contains initialized static variables, that is global variables, and static local variables. The size of this segment is determined by the size of the values in the program source code and does not change at runtime. The data segment is a read-write since the values of variables can be altered at runtime. Okay, so you should read about this a little bit more to understand, if you are more interested, what exactly these prefixes are and registers are. But the whole concept is that these forms the code contains of a .asm file, the assembly line code, assembly line files that we are given, and those assembly line analyzing these keywords are extremely important to take a conclusive decision on the contents of these files, and hence the ultimate purpose of this challenge, that to decide if a file is a malware or not. All right, now before going ahead with this code, a quick concept on the multi-threading, because this whole code implements multi-processing and multi-threading of Python. So let's quickly understand this. So I drew this image just now. So basically, in the hardware part of our computer, how they are at a very top level, extremely top level, how they are architected is that at the top we have the CPU, and nowadays most of the CPUs are multi-core. So we have, for example, in this architecture we have 4 cores: C1, C2, C3, C4. This is the CPU, and the CPU has a link to the RAM, and this is my RAM, and the RAM in turn is connected to our hard disk, which is HDD or SSD if you're using solid state. So now let's take our example for this malware challenge. So all our data, this huge 200 GB is residing in this HDD, and if we want to read all of them sequentially, it is going to take a long time, and the process will be really time consuming. So we are implementing here the multi-processing technique of Python, and to do that, the fundamental concept goes like this: that the RAM, because it has access to the SSD, it reads data from the SSD, and say for example this data and these 4 data is going to RAM, and then from RAM the processor is processing them. So this particular data point or file can be processed by this first core, then the next file can be processed by the second core, and so on. The third one can be processed by the third core, and the fourth one can be processed by the fourth core. But given it's a multi-core or multi-processed CPU, all these 4 processes can run in parallel, and that's why we are going to use the multi-processing module of Python. This is the module that I'm talking about. I will come to that in the code. So this is multi-processing module, and that pretty much leverages the structure of hardware and processes the files in parallel, or do the computation in parallel. All right, now that we have kind of understood how the multiprocessing architecture works in Python, now we are going to implement the code to do the count vectorizer on the ASM files. And once again, I have taken this code from this repo. So what they are basically doing is they are segmenting the whole 150 GB of ASM files into 5 different folders, and then processing those folders parallelly. So this is the key concept here, and let's look at how this is implementing that. So first I'm creating 5 folders: first, second, third, fourth, fifth. The 6th one is just going to contain the output, and then to move the whole 150 GB of file into this different folder, we are implementing a loop over this range. The range is 0 to 10,868. And why 10,868? Because that many number of ASM files we have under the ASM directory. And then we are just implementing these if else condition with the remainder operator. So if the remainder is 0, then those files goes to the first folder, and if the remainder is 1, then with shutil.move I'm moving those files to the second folder, and so on for the next 3. That is, if the remainder is 2, then moving to third, then fourth, then fifth, and so on. So now my 150 GB is divided into these 5 folder, each containing around 30 GB of data, and then I'll be processing it parallelly. So now it's a long piece of code. They are just implementing 5 processes, naming them as first process, second process, third process, and basically all this code is doing, all this function, all these 5 function is just the same. And what they're doing is they're just implementing the count vectorizer, that is counting the number of times each of these keywords or each of these 52 selected string that we have selected as to be the most important for the classification of files, and counting how many times they have appeared in each file. That's all this code is doing. So I'm not going into the detail in this code because you can just go through line by line and it should be simple enough. And all the second process is just the same as the first process. Then I have fourth process and the fifth process, it is just the same. And then this is the important part. After all the process of all these 5 different functions are defined, then I am here, the multiprocessing concept is implemented. So first I'm making use of this process, because to create a process you have to create a class, you have to create an object of the process class. So you can read more about it here in the documentation of multiprocessing module. So what it says is multiprocessing is a package that supports spawning process using an API similar to threading module. The multiprocessing package offers both local and remote concurrency, effectively sidestepping the global interpreter lock by using sub-processes instead of threads. Okay. Yeah, the process class, this is important. We have to instantiate an object of the process class. So in multiprocessing, processes are spawned by creating a process object and then calling it start method. Yeah, that's important. And that's what this code is doing, that they are creating 5 process object, P1, P2, P3, P4, P5, and from the process class. So, and then the start method of process is used to start the thread execution. And then finally using the join method after completion of all the threads. So once the process starts, the current program also keeps on executing. That's a whole concept and the whole purpose here. So in order to stop execution of current program until a process is complete, we have to join them, and that's what it is doing here. So basically here, as a result of using the join, the current program will first wait for the completion of P1 and then P2 and then P3 and P4 and P5 and then join them all together. All right, so now this is done. After this whole thing is done, we will get this data frame. And now the most important point to remember, this whole code execution of the 5 process and doing them in parallel and finally joining them, it took almost like 36 hours to around 45 hours, somewhere in between, in my computer. And in my computer has 8 cores and 32 GB of, no, I have 16 GB of RAM and 8 cores. So you really have to keep your computer completely dedicated to this part for almost 2 days to execute this part of the code on the 150 GB of data. And all right, at the end we get this final file. After doing all this process, the whole result of this process is actually exported or converted into a CSV file, and that's being named here as asm output file.csv. And this is the result. This is kind of the result we get, that each of the word 52 featured, most important feature words, and how many times they appear in each of the files. And we have, remember, we have 10,868 files. Okay, now this data frame is done. This is one of the very important feature we are going to use and finally merge. That will come to after after doing some more featureization. But now let's move on to our next featureization technique. All right. And before I move to the next section of building the next feature, I just want to put things in the context again that what we are doing currently is feature engineering on this problem. So basically, we are given a huge set of 200 GB files in the trained data set, and we are extracting features from those files here, because here the problem is very different. Unlike a normal classical machine learning, we do not have a tabular data. We are just given a set of files and we have to build our features from that file. So till now we have just built one single feature, which is this one. What we did in the immediately preceding step, that we extracted unigram from the ASM file based on the top 52 important keywords. So this is just one feature. We still have to build all the 7 other features that I have listed out, because ultimately all these 8 features will build our final training data frame on which I will run my machine learning model. So let's build the next feature, which is a size of byte files. This is going to be my next feature, size of byte files. I already discussed these, how to calculate size in some time back here while calculating something else. I forgot what was that. But anyway, I will go over this topic again and see what we have done till now. Yeah, so here is that part of the code where I calculated the size of byte files and build this data frame to run my box plot on based on the file size on the y-axis, and on the x-axis was my classes. So yeah, we have already seen this a pretty simple code using os.stat to get the size of each file and appending that size as a megabyte into the data frame. And why now this will come into it will make sense when we are building features, that why we needed the size at all, or why we thought of calculating the file size as one of the feature. So let's see this box plot again. So in this box plot, I plotted the file size on the y-axis and on the class, all the classes on the x-axis, and this is only for the byte files. Now earlier I mentioned that we do not have any conclusion or any conclusive decision from this plot, but just a couple of points to note here, that although some of the box plots here are overlapping, but still they seem to give us some information, like this number 2 class and number 5 class are kind of similar, although a large part of them are overlapping. Why they are similar is because both are within the file size, probably between 4 MB to probably 7 MB. Now we already know the class 5 are very rare. Look at the distribution of our histogram. Class 5 is only 0.4%. So given that information, most of the files during these file size range comes within the class 2. So this could be one of the important information while inputting to our machine learning model. That means that file size may be contributing to the ultimate decision or ultimate prediction of file classification. And so is the case for class 4 and class 6. Mostly they are overlapping, but these two classes again are within a particular file size. And class 1 is also within a very specific range of file size. So although overall the plot does not give any conclusive statement, but it still gives some information that file size can be an important factor in the overall modeling. And that's why we are going to build one of the feature as the file sizes, and we will do that for both the byte file and also the ASM files. And our next feature that I'm going to calculate is the unigram of byte files. And So before we calculate the unigram of byte files, we have to understand one quick concept, that how byte file is constructed, and how their value ranges between 0 to 256. So have a quick look at this. So this is the structure of our byte file. So we already saw this, that the first longer part represent the address, and then we have a pair of letter or number throughout for each byte file. So I have 00008040. Similarly, it could be 80 1C04. So basically, these number and letter combination, this pair ranges between 00 and FF. 00 represent all 0 and FF represent all ones, because each of these represent actually binary format. Means out of this pair, each of these letter or number represent 4 binary digits. So in this case, FF, the first F represent 4 1, and the second F represent another 4 1. So together 8 of them. So this is the case with each of the representation, each pair, that it's a 8. It will be like this 8 binary representation or 8 binary representation. And because each location can have 2 values, if you multiply all of them, that is 2 into 2 into 2 into 2 in 8 times, you get 2 to the power 8, which is 256. And that's why this number ranges between 0 to 256. And now coming back to calculation of unigram on byte feature file. Again, first understand that here what we are doing is, from the byte files, we are extracting some features. And to do this feature engineering, we are effectively converting these byte files into a text problem, so that we can get some textual analytics parameters. Unigram is actually extensively used in text analysis, in text mining or NLP. So that's what we are doing here. We are extracting unigram, which is a text analytics parameter or text analytics tool, to be applied to these files, byte files. So here for the unigram calculation, what we are doing in this part of the code is that the first part, this represents the address. We are completely removing this part first here, with the use of I think I'm using okay, that I'm coming in a second. Let's first discuss the concept here. So we are removing this address, and then for the rest part, all this hexadecimal representation, for each pair we are thinking of it as word, and we are getting the word out of that, and we are calculating each of these word, how many or each element of this word, how many times they occur, or calculating, that means effectively we are calculating the bag of words or the unigram on each of these words. And to do that, we are removing the space in between and calculating the frequencies that these elements or these part of the words or these each of these pair, how many times they occur. So ultimately I will get a data frame like this, that this is a 0th file, this is the file ID, and this is all my features. And that's what these unigram code calculated above here, that how many times 0 occurs in these, this is that many number, how many times F7 occurs is 2804, and so on and so forth for each of the file. And when I print the shape of the file, which I'm doing 1 second. Yes, so here is the shape of my data frame, which is this data frame has 2 rows and 258 columns. And let's see, this exactly matches what I want. The 258 columns, the first column is just this number, sequence number, and then this one is a ID of each of the file, and this 256 is coming from what we just discussed, that there could be maximum 256 possible values for byte files, because byte files, the way that we discussed, that it ranges between 00 and FF, and between 00 and FF there could be maximum 256 unique values. And that's what we did here by implementing the above code, and that's why I'm getting 258 columns in the final data frame. So basically, again, what I did, what we did here is we thought of each of this pair as a word, and and then calculated the bag of words or the unigram concept on these files. And now this part of the code here, that's where is implementing the count vectorizer or the unigram or bag of words that I just discussed. And why I had to implement it manually here is because the scikit-learn count vectorizer cannot work with this huge 50 GB of data, because count vectorizer, I think it requires the entire data to be loaded into RAM at once, and loading 50 GB of RAM definitely is not possible in my local machine. And also I do not have a cloud machine where 50 GB of with a 50 GB of RAM currently. So if and that's the reason these custom built count vectorizer, but this is actually very simple code. It's just building a feature matrix and calculating how many times each of these pair and each of these letter occurs in a single file. That's all it is doing. And why I needed to understand this concept of byte files can have a maximum of 0 to 256 value in between is because look at this, our feature matrix that we are building to calculate this data frame. Finally, it's a 2D matrix, a multidimensional matrix, and one of the dimension of this feature matrix is this maximum value that a byte files can take, 256. So yeah, so this is the final data frame that I get, and this becomes my the next feature, which is unigram of byte files. And finally, when I make my final training data set, then I will actually combine or merge together unigram byte files with size of byte files to get a single feature. But for now, our 3 features are ready. So what are the features we got till now? We got this one just now. We already got this one, size of byte files, that also we calculated. And we also got this one. We have already calculated with the long code that will require 48 hours to run to get this feature. So 3 features we got out of 8. And still 5 more to go, and the next one I will probably calculate the size of ASM files. And so now I'll be calculating the file size of the ASM files. It's exactly the same process. The code is exactly the same what we applied to calculate the file size of the byte files. So initially I get the list directory of all the ASM files. Remember, we created the directory containing all the ASM files in a separate directory. So that's what now I am capturing with these files variable. And then the simple code using os.stat, I loop through all the file names in this files directory, and then append the size of the files to these variable named size bytes. And I get this size of each file with the stat info, that is, and the stat info is just obtained from os.stat, this module of Python. And then I finally create a data frame ASM size bytes, which has these extra column size for containing the size of each of the files. And this is kind of, it looks that I have the class names, each file unique IDs, and also the size of the files in a separate column. So with that, by calculating the size of the ASM files, we are done with these many features in our planned featureization technique. So I'm done with 1, 2, 3, 4, and the next one I will calculate is this one, that bigram of byte files. Bigram of byte files. And first I will calculate the bigram of byte files, but that will give me a huge number of features or columns, but which is not necessary and not optimal, and that will really make the code non-executable, because it will be so large. Because when I extract bigrams from 50 GB of byte files, it will be, the number of features and the number of columns will really be tremendously large. So I will take only the top 2000 most important bigrams of byte files. So first calculate the bigram of byte files with this function. So here is where I'm calculating this one, and I'm mainly using count vectorizer. And the most important part is this one, that count vectorizer can calculate both unigram, bigram, or trigram. So here with this parameter n-gram range, I am mentioning whether it should calculate bigram, and by giving these a tuple of 2 2, it will only calculate the bigram. So quickly check out their documentation. So this is the documentation of a count vectorizer of sklearn, and if you go to, and one of the parameter that count vectorizer takes is n-gram, and if you go to the definition, so n-gram range by default takes a tuple of 1 1, which is for unigram. So here is how to configure that the lower and the upper bound, so the tuple takes min x and max x. By default it's 1 1. So the lower and the upper, it sets the lower and the upper boundary of the range of n values for different word in grams or character in grams to be extracted. All values of n such that min x less or equal to n and n is less or equal to max n, obviously. For example, n-gram range of 1 1 means only unigram. This is the default value of n-gram. And 1 2 means unigrams and bigrams, and 2 2 means only bigrams. So this is what we are using in this code here for calculating the bigram from the byte features. And the next one we will calculate. So this is a code to calculate this bigram. Pretty simple code. It just I am taking all the files of the byte from the byte files directory, and then creating a CSV file with open root path plus featureization byte files. So I'm creating this CSV file and mode equal to W, that is write. And this is where I will be assigning these data frame, that is the data frame which includes the bigram features. And then it is just I am taking an enumeration of the file list byte files and then looping over them and applying vectorizer.transform, which will return me a sparse vector. And ultimately I am just writing a single row in this CSV file, and this single row will be repeated for each byte file. So this will be, if we have 10,868 byte files, these writing execution code will be writing that many numbers to get me the final data frame which has all the bigram of the byte files. And the next one is extracting the 2000 most important feature from byte bigrams using select k based with chi-square test. So let's do that now. So now basically before I apply the feature selection with select k based, let's quickly look at this data frame that I got after extracting the bigram from the byte files. So we have already written the full bigram into this file, byte files bigram df.csv. And now if I read that file, this is what I get. This is a kind of data frame. This is exactly the data frame that I get after getting all the feature names by using bigrams. So this is my bigrams. See, it takes two sequential word or two sequential text as a feature. So 0 0, this is the first one, and then the next one takes this 0 0 and the next one, which is 0 1. Similarly, I get a huge number. How many I get? 66,050 columns. This is so many columns that I get. That is, there are total 66,050 bigrams in all my byte files. Now out of that, now I will extract only the top 2000 by using the select k based of sklearn. So this is the function from sklearn documentation. And feature selection is normally a technique where we choose those features in our data that contribute most to the target variable. In other words, we choose the best predictors for the target variable. And a couple of obvious benefit or obvious advantages are that it reduces overfitting, because less redundant data means less possibility of making decision based on redundant data or noise. It also improves accuracy because less misleading data means modeling accuracy improves, and obviously reduces training time because just look at our case. So it reduces from 66,000 plus features to 2,000 features. And select k based, this function of sklearn mainly takes the most important parameter that it takes is the score function. You can there's so many options to give the score function and basically this is a function taking two arrays x and y and returning a pair of arrays. And in our case I gave it the function of chi-square. One second. Yes, score function I give chi2, and if you look at the documentation, this is what it says, that ch2 will apply chi-squared stats of non-negative features for classification task. So this is what it will do here. One second. Yeah, so let's go back to our code. All right, so after applying chi-square, I create these object here, and then I applied dot fit on my x byte diagram all df, and this is the variable which contains the contains a whole data frame. That is, after reading with pd.readcsv, this variable x byte diagram all df contains a whole bigram data frame. And on these I apply the fit function, and finally I extract the most important features. So that I get by applying this k equal to 2000 because I want the top 2000 features, and it's clearly mentioned in the document that select k base takes the k parameter, which takes an integer or an all, a string. So if you pass an integer, that will be the number of top features to select, and if you pass all, that will bypass the selection altogether. And all right, so I want 2000 features, so I pass 2000, and these whole thing is being held in this variable select k based object, and on this I have to apply the fit function. That's what I do here, fit, and supply, and just regularly to the fit function I supply the x and the y. My x is the full x of bigram df, but I'm dropping the id column here, and the class labels are the whole class labels for the byte files. And then this whole this fit function, this will give me an nd array of this form, which I am capturing with this variable. But I want to create a data frame with the actual scores, that is scores of importance for these top 2000 features. And so I do this next line, I create a data frame with pd.dataframe, and I extract only the scores from this important feature by invoking this scores, extracting the scores parameter here. So if you multiply this feature with a scores underscore, then you will get the actual scores of importance. And all right, and then in the next cell I am pretty much creating a data frame for holding my the actual scores of importance and also the feature names. Remember, we got our final data set. The data frame that I want, that should hold both the scores and the feature names of the top 2000 features. So that's what I'm pretty much doing here. I'm first concatenating the bigram column df with the feature scores that I just created above here, and then I'm creating a data frame out of that. So and then if you just want to check the top 10 features, you can use in largest function. And here I'm just for the sake of checking or testing that it's working, that I'm applying this in largest function for the 10 largest feature names, and this is what I get if I print the head of that with 2. All right, so that was the bigram features, top 2000 bigram features on the byte files. With that, we are done with I think this one as well. So now still 3 more featureization or features to build, and that's what I will do now. All right, now that our top 2000 bigram of byte files is done, the next feature that I want to build is this one, top 500 bigram of opcodes of ASM files. So let's do that. So before we start actually hitting the opcodes of the ASM files, quickly look at the bigram function that I have written. 1 second, because I will be using this bigram function to calculate the bigram on the ASM files. Yeah, so I wrote a bigram function earlier in the file, which is this is just going through just by the, like I discussed on the bigram, it captures each sequence of words, and in the case of bigram, it captures each each pair of sequence of the words, and that's what this function is doing. That it's first I'm creating an empty string, and then I am looping through the entire argument of bigram tokens that is given as an argument to the function. And then there are 2 loops. One is so I have to go through each sequence of pairs, so I'm just doing I in TQDM range lane bigram tokens, and then again j in range lane bigram tokens, and then I'm just adding I and j together. So and then after adding, then I'm appending that to the to this vocabulary list for byte bigrams dot append, and just I'm appending the bigram, and the bigram, in, like I said, that it's just this I and then an empty space and then the j. So and bigram token is a whole list of bigrams. Sorry for that, the noise. All right, yeah. So bigram token is just the list of it's given as an array for the whole text on which the bigram is to be calculated. Okay, now we will go back to calculating our bigram for opcodes of the ASM file. So now here first we have to understand a quick structure of the opcodes on ASM file before we apply the bigram function. So first of all, this is the opcodes list that will be supplied to the bigram function, that is calculate bigram opcode for bigram. So opcode for bigram is this list, and the way that it was derived is again by going through a research report and papers and blogs, that the most important bigrams were, sorry, the most important opcodes for ASM files were shortlisted to be these, and that's our opcode. And then we are also building a dictionary, but this is just because a little bit faster processing. So we are building a dict and then applying zip for all the files in opcodes for all the strings in opcodes for bigram. So from this list, we are creating this dictionary, and then creating a separate folder just to make the calculation clear, because there will be a lot of subdirectories that we have already created during the notebook or will create. So I'm just also creating another directory to keep some of the files separated. Now coming back to the opcode, that we already know that our opcode contains these 6 things: address, segment, sorry, no, our ASM files contains these 6 things: address, segments, opcodes, registers, function calls, and APIs. And calculating the opcode sequence is very important before applying the bigram, because calculating the opcode sequence for each ASM file and saving it in the form of text file is important, so that we can process the ASM file as text files, and in the text file each row corresponds to respective file. So we'll go by row to move through file by file. And I'm also noting that in ASM files, the opcodes for bigram, that is these ones, were not placed side by side. Instead, there are few words between 2 opcodes. That is, the opcodes occur with an interval. So during extraction of these opcodes for bigram, we need to preserve the sequence information. For example, which opcode precedes another opcode and which opcode is followed by another opcode. And based on these, a bigram data matrix of vectors is to be derived containing the bigram sequence info on each file. So first here we are creating that sequence. So pretty much we are creating a list from all the ASM files, and then reading that file with codex.open. Codex is a separate Python module which will for reading some file with and here I'm encoding with it with CP1252. You can read about it in their documentation. They have very detailed documentation here. This is a documentation for codec. Sorry. They have given all the methods and on the encoding strings that we should use, things like that. Yeah, you can think about reading this documentation. And so we are reading those ASM files, and then with our strip and split we are creating a line segment. It's like so our strip will just strip any empty space, and split will split it and make it into a list. And then we are creating another dictionary called sequence of words that will contain the word in the line. This is a simple code just to create a sequence, and then we are executing these function here, so that these opcode ASM files and opcode ASM bigram.txt file gets created and updated with all the necessary information, because now we are going to calculate the bigram based on that. So after that step is done, now then I'm applying this calculate bigram, the function that we discussed just now, and get a variable containing all the bigrams from opcodes for bigrams. And what is opcode for bigrams? Again, this is just this variable. And after invoking this function, after passing this list through the calculate bigram, I get opcode ASM bigram vocabulary. This is my bigram vocabulary for all opcodes from ASM files. But this is just the vocabulary of bigram. But what I need is I need a count of each bigram. That is, I have to go back to scikit-learn's count vectorizer again and get the counts of each of these bigram vocabulary. And that's what I do in the next step. In the step here under the number 45, I calculate, which is calculating opcode bigrams with above defined function and make them a feature, and then save the data matrix of feature as a CSV file. All right, so now I have got the vocabulary from the previous step, and then I'm just applying count vectorizer with tokenizer, lowercase, n-gram range 2 and 2, like I discussed, that 2 represent 2 is for representing bigram, for calculating bigram. And for the vocabulary, I pass this entire bigram vocabulary that I just calculated in the previous step. So now this will give me the vectorizer opcode, and just a regular process. I have to apply a transform on them. But before that, I do certain little operations that I'm creating a list of all the files, which is from opcode ASM files. And what is our opcode ASM files? This is this. We 1 second. Where is our opcode ASM files? This is such a long notebook that sometimes I'm losing track. Root path. Okay, yes. So opcodes ASM files is that the one that we already created earlier under our root project directory. So I'm just getting these. Let's quickly check the first time it was created. Yes. So here in the previous step, we created these opcode ASM files. If not os.path.isdir, then we created with makedir. All right. So now I'm just going to create a file list from that file, and then the regular codes here the whole these block will pretty much, what they will do is that it will apply the transform with these vectorizer opcode, and then create ultimately it will create a data frame and create a CSV out of that. So what I do is I create an opcodes ASM bigram df.csv file with a write mode, and then I am just looping through the entire file list with an enumeration, of course, and then for each of the file I am replacing the new line with an empty string, then applying the transform method on vectorizer opcode. Vectorizer opcode we just created here, this one, and after this transform and this transform of scipy of scikit-learn will give me a sparse metric, so I also have to convert it to a dense metric. That's what I do here, that update each row of the data frame with bigram counts of the respective ASM file, and count vectorizer produces sparse representation of the counts using scipers.sparse.csr matrix, and with two array I make it a dense matrix, and then ultimately I'm writing these each row I am writing these to this file opcode ASM bigram df, and again opcode ASM bigram df has been defined here, that under featureization opcode ASM bigram df.csv as this one, and finally I'm creating a data frame. So this looping will go through for each file of under this file list opcode, which has all the ASM file and ASM file opcodes, and then finally I'm creating a data frame, and if I print the data frame, this is the final thing that I want, and I get this is a bigram of the opcode files of ASM files, of the opcodes of ASM files. So JMP appears 0 number of times in the first file denoted by this hash number, and it appears like 380 times for this file. So similarly I get all these column numbers and the respective count. And how many columns I have? I have 677 columns. But the next step, I'm going to extract only the top 500 from these 677 columns. And just like our previous exercise on byte files, we apply the same kind of steps. That is, we will be using select k best of scikit-learn with the score function of chi-square, and then I pass k as 500 because I want the top 500 feature, and the rest of the codes here is just the same like we used for byte files. That is, I create first I create a score list from my top feature score, and what is my top feature score is this one, that after applying the select k best I get a list of score importance, and I can extract that with this dot score underscore method, and then I create a list, and I ultimately create a data frame for one containing the column of ASM opcode bigram top feature name. So this is a feature name in the data frame, and another one will come. This is our final data frame of the top 500 bigram of opcodes of ASM files after creating a data frame. And so in this cell I'm just creating converting creating a CSV file from the data frame with the to CSV method, and this is what I get, that a data frame which has only 500 columns and the bigram for the entire ASM file list. And so with that, I am also done with this feature, top 500 bigram opcode of ASM file. Now I will be left with only two more. So let's do the next one, which is top 800 trigram of opcodes of ASM files. So first build our trigram function, calculate trigram. It's just like the bigram, but instead of taking 2 pairs of words, we'll be taking 3 pairs of words. So this function to return all possible n into n combination of trigrams. It is just a similar kind of code that we will be given a list of tokens, and then I create a string, and then I will loop through the tokens I, j, k, and then the trigram will be just token I plus an empty space plus token J plus empty space plus token K, and finally return this and trigram result. These final result will be updated or appended with this diagram, that is I calculate through the looping. So for each loop I will have one trigram, and that will be appended to this trigram result that I defined at the top, and then finally returning the trigram result. So given any list of tokens, this function will give me the trigram. And now the time to apply it on our ASM files, and the process is just the same that we applied for calculating the bigram. So we have a list of opcodes. It's a same that we used for bigram, and then we are applying these calculate trigram that I just defined above here, and passing these opcode trigrams to this function. So this will give me the vocabulary, and now I have got the vocabulary. So I need to apply count vectorizer to get the count of each one of this vocabulary, and that's what I do. Exactly the same code, only difference is that vocabulary, for the vocabulary parameter I am passing opcode trigram ASM vocabulary, which is this. So otherwise the rest of the code in this cell is just the same that we applied for bigram. Only difference is that here we are calculating the trigram. So ultimately we get a trigram at the end, and we are creating a data frame from that trigram, and this is that data frame. And see the difference. Only difference is that now we have three words. For bigram we had this kind of structure, two words, because this was bigram, and now we have got the trigram and the count of that. So yeah, so you can see number of zeros are much more here, because now we are counting the frequencies that these three words together appeared in this file. So definitely conceptually you can understand, normally this should be, the number should be less, because now we are capturing, the condition is a little bit more stricter now. Instead of two words, now the condition is three words, trigram. Okay, and then top important. So this is our full data frame, but and this has 17,577 columns, because it's a combination of all the trigram. And just by the mathematical rule of combination, the number of combination of three different things taken three at a time will be more. So yeah, so but we do not want so many columns, definitely. So I'm going to do the same kind of steps here, that I want to extract only 800 features from these opcode trigrams. And again, the benefits are on multiple level, that while we are extracting only the top features, we will reduce the chances of overfitting the data, we'll reduce the training time, and also our accuracy score will be better, because all the noisy kind of parameters will be filtered out. So again, this code is just the same that we applied for bigram. So here pretty much I'm applying the select k based of scikit-learn with k equal to 800, and the score function is again chi-square. From these I will get the scores, which is this method, and then I will get a list of scores. I will concat that with the actual scores and the column names, and then create a data frame out of that. And from that data frame, yeah, so that data frame, from the data frame ultimately I will create a CSV file with a 2 CSV, and this data frame that I have printed here with the head, it is just to show the how it looks like. So here I have made use of this n largest function, which will give me the n largest 800. Yeah, so this is my final feature that will be fed into the final model. So this data frame is for the top 800 trigram on the ASM files, and you can see that column number is 800 here. Initially we got a column number of 17,500, and out of that we extracted the top 800 by important score. All right, so that completes my this feature as well, top 800 trigram files. And now I will quickly go over these last feature, but it's a very special one. You have to remember that I will create images from ASM files and take the top 800 from that. So there's a lot of concept goes here, and a lot of papers have been written here, and there has been quite a bit of discussion in the Kaggle competition as well. So I don't want to go into too much of detail on this one, because then it will become a separate video altogether. Probably I will make a separate video on these particular aspect of this competition, that how to analyze these ASM file as an image. So I will just point out some of the fundamental concept used here and how I got that 800 features, so that you can you can make sense of that. But there are a bit of details here, which I will give some of the links in the description of the video, and I recommend that you may want to read through those. So this is that code for converting ASM files to images, and I plan to make a separate video on this particular specific topic itself, because it needs some concepts to be properly described and explained before this code can be well understood. So for now, just know that this code converts the ASM files in the ASM directory into images, .png images, and that's the base on which this conversion is done is kind of linked to the size of the ASM files, and after doing some mathematical operations on them. So, and after we convert them to PNG, but then again the same process we have to apply. We have to get the most important pixel data from those pixelated images. So what we do is we load all the ASM images, convert it into a NumPy array, and take the first 800 pixel from each image. It's relatively straightforward approach. There are quite a bit of more in-depth approach to handling this problem, and I will refer you to some of the links, but this is the approach I took, and this code is again relatively simple, but they are connected to this code of conversion of images. So I will go into I will go in detail on a separate video on these section of the code. For now, I'm just referring you to some of the blogs that was recent. I definitely recommend that these you should watch this video as well, from this guy Jiwei Liu. It's a first place approach in Microsoft malware classification. So I think they own the first rank in the competition. And also in the discussion, you can also read about some of the discussion thread there. So he has also given in his notebook, he has also given the GitHub repository link, I think, and they have explained in some more details on these image conversion, on their approach, etc. So anyway, so these definitely needs a separate video altogether that I will do in a while. But for now, this is our last feature that we got, and what we got is, after we got the top 800 image, is these data frame. This one. So each file will have so many features, and of course in a corresponding number according to them. And so this is going to be fed into our final model as well as a last feature. So now we are done with this one as well. So now we are almost ready to run our final model, but before that we have to make the data frame completely finalized, merge all the individual features that we have built so far, and create a final data frame before that final data frame is fed into our XGBoost model. All right, so this is the final step of our feature engineering work that we were doing all this while. So now I have to combine and merge all these new features that I was building all this while. So I have got these 6 different features, actually 8 of them, but as we can see that the unigram of byte files plus size of byte files has been combined already, and that's one feature. And similarly, top 252 unigram of ASM files and size of ASM files also have been combined to form a single feature. So now finally we have separate 6 features: 1, 2, 3, 4, 5, 6. And also you will remember that as and when I was building features, I was creating a data frame from that feature and saving that data frame as a CSV file. So now the first step is that all we have to do, we have to read those CSV file and get them in a variable. So 6 separate variables after reading 6 CSV files for all these 6 features. And in this cell, that's what I'm doing. That the first one is unigram byte features with size, and for that I'm just reading these featureization unigram byte feature with CSV file. And remember, we have already, just to repeat again, that these file is what I have created during the feature engineering work. So when I created these byte feature and the size of byte files, I combined them to form a data frame and then exported them as a CSV file and saved it in the featureization folder under the root folder of the project. And now I'm just reading them. Similarly, I'm reading the CSV file for the ASM files. So in this next line, exactly that's what I'm doing. That during the featureization or feature engineering steps, we earlier, when I calculated the unigram ASM feature on the ASM files and the size of the ASM files, combined them and exported them as a CSV file. So now I'm just reading them. But here there's a little code here for dropping few of the classes. So I'm dropping class RTN, dropping few of the features. So the features I'm dropping is class rtn.bss.code. And why? Because during the EDA, I found out that these features were not contributing to the classification as much. So you will see that probably I have not discussed particularly on this part that how I found out that they are not contributing enough, but I am definitely included that in the notebook. So you will get that when you get to see the notebook. So yeah, so I'm just doing the same thing and dropping these features and getting these variable containing the features for ASM file unigram and ASM file size in a single variable. And so the similar thing I'm doing for top 2000 important byte diagram DF by reading the same CSV file that I saved during the feature engineering work. Same for this one, and this one. So now I have got 6 variable by reading 6 CSV file with pd.read_csv, and they are my final features. So they are the final data frame that is going to be fed in the final model XGBoost. But before feeding them, I have to combine, or I have to merge these variables in a single data frame, because right now they are 6 different data frame. So that's what I'm doing in this next cell here. So initialize a data frame for representing the combined features and set it equal to the unigram byte feature with size. So I'm just initializing these final combined feature final. This is extremely important. This is what is going to be fed to our model. So I'm initializing it to be this variable unigram byte features with size, and that just has been defined here when we did the pd.read_csv, this one. So it is just, I'm just initializing this data frame to be equal to this, and then now I have to merge the rest 5 to this data frame, and that I'm doing with a little bit of code. I'm just declaring a list containing the other 5 that I just defined here, and then I'm combining them with this little code of pd.merge and looping through each of the elements of this list, and then I'm doing pd.merge with the first initialized combined feature final DF. So after this line of code, I will have the combined final DF, which has all 6 data frame of features inside it. And now again, I'm doing a 2 CSV to save it as a CSV file. It's just a good practice too, because now I'm dealing with such a huge data. At no point of time I want to lose, for some reason, my computer suddenly malfunctioning, or Jupyter Notebook suddenly crashing. I don't want to lose any data point at any point. So at each step here, because this is the final step, I want to save it as CSV file. So if something happens, I can quickly just start from here by reading this CSV. Because remember, some of these codes from here in this notebook took almost 2 days to run. So you have to be extremely careful with this notebook if you plan to run it ever in your local computer or in your cloud machine. All right, so now this is our final combined feature, the combined feature final df.head, and this. We have total 1628 columns. Remember, initially we had a lot of columns. We had more than probably 70-80,000 column, but after we did all the feature extraction of with the most important feature using sklearn select k best, now we are left with 1628 columns only. And now the final step of the regular step of a train, test, and cross validation split. So I'm going for a 64% train, 16% cross validation, and 20% test. And so it's just normal code here. I'm just reading this final combined CSV, and then I am doing a fill NA of the fill NA 0 on the x values, and yeah, so, and the y value also, I'm just taking the class from the final merge data frame. I'm only taking the class, and the for the x values I'm dropping id and fill NA with 0. Okay, and now this so this becomes my x and this become my y, the actual ones. So now so on these I will be splitting them. So now this is the final, the famous train test split function on this dataset, and I'm getting a train dataset, test dataset, and cross validation dataset, and I'm printing the shape of them as well. So my x train is 6955 by 1627. The number of columns definitely would be same for each of them, but number of rows in my train is 6955, in my test is 2174, and cross validation is 1739. Okay, so now everything is ready for our final XGBoost model to be trained, and that's what I'm doing here. First, I'll be using randomized search CV to get the best params. So I'm just declaring a classifier with XGB classifier, and then setting all the params. So learning rate, I have given quite a bit of reasonable range here, starting from 0.01 all the way up to 0.2. Number of estimators also 100, 200, 500, 1000, 2000. Max depth 3, 5, 10. Call samples by tree is 0.1, 0.3, 0.5, and 1 subsample. And tree method, this is important. I will be running this both in my local machine and also in Google Colab with the GPU. So you have to specify these to take to use the GPU, the tree method GPU hist. And then I'm creating this random classifier with randomized search CV, and when the fit function is applied on this random classifier, it will give me the best params. So most important things before I run my XGBoost. So I get the best params to be these values. So this is the best params that I have, and I will be using exactly these parameters in my final XGBoost. So this is the final running of XGBoost with best hyperparameters that we got from above randomized search CV. So here number of estimator is I'm taking it from the from these best params. So I'm just using this notation here, random classifier dot best params underscore, and then you can pass the exact string for the number of estimator, which is n estimators, and it will give you whatever was n estimators, that is 1000. And similarly I do for subsample, max step, learning rate, call sample by tree, and tree method is definitely we have to use the GPU, so the GPU hist. And then the next code is just a regular boilerplate code of XGB classifier. So I am getting XGB classifier with best hyperparams and passing the full parameters. Number of threads I'm specifying to be -1, so that it will take whatever number of cores or threads are available in my machine. So for that time, if you're running it in the local machine, it will almost become unusable for any other job, because this XGB classifier will take up all of your CPU cores, because I have specified -1. So you can of course experiment here. You can specify 2, 3, or whatever you are comfortable with. And yeah, so finally I get the calibrated classifier CV by using this function, and then finally I apply the fit function on my X train final merged and Y train final merged. By the way, just forgot about a quick point, and that's kind of very important. So I'm just going back a couple of steps here. So before my final train test split, when I got the combined feature final DF, we have to normalize it. And this step, it was mentioned in the, it is definitely mentioned in the notebook, but I forgot to mention it separately. But this is very important step, that we have to normalize this combined final data frame. And I created a custom normal. It is not really custom normalize. I could have used some of the ready-made normalize function available in scikit-learn or some other packages, but I anyway created my own normalize function here in the notebook. This is that function. It's just regular min max normalization, but anyway I have referred to this Stack Overflow post here, so you can check that out. It is just taking the feature name, each feature name minus the mean value divided by max value minus mean value for each of the feature values, and then it will give me the result after normalizing it. So that's we have to apply after getting the combined final data frame, because otherwise the data here hugely varies. There is absolutely huge variation in the data. Somewhere it is more than 90,000, and many places it is just 0 or 0 point something. So you definitely have to normalize it. Okay, now coming back to where we were, that is yeah, we have already we have already run the XGBoost, and we have calibrated, we have also applied calibrated classifier CV, and we got this SIG classifier, and on this I apply the fit function with the actual, that is a ground truth X train and ground truth Y train data, and that will give me all the base to get my predicted value of Y's. So this is what I'm doing in the next cell. That is, I'm again taking the n estimators to be the same as from the randomized search CV, whatever we got from its best params. And this is the important part, that before, remember the evaluation of these computation was multi-class LogLoss, and so for that first we have to calculate the predicted Y train, so predicted value of the Y's. So that's what I'm doing in this simple single line of code. It's super simple. I just apply predict proba, because this will give me the probability estimates on SIG classifier, and SIG classifier is what I got after using after applying calibrated classifier CV, and then on SIG classifier I already have applied the fit method. So now I got the predict Y train by using this method predict proba, and as an input to this function I just applied the X train final merge. This is the completely trained value of X, and with that I can apply the LogLoss, which is a ready-made function here that we have already imported. So this is what I'm printing with best number of estimators of n estimators. N estimator is just this number. I got a LogLoss of this. So for the LogLoss function you have to supply the actual ground truth Y values and the predicted Y values, and I got a LogLoss of 0.007, which is, you can say, it's pretty good. It's not within the top leaderboard, definitely, because in the to be one of the top in leaderboard in this competition with such a huge data set of half a terabyte, you really need access to superbly powerful computer, like having 48 GB plus of VRAM, similarly powerful GPU, or even TPU. Many people have actually have access to multiple TPU, tensor processing unit, to handle this computation. and I don't have access to these powerful GPU just at this moment. So yeah, so with these our reasonable resources, I could achieve 0.007. But remember, my whole training was done only my whole training and the whole notebook was done only by dividing the trained data that was given in the original competition itself. So I splitted the trained data, that is 200 GB, into 64% train, 20% test, and 16% I think cross validation. With this itself I got this log loss. But if I train on the entire train dataset, that is if I train on the entire 200 GB of train dataset, probably I would have got a little bit of improved log loss. But anyway, this 200 GB itself was such a huge fight for me to run. This was hell of a notebook for me to run. I probably spent completely 6-7 days to handle this notebook from beginning to end. So yeah, with these log loss, it's kind of okay and kind of good, I would say. And but there's a huge possibility of further analysis and further further feature engineering technique to be applied for this competition. This is such a beautiful explanation example of the finest feature engineering technique that you can apply, because you are given just a huge set of files and your job is to derive so many innovative features out of those files only. So here I have mentioned a few of them by reading some of the discussion and some of the research papers on this, that how people who have achieved really good score and one of the top 10 in the leaderboard, they have used many more features indeed to get their scores, like names of the imported function, because some of these malware, most of the malware files indeed will have imported functions in them. So the names of those functions could be an important feature, and analysis could be done on them. Then the libraries that those files used, the number of procedures used, computing the constitutionality of the executable, the number of LOC references in the .asm file. Then further, according to some papers, the malware content is often encrypted inside the binary, so we could introduce some encryption related features, computing entropy over a sliding window of half byte sequences. These are definitely some more sophisticated and complex features that we could have built, but it will take similarly that much time to process and compute and analyze. Then further extracting some statistics of its distribution, 20 quantiles, 20 percentile, mean, median, STD, etc. Statistics of first order difference distribution and parts of the entropy sequence, computing compression ratios as an approximation of Kolmogorov complexity. I don't really know what this is, so I have to read up. So yeah, these are some of the more important, some of the more ways of innovation you could bring to this competition. And definitely in those cases you will build a more powerful model and you will get your log loss even much more improved. I definitely suggest you read about their discussion forum in the competition. So this is my notebook in the Kaggle competition. So if you go to the competition, sorry, where is the competition? Yeah, so this is the competition page, the overview page, and I definitely suggest you check out the discussion forum. So I'm just will refer you to another beautiful discussion. He's a grandmaster in Kaggle, and he has described the 7th place solution here. And just by reading, you will get so many ideas how the modeling and analysis and feature engineering can be improved for this competition. Like they have used counts of various objects such as hex codes, hex 2 grams, assembly language commands, then hashes of specific parts of the ASM file, such as each of the first 50 lines and specific properties of the ASM files, for example, segment type, segment permission, etc. I have also partially introduced some of the segment type feature engineering during our analysis of ASM files, but these that he has mentioned here is definitely more advanced. And yeah, so with these they have achieved private LB, they have achieved a score of 0.006, which is definitely much better. The final CV and NV log losses were for them is 0.005 and 0.004. Yeah, so to get this kind of log loss, you really have to implement even more feature engineering and more advanced computation here. So yeah, so look at them. These are really some of the great feature engineering for length of the IDAT section, length of the dot data section, length of data section. Yeah, these are just beautiful example of feature engineering. All right, so with that, this long video comes to an end. There's definitely more work, scope of much more work to be done on this competition if you are interested. And thank you very much for watching. And if you like the video, please hit the like button. And if you have not subscribed yet, like I said at the beginning, I plan to upload videos quite frequently, averagely 2 times to 3 times per week. So please consider subscribing to my channel. Thank you very much. Hey guys, today I'll be going through the implementation of DCGAN, or Deep Convolutional Generative Adversarial Network, on the famous CelebA dataset. And before we start, a quick word: if you have not already done so, please go ahead and hit the subscribe button. And if you happen to like the video at the end of it, do not forget to hit the like button. All right, let's get started. So this is our CelebA dataset. It's a very famous one for computer vision. And what this dataset contains, it is a large-scale face attributes dataset with more than 200K celebrity images, each with 40 attribute annotations. The image in this dataset cover large pose variations and background clutter. CelebA has large diversities, large quantities, and rich annotations, including 10,177 number of identities, and images are 202,599, 5 landmark locations, and 40 binary attributes annotations per image. Okay, and what is facial attributes prediction actually? So FAP, or facial attribute prediction, is a computer vision task about deducing the set of attributes belonging to a face. Examples attributes are color of the hair, a hairstyle, age, gender, etc. And facial attribute analysis has received considerable attention when deep learning technique made remarkable breakthroughs in this field over the past few years. And deep learning based facial attribute analysis consists of 2 basic sub issues. One is facial attribute estimation, FAE, which recognizes whether facial attributes are present in a given image. And the number 2 is facial attribute manipulation, or FAM, which synthesizes or removes desired facial attributes. Now in this video, I will be implementing GAN to produce images from the original CelebA dataset. So let's quickly take a look at the fundamentals of GAN. So this is how GAN works. We have two basic fundamental blocks of GAN, which one is generator and the second one is discriminator. The generator generates new data instances that are similar to the training data, in our case CelebA images. Generator takes random latent vector and output a fake image of the same size as our reshaped CelebA images. And the discriminator is like the detective in this whole process. So the discriminator evaluates the authenticity of provided images. It classifies the images from the generator and the original image. Discriminator takes true or fake images and output the probability estimate ranging between 0 and 1. So very much what the discriminator does is it takes each image and tells it whether it's fake, that is 0, or it's a real image, that is 1. And this is a loss function of the GAN framework. It's a min-max kind of algorithm, and here D refers to the discriminator network, while G obviously refers to the generator. Okay. As the formula here shows the generator optimizes for maximally confusing the discriminator by trying to make it output high probabilities for fake data samples. On the contrary, the discriminator tries to become better at distinguishing samples coming from G from samples coming from the real distribution. The GAN training process consists of a two-player mini-max game in which D is adapted to minimize the discrimination error between real and generated samples, and G is adapted to maximize the probability of D making a mistake. When G does a good job, to fool D, the output probability should be close to 1. Now, that's the fundamental GAN framework, but DC GAN is called deep convolutional because in DC GAN we bring the mathematics and the architecture of convolutional layers. So quickly have a look at what's the difference between a normal neural network and a convolutional neural network. So the convolutional neural network is a subclass of a neural network which have at least one convolution layer. They are great for capturing local information, for example, a neighbor pixel in an image or surrounding words in a text, as well as reducing the complexity of the model for faster training. And CNN also needs fewer samples and reduces the the chances of overfitting. A CNN is a neural network where one or more of the layer employs a convolution as the function applied to the output of the previous layer. CNN does convolution between the previous layer's output and the current layer's kernel. This is a kernel in this image, the small matrix. And if the window is greater than size 1 into 1, the output will be necessarily smaller than the input unless the input is artificially padded with zeros. And hence CNNs often have a distinctive funnel shape. That is, the input is larger matrix. After applying the kernel, we have a smaller matrix, and this is just the weighted sum between the kernel weights and the input values. So this is a subject by itself, and I can make a separate video altogether on the fundamentals of CNN, which I will actually do after a while. So in this one, I'm not going in more detail of the CNN. So let's quickly look at the DC GAN, that is a deep convolutional GAN on GAN models architecture. So DC GAN was introduced pretty recently, and it involves convolutions to the generator and the discriminator network. However, this was not simply a matter of adding convolution layers to the model, since training became even more unstable. Remember, GAN by itself was extremely sensitive to parameters, and DC GAN is even more so. So several tricks had to be applied to make DC GAN useful and stabilized. And these are those four things that four guidances that were mentioned in the original research paper. One is batch normalization was applied to both the generator and the discriminator network. Then dropout is used as a regularization technique. The generator needed a way to upsample the random input vector to an output image. Transposing convolutional layers is employed here, and leaky ReLU and TAN-H activations are used throughout both networks. So this is again the architecture of a convnet or CNN, and this is the starting point is the input image or the input matrix here. So unlike a regular feed-forward neural network whose neurons are arranged in flat, fully connected layers, layers in a convnet are arranged in 3 dimensions: width, height, and the depth. So CNNs or convolutional neural network are networks with architectural constraints to reduce computational complexity and ensure translational invariance. And what is translational invariance? So it means that the network interprets input patterns the same regardless of translation in terms of image recognition. So a banana is a banana regardless of where it is in the image. And finally, this is the architecture of a DC GAN. So now first let's understand how traditional image processing works. So traditionally ConvNet uses a network that takes an image with the dimensions height, width, and number of color channels as input, and through a series of convolution layers outputs a single vector of class scores with the dimension of 1 into n, where n is a number of class labels. In DCGAN, however, under the generator part, to generate an image by using the ConvNet architecture, we reverse the process. Instead of taking an image and processing it into a vector, we take a vector and upsize it to an image. That's what this part is doing. So overall, the core of DCGAN architecture uses a standard CNN architecture on the discriminative part of the model, but for the generator, convolutions are replaced with up convolutions. So the representation at each layer of the generator is actually successively larger, as it maps from a low dimensional latent vector onto a high dimensional image. It needs a layer to translate from coarse salient features to a more dense and detailed output. Now let's quickly go through the original paper that was published in Jan 2016 by Alec Radford and Luke Mades and Sumit Chintala. So the original paper mentioned few things to stabilize GAN, like I discussed earlier, that GAN by itself is super sensitive to parameters, and DC GAN is even more so. So the architecture guideline that they have given for a stable DC GAN are the following: replace any pooling layers with strided convolutions or discriminator and fractional strided convolutions or generator. Use batch norm in both the generator and the discriminator. Remove fully connected hidden layers for deeper architectures. Use ReLU activation in generator for all layers except for the output, which uses TANH. Use leaky ReLU activation in the discriminator for all layers. So you will see that we will implement these things in the model that I'm going to start coding now with a syllabi dataset. Further, this image, you already saw it, that it takes, so what they say is that a 100-dimensional uniform distribution Z is projected to a small spatial extent convolutional representation with many feature maps. So this is a 100-dimensional vector at the start, and this is a whole generator part. A series of 4 fractionally strided convolutions. In some recent papers, these were wrongly called deconvolutions. Okay, forget it. A series of only 4 fractionally strided convolution, then convert this high-level representation into a 64 into 64 pixel image. Notably, no fully connected or pooling layers are used. So basically, what the generator takes in some noise, the 100-dimensional vector here. Then it uses conv transpose 2D, which is essentially kind of the opposite of conv layer. So it upscales the image to 1024 channels and then 4x4. We can see that depth and height is 4x4. Then it upscales again to 512 channels with 8x8. And then it upscales to, and then the whole process goes on. The next upscaling is to 256, 16x16, till finally we reach the last layer, which is 64x64, and then by three RGB layers, RGB channels, sorry. Okay, so this is the overall architecture of the generator. I strongly suggest that you should go through the paper once. It's a wonderful paper to read, indeed. All right, now I am going to start with actual coding. And for the data part, I was actually using these Kaggle competition. It was not really a competition as such. So this dataset was uploaded to Kaggle 3 years back. It's a very famous and very well-known dataset, Celeb A faces, that we already discussed, and they actually mention the details of the dataset here and what's the task to be completed for this challenge. And so I downloaded the whole dataset first to my Google Colab. I will come to that in a second. And these are the data set that hold that this folder has all the images of 200,000 plus .jpg files, and these are some CSV with the labeling of the images. So here I am in my Google Colab, the start of the whole code. And in this cell, what I'm doing is connecting my Google Drive with Kaggle dataset. So basically I'm bringing in this whole Kaggle data, 1.4 GB, I guess. Yes, 1.45 GB to my Google Drive so that I can use the Google Drive data inside Kaggle. So this code is pretty boilerplate. You can find it all across the web and in the documentation very well explained. So the first line here is just bringing in the google.colab and import drive, and then I'm mounting the Google Drive, and then this particular line pip install Kaggle. This is a Kaggle package, and you may not have to install it, but I had to force reinstall it because the Kaggle package that Colab had in my case was slightly outdated, and I was getting some warnings and few errors as well. So I had to completely do a fresh reinstall of Kaggle. And then I have to also specify the os.environment. This is the folder contain the drive the contain drive my drive Kaggle dataset. This is where the API or the .json file resides that you get from Kaggle. The detail, I'm not going to the details here in this video because there's a lot of videos on these and how to connect Kaggle data with Google Drive and Colab. So this is a standard code, and then you have to change directory to the Google Drive through this line os.chdir, because uh, unless you change directory, you if you after you get the data in Google Drive and start coding immediately or unzip the data, then all unzipping will be done in the virtual machine of Colab. So take a look at this next line so that you will understand that why I need this line. Here in this line, Kaggle dataset download. Again, it's a standard line you will get from Kaggle page itself to download the data from Kaggle to Google Drive, and then you have to unzip the data. So this unzipping part, uh, I have to change the code here. I think I have taken it from the my earlier project on gravitational wave detection. So it will go something like so it will go something like my drive, select dataset, and the dataset dot zip. I think the folder will be, the whole data will be downloaded as a zip file. So unzipping this, before unzipping this, you have to do a os dot change directory here. Otherwise, the whole unzipping of this data will be done in the virtual machine of Colab, that is in this folder. This is the folder structure, directory structure of Colab's virtual machines, and it will be there only for this particular session, that is 12 hours or 24 hours, depending on whether you have the free version of Colab or the pro version. So if I do os.chd, then all the next operation will be executed in that particular directory, and that's what I'm changing my directory to Google Drive, and then my unzipping command will unzip this whole .zip folder into Google Drive. Okay, so that was the first cell, and then my next is the standard importing of all the libraries. It's just the standard libraries, NumPy, Pandas, and etc. The important part is the Keras. I'll be using TensorFlow and Keras here. So I'm importing all the Keras.layers, conf2d, dropout, dense, flatten, conf2d transpose, batch, normalization, leaky relu, and reshape. All right, now I am going back to VS Code because it's slightly easier for me to write codes in an IDE compared to Colab. Okay, so first I'm just creating an empty array, and that array will contain the full image path of each of the .jpg files. Full image path. full image train part. So first get the folder name which contains all my images, and that's this folder actually. I'm just following the folder structure in a Kaggle challenge. So it's up to you how you, if you are working in a local machine or in Colab, certainly this will be difficult based on where you keep your .jpg files. And now I will be looping over each of the .jpg files and creating a full path of the jpg files and adding those paths to this array, so that this array contain the full path of each of the .jpg files, and from here I can extract how many ever image files I want to extract. Because remember this, for this training I will not be using the 200,000 files because that's too many for both my local machine and even for Google Colab Pro. I was getting indeed out of memory error multiple times when trying to work with the full 200,000 images. So I will be extracting only 50,000 and work with that. And then let's see how it goes. Okay. In os.listed full image train path. I'm looping over all the file names, and if the file contains .jpg, if jpg, okay. Remember our file structure in Kaggle. So let's quickly have a look at that. So this is our file structure in the original Kaggle dataset. So the root folder contains an folder named img align celeb a that has another folder with the same name, and within that I have all the .jpg files of 200, 2000 and 569, 570 indeed. Okay, so oh no, this will be a few more because I have probably 20 or 30 images here. So anyway, this is our folder structure. So let's loop over that. If .jpg in path, I'm just adding, now I'll be building a image path containing this full thing plus the .jpg file name. All image path .jpg and full image train path. And now I'll be extracting 50,000 images from these array, all image path. So let's name a variable. Equal to with the slice notation. Let's check out if they contain the correct size. Image just print the lane of it. Yeah, it printed 50,000. Okay, now this is my overall plan to work with the 50,000, but during the actual coding part, because I have to run each cell immediately and don't wait for the result, I don't want to wait to look through the 50,000 images for each cell. I will just take 500 so that all my different cells in this Jupyter notebook runs quickly. And now I will be working with the image. So let's add a code. So first what I will do is I will crop the images so that I get only the portion which contains a face. So I'll be making use of these Python image library PIL and the image module which has a crop function. Let's do that. First, I'm defining a cropping box that is, which is a tuple containing 4 numbers, and this defines pretty much the left, the left side, upper side, right, and lower side of the cropping parameters. Cropping box. I checked this number; it kind of worked well for me. 0175, and now I have to actually crop them. So this. So this is my this variable training images will contain my full the full image array, that is the full numpy array of the images with which I will be training. So that's what I'll be building now. And I will be making use of, I'll be first reading the image token. Cropping box. My np.array image. Okay, makes sense. I'll be resizing them to 64 by 64 size. Resize text. Quickly check their documentation. Resize text size as a tuple int resample. Okay, size is enough for me. 64 by 64, and for path in image 50k, this should work. Let's quickly check out lane running images. NP not defined. That's strange. Okay, I did not run the whole file indeed. Let's let's comment this out because I don't need them here in my local environment. Okay. Now, yeah, it worked. So my training images now has 500 rows. Remember, we selected only 500. Later, of course, like I said, I will be changing it to 50,000. Now, let's quickly check if my training image is actually what they are. This should be numpy array. So, oops, sorry. Training, I'll print training images. And yes, they are three-dimensional numpy array like this. So yeah, it goes on for 500 rows, that is for 500 images. Yeah, so as you can see, the number varies widely: 10, 15, 17, 189, 194, 234. We cannot have that. I will have to normalize it to make it between, to limit it between 0 to 1. So let's do that first. Clear cell output. I will be manually normalizing it. Remember the concept of normalization. That is, right now my numbers, all these NP array ranges between 0 to 255, which is 255 being the maximum value. And I want to normalize these image values to between 0 and 1. And that's because neural network process inputs using small weight values, and input with large integer values can disrupt or slow down the learning process. As such, it is a good practice to normalize the pixel values so that each pixel value has a value between 0 and 1. So, and our normalization formula is this. Normalized is between, it is a min max normalization, so minus min x divided by max x minus min x. The whole thing is again between my braces. And yeah, now this is what I am going to implement for my NumPy array representing the full image set. So I in range training images. So I am looping over my full training image. This is the array containing all the images. I'm looping over each of the element over for it. So each training image will be denoted by training images I. And that value should be, let's do, sorry. No, I do need the training images I minus training images I, the mean value, and that needs to be divided by this part, max minus mean. And remember, for our case, the max value of the pixel is 255. So we can actually replace the max value with 255. That's the max value for each pixel. $255 minus training images I, no, mean. Okay, that should work. And now let's convert this whole thing to proper NumPy array. Training images equal to training images. This will give me a well-structured NumPy array with which I can work. And now quickly print them to check if they were really converted between 0 and 1 value. Running images. Yes, indeed. Now you can see that each values, all values are between 0 and 1. All values. And we can actually check even further that all these values, the mean and maximum values of these, this is a 4-dimensional NumPy array, so we can actually check that none of the values are beyond 0 or beyond 1 on the minimum side or maximum side respectively. Let's quickly do that. So I have to print the max values of these training images columns. So I'll be using np.max, and I'll be np.max, what kind of arguments it take. Consider definition. Yeah, it takes print. Oh no, 1 second. Okay, forget about it. np.max takes actually the first argument is the original NumPy array, and it takes an axis parameter, which will be 0. And similarly, I want to do that for the minimum values in n. Now let's print it. Yes. So okay, let's Okay, let's just quickly check it as it is. So first I printed the max values of these training images, which is a 4-dimensional array. So these will print the maximum column values, and we can see that none of them goes beyond 1. Okay, and we also printed the minimum values for x is equal to 0, and we see that all of them are capped at 0. So no minimum values which goes beyond 0. That's what we want. Okay, so our normalization is done. Let's comment that out. And to check the shape of the training images, I can quickly print that shape. And that's 500 number of rows or samples. And these three terms are actually the shape of the image. Remember, we resized the images here, resize 64. So here I have an image size of 64 by 64, and 3 are the number of channels. So all right, now I want to print the actual real images, few of them. I want to print 10 actual real images, so that I will do it from here. So this is the code to print the images. I have a plot figure size declared here, and now I'm just looping over a range of 2. That is, I want to print 2 rows of images, and in each row there will be 5 images. So the inner loop has will range over 5, and then I'm using the im show and plt tight layout. The tight layout documentation says, oops. Anyway, the documentation is not coming here. Okay, I'm just running this cell, and I get a yes. So I get a plot of 10 images. These are actual images from the real data of Celebed. All right. Now my next step is to actually build the generator function, and that would be, I'm not typing the code here because that will make the video length incredibly long. So it's better for your time as well. So this is my code for the generator part of the model. Now I will go over the explanation of each of these terms and what they are doing, what is especially this topic of conf 2D transpose before we go further. So initially we declared this noise shape to be 100. Remember the original, from the original paper of DC GAN, it starts from a vector of 100 at the first step. So let me just quickly open that paper. So here is the original paper of DC GAN, and this is the generator part of the model architecture. And we can see that the starting point is a 100-dimensional or a vector of 100 dimension called Z, and it clearly says that a 100-dimensional uniform distribution Z is projected to a small spatial extent convolutional representation with many feature maps. Yeah, so that's what we are doing here. Let me go to my code. That's what I'm doing here. That this noise is that randomly generated starting point, or Z, as per the architecture. And the first layer is a dense layer, and then I am reshaping it to 4 by 4 by 512. And a quick word on this input shape, which I'm giving these noise shape of 100. So if we see the documentation, so this is the documentation from Keras, and it says that note that you can also omit the input shape argument. In that case, a model doesn't have any weights until the first call to training or evaluation method. So in this case, I created a model, sequential model, and then add a layer, dense layer, and then another dense layer. But till this point, there is no weights or no input shape is defined here. That means a model.weights not created yet. So to have these weights initiated, I have to supply the input shape, and that's what the next block of code is doing. Whereas if you specify the input shape, the model gets built continuously as you are adding layers. So that's a situation definitely I want here. Okay. And so then in the next one, I am reshaping it to 4 by 4 by 512. And this is the most important part, conf 2D transpose. So remember, the whole architecture of generator is like a opposite of normal CNN. We start from a low dimensional vector and upsample it. So that's this conf 2D transpose function is doing here. So a quick look at the documentation. All right, before we go to the documentation, have a quickly check out what this conf 2D transpose is doing at all. So this image, it's a normal CNN. So we start with a 3 by 3 image and apply on this image a smaller kernel or smaller matrix, also called filter. This is my 2 by 2 kernel, and the output of applying this kernel on this image is this 2 by 2 matrix. So we start with a larger matrix, apply a smaller filter on this large matrix, and output comes a smaller matrix compared to the input. But what if you want to start with a 2 by 2 output and apply a kernel and get a larger image? So that's the situation we are dealing with in generator part of a DC GAN. And it is kind of the reverse of the normal CNN, and this whole thing that we are seeing here, this problem can be solved with the conf 2D transpose API of Keras. So now let's quickly go over their documentation. So this is the API Keras documentation here, and it clearly says transposed convolution layer, sometimes called deconvolution. The need for transport convolutions generally arises from the desire to use a transformation going in the opposite direction of a normal convolution. The most important part, opposite direction of a normal convolution. And this is what we do in a generator. We start on the opposite direction of a normal CNN. That is from something that has the shape of the output of some convolution to something that has the shape of its input, while maintaining a connectivity pattern that is compatible with said convolution. All right, so this is pretty much the most important thing you have to understand. They have, if you are interested, you can check out their source code here in the GitHub under the Keras team, Keras, and you will find this class under the layers and then convolutional.py file. And this is a beautiful piece of code, very large code base indeed. And we can see that these within the init function, they initiate all these same kind of arguments that we apply for a normal CNN: kernel size, filter, strides, padding, everything is there. All right. And similarly, so I'm adding the same kernel size, the same kind of arguments to my conf 2D transpose function. Kernel size of 4, strides of 2, and padding same. And remember, the conf 2D transpose is fundamentally works like CNN. It just in the opposite direction. So the transpose, under the transpose layer, it simply swaps a backward and forward pass, keeping the rest of the operation the same. And that's why the transpose convolution also will take the similar kind of arguments like slide and kernel size, etc. And I found this beautiful blog. If you are interested to know more about the kernel size, strides, padding, etc., and I will put a link to this blog in the in the video. So here's the blog I was talking about. Understand transposed convolution, written by Quan Wei. It's quite a long blog and it's really exhaustive. So he has given some of the good definition. So here, what are the parameters? Kernel size, strides, and padding in Keras conf 2D transpose. So kernel size in convolutions, that is in normal convolutions, the kernel size affects how many numbers in the input layer you project to form one number in the output layer. The larger the kernel size, the more numbers you use, and thus each number in the output layer is is a broader representation of the input layer and carries more information from the input layer. But at the same time, using a larger kernel will give you an output with a smaller size. And this is for normal CNN, and see how this is a pictorial representation of this kernel size effect on output. But this mechanism is just the reverse for transposed convolution. That's what he's saying in his blog as well. In transposed convolution, when the kernel size gets larger, we disperse every single number from the input layer to a broader area. Therefore, the larger the kernel size, the larger the output matrix if no padding is added. So 2 by 2 matrix, input matrix, on this we apply a 3 by 3 kernel and I get a larger output matrix under the transposed convolution. Similar kind of cases for strides as well. So in normal convolution, the strides parameter indicates how fast the kernel moves along the rows and columns on the input layer. If a stride is 1, 1, the kernel moves 1 row, 1 column for each step. If a stride is 2, 2, the kernel moves by 2 rows and 2 columns for each step. As a result, the larger the strides, the faster you reach the end of the rows or columns, and therefore the smaller the output matrix. And this is an image of that movement, but this mechanism is same, just the opposite direction for transposed convolutions. Here, the stride parameter indicates how fast the kernel moves on the output layer. As explained in the picture below, notice that the kernel always moves only one number at a time on the input layer. Thus, the larger strides, the larger the output matrix if no padding. Okay, so these you can of course go through this blog. It's a really beautiful blog, and he explains all these parameters very well. So going back to my code, and after the conv2 2D transpose, I am adding a batch normalization. Okay, before I go to batch normalization, another quick word on this conv 2D transpose. Keras also has another function called upsampling 2D, and that's sometimes is confusing, that because many people think conv 2D transpose is also effectively doing an upsampling, and the other function which is called upsampling 2D, that is also doing upsampling. So what is the difference? So remember, upsampling 2D is just a simple scaling up of the image by using nearest neighbor or by linear upsampling. So nothing smart, no special computation is done on that. But the advantages of upsampling 2D is it is cheap computationally. On the other hand, this function, that conv 2D transpose, is a convolution operation whose kernel is learned just like normal conv 2D operation while training your model. So using conv 2D transpose will also upsample its input, but the key difference is that the model should learn what is the best upsampling for the job. So it is in a simple word, it's much more smarter way of computing compared to the other function upsampling 2D. All right, now my next one is batch normalization is added to the model after hidden layer, but before the activation. So batch normalization is pretty much to stabilize the overall training process. So batch normalization standardizes activation from a prior layer to have a zero mean and unit variance. This has the effect of stabilizing the training process. Under batch normalization, it fundamentally limits the amount by which updating the parameters in the previous layers can affect the distribution of inputs received by the current layer. These decreases any unwanted interdependence between parameters across layers, which helps speed up the network training process and increase its robustness, especially when it comes to network parameter initialization. So batch normalization is used after the activation of convolution in the discriminator model, and for the generator model it is used after transpose convolution layer, but before the activation layer. that is before applying leaky ReLU, and that's why I'm applying leaky ReLU after the batch normalization is done here. Okay, now that the generator model is done, let's quickly see how our generator model is doing in outputting some images from random noise. So I have this code here. I'm just creating a random noise of 100-dimensional vector, and then invoking or passing that noise to my generator model, and then plotting with IM show generator image. Let's run this cell. All right, it's interesting. So this image that is created by my generator model from the 100 vector, it's just pretty much random noise, but it's the potential of the generator model is shown right here, that given just 100 vector random noise is created this image, and that exactly the job of the generator model. Okay, so now in the next model, which is discriminator, and this is my code for discriminator model. It is much more conceptually easier to understand if you understand CNN, because discriminator is just a regular CNN model implemented. So here I'm giving, again, it's a sequential model of Keras, and I'm the first layer. I'm creating a plain vanilla conf 2D with 64 and 3x3 strides, also 2 padding same, and input shape is just the same as we gave to generator model. Sorry, input shape in the generator model was 100, but here it's I'm specifying 64 by 64 by 3. Sorry about that. Okay, so and then the next I'm adding a leaky ReLU, and then a dropout so that my model doesn't overfit. And then the next layer is again another conf 2D, and then a batch normalization, then another leaky ReLU dropout, and then the last one is flatten, and then the last is fully connected dense layer, and return discriminator. And then I'm getting a discriminator variable with the output of this function. So that's my discriminator model. And now the next step, I have to generate the combined generator and discriminator and compile my GAN model on top of that. So this, sorry, let me get the code of this. Okay, so this is my code for the for combining generator and discriminator together, and then I am compiling it. Discriminator.compile optimizer, I'm using Adam, and because my discriminator will select each image to be either fake or real image, it's a binary classification problem, kind of 0-1. So I'm using loss as binary cross entropy. Then discriminator.trainable, I'm setting false. I will come to that, the meaning and significance of this line in a second. Okay, then I'm compiling the GAN, and if I run the last line is summary, it will create a summary of this compilation, the whole GAN model that I have built. Discriminator is not defined. Okay, I did not run this cell. Yep. So this is the my GAN summary here. Okay. All right. So now the question is why I'm setting discriminator the trainable equal to false. Why would we want to do this is because we are not going to be training the generator model directly. We are going to be combining the generator and the discriminator into a single model, then training that single model. This allows the generator to understand the discriminator so it can update itself more effectively. So setting discriminator.trainable to false will only affect the copy of the discriminator in the combined model, and which is good, because if the copy of the discriminator in the combined model were trainable, it would update itself to be worse at classifying images, which is not what we want. And now the final training. Remember, training GANs is an art form itself because a slight mistake in the hyperparameters and the mode will collapse. So play with different hyperparameters to obtain better results. The overall architecture for our training is as follows. The final architecture of DC GAN here. Number one, initially both the networks are naive and have random weights. The standard process to train a DC GAN network is to first train the discriminator on the batch of samples. To do this, we need fake samples as well as real samples. We already have the real samples, so now we need to generate the fake samples. And then to generate the fake samples, create a latent vector of shape 100. Remember, the first step for DC GAN as per the original paper was a vector, a 100-dimensional vector. So we will create a fake sample with 100-dimensional vector over a uniform distribution. Feed this latent vector to the untrained generator network. The generator network will generate fake samples that we use to train our discriminator network. So the training loop begins with generator receiving a random seed as input. Here the random seed means this 100-dimensional vector. That seed is used to produce an image, and then concatenate the real images and the fake images to create a new set of sample images. We also need to create an array of labels, a label 1 for real images and label 0 for fake images, which is the whole purpose of this training, that each real image will be labeled as 1 and each fake image will be labeled as 0. Now, after that, the discriminator is then used to classify real images drawn from the training set and fake images produced by the generator. And the loss is calculated for each of these models. Okay, so that's my... Now let's start with the actual code. I am pasting the whole training code here, and that is this. Let's go line by line over here. So initially, while coding, I'm giving an epochs of 1, but so because I want to see the result almost immediately. But after my coding works perfectly, then I will give an epochs of 300. And why so many epochs I will give is because here the total data set was like 200,000 plus images, but I took only 50,000 of that, and that's why I'm increasing the number of epochs. And batch size I'm using 64. You can also use, of course, 128 to 56 based on the power of your GPU. Then I'm creating two arrays, loss from discriminator model and loss from generator model. This will hold my collect the losses from the discriminator and generator model respectively. With tf.device, I'm using the GPU 0 for, and then I'm starting the looping over the epochs for epochs in range epochs. Print, currently it is just a printing, and then inside each epoch I am looping over the whole range of each batch, because I have to do this training batch by batch, and that's why I'm doing training images.shape 0. That will give me the number of elements in this current batch, or number of rows in this current batch, you can say. And why I'm using these double slashes to divide the batch size, that's because benefits of double division operator over single division operator in Python is that double division returns the float value for both integer and floating point arguments after division. So after these batch size division, I will get the current batch size, and then this is the first step, as we discussed in the previous screen, that the whole process starts with a noise vector of 100 dimension. And my noise shape, this particular variable has already been defined somewhere up here. I think noise shape is 100, and I'm using the same variable here. Yeah, so I'm starting a sample, creating a sample the sample of batch with uniform distribution, and that would be a 100-dimensional vector. And then I am directly bringing in my generator that I defined above to generate a batch of fake images. So this particular line will just pass the noise to the generator model and predict on batch. With the predict on batch function, it will create a whole batch of fake images from the generator model. Now again, a quick word on how this training code is organized and how we are looping through the batch and epochs. Here we are training two models at once, the discriminator and the generator, and we cannot rely on Keras's dot fit function. Instead, we have to manually loop through each epoch and fit the models on batches. And so on the same line, for predicting the image array from the generator, we cannot use a predict function. Rather, we have to use this predict on batch function. And what's the difference between predict and batch and predict function is that predict will go through all the data batch by batch, predicting labels. It thus internally does the splitting in batches and feeding one batch at a time. Predict on batch that I'm using here, on the other hand, assumes that the data you pass in is exactly one batch and thus feeds it to the network. It will not try to split it. So in summary, predict method has extra operations to ensure a collection of batches are processed right, whereas predict on batch is lightweight alternative to predict that should be used on a single batch. So when your when your dataset is very large, normally you have to use predict on batch because you want to configure your own batch size and your own way of looping through the data, unless you have a superbly powerful GPU or TPU. So yeah, so this is the logic why I'm using predict on batch. Let's quickly check their documentation here. Predict on batch, yeah. It says returns prediction for a single batch of samples, and it takes input data, the arguments, and input data could be a NumPy array or array of list, or a TensorFlow tensor or a list of tensors in case a model has multiple inputs. Okay, and that's what we are passing. We are passing here the noise vector, which is a NumPy array. All right, and now after I have generated the fake images, now I am taking the real data set of train images, and that's what I'm doing in this line, that from the whole training images I am getting through the notation of slicing, I'm getting only the images for this batch, that is I into batch size to I plus 1 into batch size. And then I'm creating labels. So first I'm creating some real labels. That is training labels real is will consist of np.ones, because like I said that all the real images will be classified as 1, and that's what this line is doing, creating a one creating all the training labels with classified as 1. And then I'm setting training discriminator.training equal to true, because now I will be training the discriminator, and that's what I'm doing under this line dloss real. Here I'm training the discriminator network on real images and real labels. So I am passing to the discriminator that I have defined above, I am passing a train dataset, which is my real dataset, and train labels real, which is actually classified as 1. So, and what this train on batch is doing, quickly check the documentation. This is runs a single gradient update on a single batch of data. It takes the x as input argument, and which could be a NumPy array or a TensorFlow tensor or a dict mapping input names to the corresponding array of tensors. Okay, so all right, now in the next, let me quick, yeah, now I'm training after my after training the discriminator network on real images. Now I have to train on fake images as well, and that's what I'm doing here. First, I'm creating some training fake labels. And remember, fake will be classified as zeros, and that's why I'm using np.zeros here to create all these zero classified fake labels. And then dloss fake is just the same code like here, but instead of passing real data or real train labels, I am passing the fake images which is generated from the generator model, and also the fake labels, that is this one. And then the noise, it's the same kind of same vector, a 100-dimensional noise vector created from uniform distribution. Okay, and why I'm creating this noise vector here again is because now that my training of the discriminator network is done, now I have to create all the variables to run the training on the whole adversarial network. I will come to that in a moment, but let's first make a comment here so that it's clear. Create to make ready the adversarial network, the whole. Okay. Okay, so noise vector I'm creating, and then I'm also creating a train label fake for generator training. So these are my these will be fake labels that is classified as ones. That's why I'm creating np.ones that will be fed to my adversarial network. So, and again, discriminator.trainable I'm setting to false, because like we discussed earlier that when the adversarial network is getting trained, I cannot train discriminator model simultaneously. I have to freeze it. So now the final training part of the generator. To train the generator network, we have to train the adversarial model. And what is my adversarial model? This is the one I'm talking about. So I created this GAN as which is equal to sequential of generator and discriminator both, then compiling discriminator and then freezing discriminator by making it trainable to false, and then compiling this GAN model with optimizer of Adam and loss of binary cross entropy. And this GAN is what I will be using here. Yes. So the generator loss is equal to GAN dot train on batch. Train on batch is again, it will train on each single batch, and to these I'll be passing this noise that I just created of a random uniform variable and these fake train labels, which are all classified as one. And why I'm doing this is because, so what basically I'm doing here, that I train the adversarial model on the batch of noise vector and real labels. Here, real labels is a vector with all values equal to 1. And then I'm also training the generator to fool the discriminator network. To do this, I provide it with a vector that all values equal to 1. That is this noise I'm talking about. All these values are equal to 1. In this state, the generator will receive feedback from the generator network and improve itself accordingly. And now finally, I just have to update the loss array that I declared earlier, and that's just these. Loss from discriminator model dot append, I append both the dloss real and dloss fake, and similarly loss from generator model dot append, I append here only the generator loss. And now I manually check, or you can say it's just like a checking, a passive method of checking the images by just looking at them. And that's what I'm doing in these lines of code, is that after every 50 epochs, I'm taking a sample of 10 and predicting from that samples by feeding it to a generator model, and then I'm just plotting those images with plt.subplot function, the fake images indeed. So yeah, so if I run this, I will get fake images. Let's run it. Remember, it's running just for one single epoch, so I will not see any discernible photos or images at all. And that's what it happened, that it ran in 7.1 second, but it was just a single epoch, and it created some images, but those images don't contain pretty much anything, because first of all, it's just single epoch. And then remember, at the very first step, we took only 500 images, so no reasonable training can run on 500 images only. But anyway, it just proved that this code overall is working. And now if I run it for around 50,000 image, and for 10-20 epochs, I will start to see the actual images forming, that is fake images forming gradually. And I ran these training code, the whole training code in Colab, with 50,000 images and 20 epochs. And then I plotted that result. That is, after this training, I ran this code to plot the images, the resultant fake images that I got from the generator model with this code. It is again a very simple code that we used already earlier in this here. That is, I'm first creating a noise vector and then passing that noise vector to the generator model to predict. And here I can use predict. I do not have to use predict on batch, because it's a small batch, and I want Keras to decide the proper way to split the batches. So yeah, so I'm just passing this noise to the generator model to predict and create fake images, and then plotting those fake images with the plot.subplot function. It is just simple plotting code here, and I got this kind of result. Yeah, they are still in progress. You of course do see that none of them are properly recognizable. That's because I did not run the full 300 epochs. I only ran for 20 epochs, so they are kind of still forming at the very beginning stage of forming the images. So yeah, that's my result. And now I am indeed going to run 300, and after 300 epochs I got pretty believable result. You can run this code in your machine or in Colab for full 300 images, or if you can also for the full data set of 200 plus 200,000 images, and then you get almost, the fake images will almost be unrecognizable from the real images. They will be so real. All right, so that kind of wraps up this video. If you like the video, please hit the like button, and also I'll be uploading videos pretty frequently, 2 to 3 times at least per week. So consider subscribing to my channel. Thank you very much. Okay, so today we'll be going over this Kaggle competition for gravitational wave detection. You can see this site open over here. So first check what this competition is all about. So in this competition, you were provided with a training set of time series, a huge data set of 72 GB, coming from 3 gravitational interferometer, which are LIGO, Hanford, LIGO, Livingston, and Virgo. And what are interferometer? Of course, you can read all the details in this overview page over here, and there's a lot of discussion and a lot of code out there. But to brief on the interferometer is that these are extremely advanced instrument to measure the minute details of gravitational waves coming to Earth from billions of light years away. So in the data given in this competition, each time series contains either a detector noise or detector noise plus a simulated gravitational wave signal. And the task is to identify when a signal is present in the data, that is target equal to 1. So we need to use the training data along with the target value to build our model and make predictions on the test IDs in the form of probability that the target exists for that ID. So basically, data science is helping here by building models to filter out the noises from data streams. And we already know that the data stream includes both noise frequencies and gravitational waves frequencies. So we can single out the frequencies for gravitational waves with the help of our data science modeling. So now have a quick look at the data. Okay, this is the data folder, and you can see it's a huge 72.06 GB of data. We are giving a training levels and sample submission. So if you go to the train data set, it's quite a bit of nested folder structure here. So let's see. All right, already 4 levels of folder structure, and click on this file. Okay, this is the first file, and it's a .npy file, which is the NumPy file. And to give the basic description, we are provided with a train and test set of time series data containing simulated gravitational wave measurement from those network of 3 gravitational interferometer. And each time series contains either detector noise or detector noise plus a simulated gravitational wave signal. And the task here is to identify when a gravitational signal is actually present in the data. So each of these, there's so many, I think there are probably millions of NPY file here. And each of these .npy data file contains 3 time series. We will see in the actual notebook in a bit. So each of these .npy file contains 3 time series, one coming from each detector, and each of the time series spans 2 seconds and is sampled at 2048 Hz. And we have a total of, yes, I have the data, we have a total of 5,060,000 files, and each file is of dimension 3 into 4096, and that's how this huge data set. And now the actual IPython notebook that I submitted for this competition, to give the overall purpose of this notebook is I wanted to implement a basic EDS to understand the overall structure of the data and also the flow of the data, and also implement simple CNN with one layer of ConvNet with Keras. This model got me a score of 0.491, or I think 0.5 or something like that, with 1 epoch, which is definitely not a very good score, but that was not my intent here in this notebook, because I just wanted to achieve some baseline level of calculation with this notebook. So yeah, I will share the link of this notebook in the description for both my GitHub and in Keras and in Kaggle. All right, so first, initial imports, all the regular imports, only 2 mention a special mention of this package GWPY, which is for handling specifically gravitational wave kind of data, time series and NumPy data, and also this package NN audio. This NN audio is for implementing some spectrogram from the waves data that was given in this competition. And remember, this particular competition has 5,060,000 .npy file. And what exactly are .npy files? They are standard. These .npy files are just standard binary file format for persisting a single arbitrary NumPy array on the disk. The format stores all the shape and the data type information necessary to reconstruct the array correctly, even on another machine with different architecture. The main benefit for using .npy file is that they are incredibly fast for reading purpose compared to normal plain text or .csv files. And now initially I just wanted to check a single file, what they are and what kind of plot they produce. So I just have declared some of the variables here for the root directory, and randomly I have taken a single file here. You can say this path root directory plus train, then 000. There's 4 levels of nesting, and I'm plotting a single time series with this function get t series from file. So t series 1, I'm taking the first time series. That is, remember, each of the .npy file has 3 time series in it, coming from the 3 interferometers. So that's what I'm exactly doing here, that my first time series takes the first time series, the second one takes second, and third one and third. And sampling rate is 2048. And I'm implementing this time series function, which is from GWPY, that I have imported here from gwpi.timeseries, import time series. All right, so yeah, and this is the plot, and this plotting function is also coming from gwpy. You can see it here. Yeah, gwpi.plot, import plot. All right. Yes, so this is this particular graph that you can see, it's coming from one single .npy file. So each of the .npy file has this kind of data, and it is a time series plot. You can see that all of the .npy file has similar kind of time series data. And now I will be loading all the NPY files, and first take a look at the labels, the CSV file for labels that we are given. So here is the data. I am just reading the labels file, target labels file. Now we have the IDs and the target is 1 and 0. So it's a binary classification problem. 1 here means that this is a gravitational wave indeed, and 0 means it is not. And all this ID, they correspond to the file names. That is the 5,060,000 .npy files that we have. These IDs correspond to those file names. And so let's load the files. And by this code, you can check out this code. I'm using the glob module, and root directory is already defined. And from there, I am just going inside the 4 levels, nested levels of directory structure here. So within the train, I have another 4 labels, and what this star asterisk is doing is they are practically taking all the path names, all the file names from here, and storing into these variable names. And then further, with few lines of code here, I am getting the exact file path names like this, as you can see. Input, G2net, gravitational wave detection, etc., etc. And finally, I'm making this DF train, which will become the base of our calculation going forward. So it has got just 3 columns: ID, target, and the file path name. All right, now do a simple classification first. Classification plotting. Okay, here I'm using SNS.counterplot here, and I'm just classifying the target, how many of them are 0 and 1, and it's a very, very balanced data. As you can see that it's almost equal. The 0 and 1s are almost equal. And now I'll be doing a simple EDA with the basic security analysis of the waves. Now, what is security? It's a constant quality factor transform, and it was first published in I think 1988 or so. I have actually mentioned, 1988. I've actually mentioned the original paper here. And what this does is the constant Q transform transforms a data series to the frequency domain. It is related to the frequency transform in general. The transform is well suited to musical data and proves useful where frequency spans several octaves. Now, why we are using it here is because here also we are analyzing waves data. What we are analyzing is our gravitational waves, and so all the concepts of digital signal processing or waves analysis equally apply here, because here also we'll be dealing with frequencies, wavelength, and characteristics of the waves, its domain analysis, etc. So I have put some explanation here about the CQT, and I'm also using this NN audio package, which implements this particular CQT original paper's algorithm, and it's also the most popular one to analyze audio waves and also the gravitational waves. So let's come to the calculation here. So this is our original data frame that we have just built a while back. And I have 2 functions here. One is get security spectrogram, and another one is just for plotting them. So in this first function, get security spectrogram, I'm passing the waves of each file as the argument. And the transform I'm using here is the security 1992 V2. This is the algorithm that I was talking about from the original paper, and NN audio improves it slightly or modifies it slightly, and that's why they call it V2. So all I'm doing is I'm using np.hstack. I'm stacking the waves horizontally, and here the arguments, you can see that SR stands for sampling rate, F mean for I think that's for the bin of the transform. Yes, so F One second. Yeah, f mean here is a frequency for the lowest security bin. I'm just reading from their documentation, which you can find it here. This is a GitHub repository of NN Audio. All right. So coming back to our function, f mean is the frequency for the lowest security bin. F max is for the highest security bin, and hop length is the hop or the strides. The default value is 512, but we are passing here as 64. And now in the plot, I am just getting I'm just using implementing 5 plots. So in this range of 5, I'll be passing 5 waves to this get security spectrogram function, and this is a plot that I'm getting here now. All right, so that was security, and then I'll also be plotting some basic KDE box plot and time series in the next section. So I'm defining a multi-plot function which will plot all the 3 of them. That is depending on the plot type here. I am implementing both the box plot, KDE, and the time series plot as well. It is just for normal, very basic checking of the data and its whether it's balanced or imbalanced, something like that. And normally from all these box plots and the probability distribution plot, that is a KDE plot, we can see that the data is superbly balanced. All right, now okay, that was my initial EDA. I have not, now I'll be moving to the actual model building, and I'm using the Keras sequential model here. Okay, now before going into the actual model building, a quick note and word on the Keras sequential API. So in Keras, there's 2 ways to build models, which is one is sequential and another one is functional. The sequential API, which I'll be using it here, allows you to create models layer by layer for most problems. It is limited in that it does not allow you to create models that share layers or have multiple inputs or outputs. So in short, you create a sequential model where you can easily add layers, and each layer can have convolution, max pooling, activation, dropout, or batch normalization. And the second way, which is a functional API, allows you to create models that are much more flexibility, as you can easily define models where layers connect to more than just the previous or the next levels, but you can actually connect in layers literally in any way that you want. So as a result, you can build much more complex models with the functional API. But for simplicity's sake, here I'll be using functional API, which pretty much is a linear stack of layers. So you can create a sequential model by passing a list of layers, instances, to the constructor. The common architecture of ConvNets is a sequential architecture. However, some architectures are not linear stacks. For example, Siamese networks are 2 parallel neural networks with much more shared layers. So let's get back to our code. Okay, so here I'm starting to build the model, but first we have to do the data generator code. And here again, why I need a data generator before I pass such a huge data of 72 GB to the model of Keras. And the key reason is to be able to handle large data with batching. So with data generator function, your RAM, CPU, or GPU does not need to handle the full data at once, which will anyway not be possible for this huge 72 GB of Kaggle data. So basically, since our code will most certainly be using the multi-core architecture of CPU, that is, it will be using 4 cores, 6 cores, 8 cores. So to take the most advantage of that, we have to make our code such a way that it processes batch by batch, and so we do not have to worry about the data generation part. Rather, we can focus on our model. So here is my data generator function. It is also very well explained in the Keras documentation, and it should, Keras documentation gives the overall architecture that this data generator function should have, and as per it, that it should have the init function, len function, get item, and this final data generation function. Out of these, I think the Keras documentation makes it mandatory to have the minimum, the len private function and the get item private function. So you can go through these in detail with the notebook that I'll be attaching in the description. So pretty much what the lane is doing, it's returns a number of steps in an epoch using the samples and the batch size. And the get item method is called with the batch number, and it returns you the X and Y for this batch. And finally, the data generation is the most crucial part. So it it loops through the entire data of these 5,060,000 files that we have for this data set and returns you batch by batch. So yeah, that was my data generation class. Yes, and now I'll be moving into the actual building of the model. First, a few defining some variables that will be necessary. So I need the sample submission is just this file that was given in the root of the directory. And I also need 3 sequence of data or 3 series for train, test, and validation. And that's what I'm doing here in this code, train generator for sequential model. So this is generating a sequence from this data generator function, and I'm processing it 4 things: the path, the train indices, which is my which is defined here, which is the return value of the train test split. I'm splitting all the train labels, indexes, and okay, so the train generator sequence model and validation generator for sequence model, test generator sequence model is defined here with the data generator function. And this is the actual where I'm building the sequential model of Keras. So first I'm adding a convnet and then a batch normalization, then flattening the layer, then a dense fully connected layer here with the ReLU function as activation, and then the final step, which is adding a dense layer fully connected and with sigmoid activation function. The optimizer here is Adam, and also because it's a binary classification problem, I'm using cross entropy as my loss function, and given it's a binary data structure, I'm using binary cross entropy as a loss. And if I do my model, the summary, it gives an overall summary of my data, which is printed here. And then this is the final step. I'm just running the model. Here I'm running it for a single epoch, and a single epoch and workers I'm passing as -1. That is, we'll be using how many of our CPU cores are available in the machine. So in my local machine with 8 CPU cores, it's an i7, and it ran the single epoch took almost 2.5 hours. So if you run in Kaggle with use a GPU in the Kaggle, it may run a little bit faster, but I'm yet to try that. And anyway, so this is my final model, and note that I'm using the fit generator here, and for predicting the result from the test data, I'm also using predict generator. So a quick note on this, that what is fit and fit generator, what is fit generator and predict generator, and what's the difference with the normal fit function or predict function of Keras. So in Keras, using the regular fit function or predict function is fine for small data sets, which can be loaded into the memory at once. But in practice, for most practical cases, almost all data sets are large and cannot be loaded into memory at once. So the solution is to use fit generator and predict generator with custom data generator function, which can load data to memory during the training or predicting. So basically, when you are using custom data generator, you have to use fit generator and predict generator. So so in the fit generator, you don't pass the X and Y directly, unlike the normal fit function. In normal fit function, which deals with much smaller data, you just pass, it's just like an sklearn's fit function, and you pass X and Y as a target variable. But in fit generator, you don't pass X and Y directly. Instead, they come from the data generator function that we defined earlier above here. Yeah, this function. So as is written in the Keras documentation, generator is used when you want to avoid duplicating data and using multiprocessing, and that's the case when you are also using data generator. All right, so finally, sample submission target. This is my target data coming from the return value of this predict generator function. And finally I'm saving it in a CSV file named submission.csv, and that's what is my final output, and which I'll be submitting to Kaggle as a competition submission. I indeed did that, and the link of which I'll be sharing in the description of this video. So that was pretty much it. Thank you for watching. Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. Today it will be a very quick video on getting the historical prices of cryptocurrencies like BTC, Ethereum, etc. And the data mainly will be OHLC data, that is open, high, low, close, and also volume. And the package I will be using is this one called Historic Crypto. This is their GitHub page, and the main developer of this package is David Oroniuk. And they have a very quick documentation. You can under the hood, this package actually hits a Coinbase Pro API, and then it downloads all the data. And for me, I downloaded the Bitcoin data all the way back from 2015 up to today, that is 31st October of 2021. It took like something like 2 hours in Colab, but I did not get any rate limit limitation, so I could download in the entire data right from 2015 up to 2021 October. Okay, so the first thing you have to do is install this package. So run pip install historic crypto, and I'm inside my Google Colab. I'm running this cell inside my Google Colab. So let's run this cell, and that will install historic crypto. But for me, I have already installed historic crypto earlier, so that's why I'm getting requirement already satisfied. And then you need to import for the historical data. So this package provides 3 modules, mainly historic data, cryptocurrencies. It is for some ticker names, etc., and also live crypto data. So for this video, I'm just going to use these historic data because I need the historic data of my cryptocurrency. So import this module, and then, so now with that import, I'm ready to run the code and get the data. So first, I want to define a variable which will hold all the downloaded data, and then I have to invoke this function historical data. And historical data takes a ticker, granularity, start date, and end date as its argument, and you can quickly check their documentation here. It's very well explained. So here the ticker is you have to supply the ticker, and that would be the corresponding cryptocurrency that you want to download the data for. For example, if you are downloading Ethereum USD data, the ticker is ETHUSD. But for my case, I want Bitcoin USD data, so it will be BTC USD. And the granularity is a number of seconds in a day of trading. So that takes a few particular values. That is 60 seconds, 300 seconds, 900 seconds, all the way up to 86,400 seconds. And this last value is actually the total number of seconds in a day. That is 24 multiplied by 60 and multiplied by 60 another time. And the start date and the end date both are strings in this particular format, that is YY, MM, DD, HH, MM. All right, so I think I am ready to supply those. So BTC USD, granularity I want 60, and for this video, for the start date, I will provide 29th of October, and I just want to download 2 days of data for now. 29th is a start date and 30th is the end date, and then I have to invoke a function called retrieve data. Yes. And now I think I'm ready to run. I have the ticker of the cryptocurrency, granularity, start date, end date. Okay, let's run this cell. Awesome, it started extracting the data, and it will get the data in chunk. Because I have just 2 days of data, it should get executed pretty fast. Yes, so it's done already. Now quickly check what this data is. So this BTC historical, that's actually a pandas data frame. So I can use head and tail on this to check out their data. Beautiful. So this is the first 5 rows of these BTC historicals, and that has a starting date that is 29th of October, and this is a various timestamp of these day. So I have got low, high, open, close, and volume data of BTC. Also check the last 5 rows, that is to check that if I have the ending date data as well. BTC historicals.tail. So I'm using pandas tail function to check out the last 5 rows. Awesome. So I have the ending date here, that is 30th October, and the timestamps of various timestamp that this API was hit. The various timestamp of these prices, these actual prices. So quickly check the shape of this data so you can understand that the number of rows that was imported, that was received. BTC.shape. Yeah. Yeah, so for just for 2 days, I got 1500 rows of data and 5 columns. Of course, the 5 columns are low, high, open, close, volume, OHLC data, and the timestamps. So I got total 1500 timestamps of data. That's really a very good number of data for 2 days. So I ran the same code for the entire historical period available for this package. That is, this package under the hood is hitting the Coinbase Pro API, and I got data from the 2015 all the way back from 2015 up to today. That is 30th October 2021, and in Colab it got something like 2.5 hours to download this entire period of data. All right, so that pretty much wraps up this video, and again I will be uploading videos pretty frequently in the subject of data science and deep learning. So if you have not subscribed yet, do subscribe, and if you like this video, smash the like button. See you in the next video. Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. So in today's video, I'll be doing a Bitcoin price prediction with LSTM, long short-term memory network, which is a special form of recurrent neural network. And for this entire project, I'll be using Tensorflow Keras implementation of LSTM. But before we get into the code, a quick introduction of LSTM. I will not go into the detail because that will be a topic of a separate video altogether. But here, just a 2-slide introduction of the basic structure of LSTM. So LSTM are a special kind of recurrent neural network, but instead of simply feeding its outcome into the next part of the network, an LSTM does a bunch of mathematical operations so it can have a better memory. A typical LSTM network is comprised of different memory blocks called cells, the rectangle that we can see in this image, and there are 2 states that are being transferred to the next cell, the cell state and the hidden state. The memory blocks are responsible for remembering things, and manipulations to this memory is done through 3 major mechanisms called gates. And at a high level, LSTM works very much like an RNN cell, recurrent neural network cell. It is of three parts as seen in this image, and each part performs an individual function. The first part chooses whether the information coming from the previous timestamp is to be remembered or is irrelevant and can be forgotten. In the second part, the cell tries to learn new information from the input to the cell. And at last, in the third part, the cell passes the updated information from the current timestamp to the next timestamp. And these 3 parts of an LSTM cells are known as gates. The first part is called the forget gate. The second part is known as the input gate, and the last one is the output gate. Now, these are the 3 main key points that I would like to mention about LSTM, that unlike a standard feed-forward neural networks, LSTM has feedback connection. It can process not only single data points, but also entire sequence of data. And then LSTM are explicitly designed to avoid the long-term dependency problem. Remembering information for long periods of time is practically their default behavior, not something they struggle to learn like RNN. And also lastly, LSTM don't suffer from problems like vanishing gradient or exploding gradient. And now I'll start off with the project of this video, which is to predict Bitcoin prices with the use of LSTM, and I'll be using Tensorflow Keras implementation of LSTM module. So this is the typical import first, that I have pandas, numpy, datetime, matplotlib, then sklearn, matrix, mean squared error, mean absolute error, all these standard modules of sklearn, which I will be needing in this project, and also the min max scaler for scaling my price data of the Bitcoin, and of course TensorFlow. And then from TensorFlow.keras I'm importing sequential, Danes, dropout, and LSTM. And then for plotting I'll be using matplotlib and also the plotly library. So I'm importing the plotly library and few of the important modules of plotly here. But the first point is about getting the historical price data of Bitcoin, and for that I have made a separate video, the link of which I will attach in this video. Here right now in front of me is a very simple code for doing that. That is to fetch all the historical prices of Bitcoin right from 2015 up to October 30th of 2021. And so I'm using these particular package of historical data. With this package, with a single line of code, pretty much you can download the entire historical data. Of course, like I said again, I have made a separate video, and the link is down in the description box. So here is pretty much that line, a single line of code with this historical data package. It's available in the PEEP repository. And to this module of this package, you just pretty much have to pass the ticker of the cryptocurrency for which you want historical data, in this case BTC USD, the granularity of the timestamp, that is if you want per minute data, you have to supply the 60. The 60 here represent the number of seconds in a minute, and the start date from which you want to fetch the data, and the ending date, and then invoke this function retrieve data. With this, pretty much you get the entire per minute BTC data, historical data between this start date and this end date, and it will be fetched as a data frame, and then I downloaded that data as a CSV file, and then use that CSV file. I will also actually share my CSV file in a Google Drive and in Kaggle. So I will leave the link of those two sources of the data in the description of the video. So with that line of code, with the historic package, I have downloaded the historic Bitcoin data from 2015 October up to October 30, 2021, and I saved that as a CSV file. So my first step here in this notebook is to read that data, read that CSV file, and check out the data frame that I have got. And for that, this is a code. I have the first, what I'm doing is the root path. I'm defining this root path because this is in my local machine. This is a CSV file where I have saved these historic data, and the CSV file name is BTC OHLC October 2015 to October 2021. And then I'm just doing pd.read CSV. And then reading the last. Remember, I'm not using head here. I'm using tail to read the last 5 rows of this data. Let's run this cell. Awesome. Now I have this data set in this format. It's a OHLC data, open, high, low, close, and volume. And this is a time column. This is a very important because my entire LSTM and my time series, etc., will be built based referring to these column, which has a time stamp. And you can see that this is the data for each minute. So this is 1 minute, and then this price is the next minute, and then the third one is for the next minute, and so on, because the entire data is for taken on each minute basis. Because while fetching the data with the package, I mentioned the granularity to be 60, that is 60 seconds. So for each 60 seconds, the data is fetched. All right, now let's quickly check out the shape of this data. You have the shape. All right, it's a huge number of lines. 31,013,276 is the total number of samples, the total number of price points we have. that is from 2015 October to 2021 October for each single second of Bitcoin trading data. That's 31 million and 13,000 number of rows. All right. And now I want to quickly check the overall status of the data, its key characteristics. So I'll be using the describe function of pandas. Cool. So this gives me the overall status. For example, the mean count, 25 percentile, 50 percentile value, etc. Of the entire data frame. And also I want to check the info of this data, which is important. So df.info, let's run this code. Okay, so this gives pretty much the type of the various features of this data set. So I can see that the time feature, the time column is object type. And this is a problem because I want the time column to be of date time format, so I can run my time series and LSTM etc. on this. So we'll convert these column to time date time format in a second. But before that, check out the other columns: low, high, open, close, volume, all are of float 64, and that's fantastic for me. So let's now convert this time column to date time format. And remember, what was my time column? My time column was this, that it gives me the timestamp of the BTC trade. Now, before I convert these time column from object D type to date time D type, quickly understand one particular important point about time series is that time series need to be converted to a particular format before it can be fed into a supervised learning model such as LSTM. LSTM is a supervised learning algorithm. So because a supervised learning algorithm requires its data, its input data, to be in a particular format or in particular samples format, where it has two components. Now, one is the input component, which is called X, and the other one is output component, Y. And so I also have to convert these time series data, that is the historical Bitcoin prices of the last 3-4 years, into this particular format of X and Y component. For example, let's take this univariate time series 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is just a vector representation of timestamps, and this is a univariate time series. Now, for a univariate time series problem that is doing a one-step forecasting, I can use the observation at the previous time point as an input and the observation at the current time point as an output. For example, these 10-step univariate sequence can be expressed as a supervised learning problem by doing a little bit of conversion, something like this. And what is this? So the first three part of this vector, that is a 1, 2, 3, taken from this vector 1, 2, 3, and 4 is here. So this 1, 2, 3 is the input and 4 is the output for this part. And then in the next sample, 2, 3, 4 is the input and 5 is output. Similarly, for the last part of the matrix, 3, 4, 5 is my input and 6 is my output. So what I'm doing is the input is 3 time steps and the output is 1 time step. And during the model training, my whatever model I use, for example, in this case, my LSTM model is learning these samples, that is going through this mapping of input and output and learning this entire sample. So for this case, I have 31 million total number of price points, and I can divide these price points like this, and the LSTM model will learn the 3 previous timestamps, which is the input, and the current timestamp, which is the output. And now I'll be converting the time column from object D type to date time D type. And I am going to use pandas as type function. This is very handy when you want to convert any particular D type to another type of a data frame. All right, so I'm just using to the as type function, I'm just passing this dict, that is the time column. I'm converting it from object to date time 64. So this is the target D type that I would like to have. Let's run this code. Okay, it completed running, and now I will be just checking if the D type got converted indeed with info function. Um, I'm still getting time equal to object. Oh, sorry. It should be. I created a new variable df date type. So I was just checking the original data frame. Where indeed it's actually good that I was checking the original data frame. The original data frame, I have the time as an object d type, and now check the same for date type. This variable. Let's run it. Awesome. Fantastic. So now my time has been converted to date time 64. Fantastic. And other column remains float 64. And now I'll be checking the total number of null values in my data frame. So I'm using these is null function, and then I'm summing all is null function with the sum function. So let's run these. Yeah, so I have zero null values. That's actually good. I do not have to deal with the null values in this case. This data is already very well formatted and cleaned. This data was actually fetched from the Coinbase Pro API, because the package that I used for fetching this data is historic. That was, I think, historic cryptocurrency price or something. Anyway, I will give the description of the package name that I used, and the data. This package under the hood, it hits a Coinbase Pro API, and I can see that the Coinbase Pro API already gives you a very clean data set that is zero null values. But I am going to check another way, that if I have any null values, just to be doubly sure. So I'm also checking values.any. So if I have any null values, it will give me it will return me a boolean that is true, and if I have zero null values, it will give me false. All right, so if any null values is false, that means I do not have any null values in this data frame. And now I'll be plotting a particular plot called lag plot, because my data is time series data. That is, I have 31 million samples of Bitcoin prices, and for each timestamp of 1 minute. And lag plot gives me some valuable information in terms of figuring out if the data has some seasonality or follows any pattern, etc. So looking at these official documentation of pythonic.com pandas plotting, you can check out what drawing a lag plot on its time series data gives you. So just quickly, I'm reading these overview key points. A lag in a time series data is how much one point is falling behind in time from another data point. And in our case, it's 1 minute, because I downloaded the data on a 60-second interval. So in a time series data points are marked over time at varying degrees of intervals. To analyze and find out if a time series data follows any pattern, a lag plot can be employed. A lag plot is drawn by representing the time series data in x-axis and lag of the time series data point in y-axis. For a data point, if the order of the lag is 1, the lag is the previous data point. If the lag is 2, the lag is data point before 2 data points in time. By drawing a lag plot, patterns like randomness, trends, and seasonality can be searched for. All right, that's beautiful piece of key information on lag plot. Now let's draw them. So here in this cell, I'm pasting the code for my lag plot. Just remember these important parameter here, the lag equal to, so I'm using 1 minute lag by defining lag equal to 1. For hourly lag, I have to choose 60, because my previous data point need to be 60 lag behind, or 60 timestamp behind. Similarly, for whole daily lag, I have to choose 1440 lag behind, because remember from the original document that we just seen, this important point, that for data point, if the order of the lag is 1, the lag is a previous data point. If the lag is 2, the lag is data point before 2 data points in time. Okay, so here I am plotting with the subplot function, total 1 2 3 4 5 plots for minute lag, hourly lag, daily lag, weekly lag, and monthly lag. And mainly the purpose of these plotting for me here is to check the correlation pattern or autocorrelation pattern in the data set. That is, whether my price is mostly correlated with minute lag, daily lag, weekly lag, monthly lag, and accordingly my LSTM model can have similar kind of time series data to get the feed from. All right, let's run this cell. I think it may take a minute or so to run because it's a lot of data, 31 million rows of data. And after the plotting code finished running, it took 36.6 seconds. This is a plot I got, and the main interpretation of this is that on a minute basis, of course, the obviously the time series is extremely the correlation is very high, the price autocorrelation is very high, and as we go down we can see that on a weekly basis the correlation substantially decreases, and on a monthly basis there is almost no correlation at all. So now I want to resample my data set on a larger time scale. That is, my original data was on a minute time basis, but I want to reduce the overall number of samples. So I want to use a group by function of pandas to resample data set on a larger time scale. But I can see that I cannot definitely take weekly time because the correlation almost breaks down from here. So, but on a daily basis, the autocorrelation still holds. So I'm going to resample my 31 million rows of data set on a daily basis. So I will group by the price points on a minute basis to a daily basis. Let's do that. Now, before applying the group by function to convert my 1 minute based time series data to daily basis time series data, I want to create a separate column here with the date time format. So so that I am keeping the original time column untouched. I'm just creating a new column with the name of date, and all I'm doing in this line of code that I'm making use of these pandas to datetime function, which converts an argument to datetime and passing unit equal to s. What unit equal to s is doing is it will interpret the number given to datetime function as that many number of seconds away from the origin, and the origin is defined as the time point from which that many seconds away this time is. So yeah, so with this, just quickly run this code cell. And all right, so now I have this new column named as date, and it has all these dates. And as you can see the I'm just printing the head, and you can see all these initial 5 rows have 1030, because like we said that our original dataset has a 1 minute gap of prices. So now I have to apply the group by function on it. Let's quickly do that. All right, this is my group by function, and what this is doing is that I'm grouping by these previous data frame by date. And then in the next line, I am taking the close price because I have the OHLC price here, that is open, high, low, close, but I'm only interested in the closing price at each time point or at each time stamp. So I'm taking the close, and I'm also taking the mean of that because now I'm grouping by date. So I want the mean of each day to be the number that I'm interested in. So let's run these. Okay, before running this, I just want to check the shape of my previous data frame, that is BTC input df date type. 1 second. So HFE. Okay, let's run this. Okay, as you can see, I have 31,013,276 samples because this data is on a single minute gap basis. And now I'm grouping by date. Let's run this code. All right, and now check my new data frame head. Cool. So this is my new data frame that I just created with having only the closing price and on a daily basis. That is because I'm grouping by date. Now quickly check this shape as well. Closing price, group by date. No, not this. DF ATC. closing group by date. Yes. Dot SAP. Cool. Now you can see I have only 2,196 samples because all these these original 31 million samples have been compressed into on a daily basis, and yeah, so that's what I want. So this variable BTC closing price group by date, this becomes the final variable on which holds the entire time series data on a daily basis, on which I will be running my LSTM model. So now I will be doing a train test split of these BTC closing price group by date variable, and for the testing set I'll be holding a sample of 60 number of samples for my testing, and then I will be taking, that is from this entire BTC closing price group by, I will be taking 60 as a test sample and the rest is my training sample. And the code is pretty simple. I'm just making use of, this is a code. Let's read this code. So all it's doing is making use of the Python slice notation with the colon to extract few things from an array. So the first line, I am taking the df train, and that's making use of this line, that I'm taking items from the beginning through stop -1, this particular line. So it's taking all the values from the beginning till the length of the entire data minus prediction days, and my prediction days is number of 60 days. So it's taking all the values starting from the first element up to a certain values, that is before up to the prediction days. And the second line, my df test values are taking all the values starting from a particular index till the end. And what is a particular index? That's from the entire length of my data frame or the series, and minus the prediction days. That's my starting value, and then taking all the rest of the values, because the colon here is at the end. Now let's quickly check the shape of these df train and df test. So df train.shape will give me 2136 samples, and obviously one column because I have only the close prices. And similarly check df test.spe, and that's the rest of the 60 number of days. Okay, now I'll be plotting a time series for this value. But before plotting, quickly make sense of these df test and df train. That 2136 is my train, and that's because, remember, our absolutely original data set was 31 million rows, and but after grouping by, I got my data set to be 2196, because this is after the group by function was applied, and I got a daily basis data instead of minute basis data. And then on top of that, I applied this train test split to get my train set of 2136 and test set of 60. All right, now I just want to build a plot and plot a graph of my train set, and this is a code. And yeah, so this will give me the a simple plot of my closing prices. Let's just run this code, and it's very simple code. I'm just making use of the matplotlib library and setting set y level to be price USD, and yeah, that's pretty much it. Let's just run it. Okay, I got the plot, and this is my plot of the daily basis Bitcoin prices. Okay, actually I did not need to have this chosen column equal to close line. I'm just deleting them. All right, now after this plot, I will be scaling the data, because I need my training set and the test set to be scaled, and I'll be using a min max scalar function of scikit-learn. But just one important point to mention here, that scaling must be done after the train test split has been done, because if you do the scaling before train test split, then you will pretty much introduce data leakage from the test set to the training set, because the whole training, the training process will get influenced by your test set as well, and obviously it will result in bad prediction from your model. So let's do the code for this. Is the code for scaling. So I'm just using a scalar and applying min max scalar with feature range 0 1, and similarly for the test set as well. And then I am applying the fit transform to get my scaled trend data and scaled test data. So that was my min-max scalar, and if you just want to print that what form of data it outputs, actually min-max scalar will transform each of the data point between a range of 0 and 1, and I'm just printing these scaled trend value now. And this is the array like this, and all these values are between 0 and 1. You can just quickly see that there's an expression e here. Actually this value, all of these are between 0 and 1. Similarly, I can print scaled test. Yep, this is the values for scale test, and here also all my values are between 0 and 1 indeed. All right, now after scaling is done, now I will be making my data generator function, because I have to make my data ready for LSTM model feed. Let's do that. So for this, I will frame the problem to take a window of the last so many number of days of data to predict the current day's data. To achieve this, I will define a new function named dataset generator LSTM in a second that will split the input sequence into windows of data appropriate for fitting a supervised learning model like LSTM. For example, if the below sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this is just imagine this is my time series data. This is my univariate time series data with 10 time steps. Then the sample for training the model will look like this. That is, I have input 1, 2, 3, 4, 5, and 6 is the output. Then for the next sample, I have 2, 3, 4, 5, 6 as the input, and 7 is the output. And so the same for the last one. So what's happening is these 5 numbers, this is my input and this is the window size. So this is the window I'm looking at. And this is my output for this window. And this is because LSTM expect each sample in the dataset to have 2 dimensions. The first is the number of time steps. In the above case, it is 5. And second is the number of observation per time steps. In this case, it's 1, because for each of these value that is input, each of the sample, I have 1 result or 1 output value, 1 observation. And because overall it's a regression type of a problem, I will use a linear activation function in the output layer and optimize a mean squared error loss function in my LSTM network. And I will also evaluate the model using the mean squared error metric. And the next one is to defining a look back period. A look back period defines how many previous time steps are used in order to predict the subsequent time step. For example, if I set the look back period equal to 5, then that means I am using the time series steps at t-4, t-3, t-2, t-1, and t to predict the value at t+1, which is the case here in this case. That is, I'm using 1, 2, 3, 4, 5 to predict 6. I'm using 2, 3, 4, 5, 6 to predict 7, and then I'm using 3, 4, 5, 6, 7 to predict 8. And now I'll be defining the look back function actually, but before that, a very quick glance at how the Python slice notation works. That is, in this 1:5 is equivalent to from 1 to 5, 5 not included. Then 1: is equivalent to 1 to end of a series or list, and then len of a and then colon is equivalent to from length of a to end, because I'll be making use of this kind of slice notation in these subsequent function that I'm going to write. So here is my look back data generator function. So all this function is doing, one second, let me position it. Okay, so all this function is doing is it takes a single data set or single series of data set, which is an argument, and the look back period by default it takes 5. Of course, I can pass a different look back if I want, and all this function is doing, it will give me two sets of series, train x, train y, and divided according to these look back period length of window size. So it will extract each window size of data and then append it to a series, and also for that window size it will define a single value to be the output value. Like I just explained here, that given a whole series of 1 2 3 4 5 6 7 8 9 10, this function will give me data set like this. The first five series, first five numbers of this series are taken to be the input or x value, and then 6 is my output value or y value. Similarly, for the next sample, this series 2 3 4 5 6 is my input value or x value, and 7 is my output value. And this function is implementing that concept through these looping range. That is, it is looping through these range length of the data set minus lookback period, and then creating for each of this lookback period, it is creating an array and then appending to my data x variable, that is this one. And similarly for each loop, it will continue to append till the entire range looping is done. And so the important line, most important line is pretty much this, that is for each window size x, the data set is making an array extracting data from I up to I plus look back period. That is, if my look back period is 5, it will give me 5, it will give me 5 number of input or 5 number of values to form a series, and then that series will be appended to these data x, and this will continue for the entire range loop. And similarly for each of the loop, I will also create this data y. Data y will have a single value appended to it, and that value is just this value, that is I plus look back period, that is the number positioned at this index. And okay, and then after these data x and data y is completely ready, then from this function I'm returning this data x and data y as a numpy array. All right, and now after this function is done, I'm just creating two data sets, that is train x, train y, and test x, test y by invoking a dataset generator LSTM and passing it my scaled train data and scaled test data. These two we already have created in the previous step. And let's quickly check that how the form is coming. So this is my train x. If I print my train x here, let's run this code, and I get this kind of data. You can see this is a two-dimensional array, and each of these inner array has 5 elements, because my look back period by default was 5, and that's exactly what I have used in this execution of this function. So each of these internal array will have 5 elements, and this is my you can imagine this is the x value. That is, as I discussed earlier, that LSTM requires a data set in a particular format. It will require a component which has x component which will be input, and a y component which will be the label or the output value. So, and similarly, that's the kind of data structure I'm getting here. That is, train x consists of many arrays, and each array will have 5 number of values, 1 2 3 4 5, and the next array will again have 5 elements, 1 2 3 4 5. And let's quickly check a particular pattern here. Let's take this number, that is the last element of the first array, 4.9069 and so on. This is the last element in the first array. Now take the second sample. These 4.9069, it has come here in the fourth position. So in the first sample, it was the last position or the 5th position value, but in the next sample, it has come to the 4th position. In the third sample, it has come to the 3rd position, because it is progressing accordingly. Like we just saw in this example, that if my whole input series of a univariate time series is 1 2 3 4 5 6 7 8 9 10, and I need to make a data set structure like this, that is, the first 5 value will be my input, 6th value will be my output. So this fifth position element will become the fourth position element in the second sample, and will become the third position element in my third sample, and it will go on like that. In the fourth sample, this fifth position element will be my second position element. So that's exactly the kind of output I am getting here in train X. Similarly, let's print the train train Y. That, remember, train Y is a will have a single number for in it, because for each of my input series there is a single output. So let's print that. Yeah, and that's what I'm getting. It's a one-dimensional array, and I'm for each position I have a single number as its element. And I can also check similarly my test. This will be test X and test Y. Yep, test X as well. I have this kind of two-dimensional structure, and in each of the inner array I have 5 numbers denoting the input numbers. And so these are 5-element array. This is a 5-element array. This is a 5-element array for test X. And similarly for test Y, I will have a structure like train Y. Let's run this. Yeah, this is a single array with and each position has a single value, because test Y, remember, it's a label of the output. And for each of my test X inner array, I will have a single test Y value. All right, and in the next cell I will be just printing their structure, that is overall shape. It should match. Yes. So I have train X, I have 2131 sample, and the column number is 5, exactly how I expected it, because this is a matrix with 2131 samples and column values are 5, because the 5 are my input values or input vector. That is, you can also imagine this is a 5 features. And train Y is will have a single. There will be no one single column, but the number of samples should match, and it's matching. And similarly for test Y, this is actually will be test X. Yeah, test X as well. I have 55 samples and 5 columns of 5 features, and test Y as well, 55 samples and single column value. I'm talking so much about this structure because for LSTM, your dataset must be compatible with the structure. If your structure becomes wrong, your LSTM will never run or will run incorrectly. So you have to understand your data structure very well, and you have to change or transform your original time series data in the format that LSTM accepts. And now I will talk about one of the most important part of running an LSTM model, which is about restructuring your input data to be of shape of a 3D tensor of samples, time steps, and features. Here are the definition. So sample is just a number of samples in your input data, which is the length of your data X or the amount of data points you have. The next one is time steps. Very important and very crucial to understand this particular variable. So a sample contains multiple time steps. That is the width of the sliding window. This is what time step is. And in my example here, I have used time step of 5. Note here that time step is distinguished from the sliding step of the sliding window. So time step is equivalent to the amount of time steps you run your recurrent neural network. And lastly, features. This is the amount of features in every time step. If you are processing pictures or images, this is the amount of pixel. In this case, I have one feature, that is the price of Bitcoin per time step. So finally, this is kind of the Python implementation of this restructuring code or reshaping code for your input data. So you have to reshape your data X into this form, that is length of the data X, which is the number of samples. Sequence length is the time steps, and feature is the number of features. In this case, it's 1, so I have put 1. The Keras official documentation as well mentions it very clearly that for LSTM. So this is a page that I'm looking at for recurrent layers LSTM under the Keras official documentation at keras.io. So they clearly mention that the inputs must be a 3D tensor with shape, batch, time steps, and features. And so in Keras, the number of time steps is equal to the number of LSTM cells. This is what the word time steps means in this 3D tensor. So to summarize again, in this 3D tensor, the sample one sequence is one sample. A batch is comprised of one or more samples. In our case, we have like 2,100 samples in the train X. Then the time steps, one time step is one point of observation in the sample. And features, one feature is one observation at each time step. So to understand this concept very well, let's take this example where I will be running an LSTM with single input sample where you have one sequence of multiple time steps and one feature. That's it. So this is my time series, single sequence of time series data with values of 0.0, 0.1, 0.2, 0.3 and so on. And each of these is a single time step. And now I have to, the target is that I am given this single series and I have to run an LSTM on this time series data. And so for that, I have to restructure this data to a 3D tensor, which is must for LSTM. So for that, as a first step, what I'm doing is I'm defining this sequence of number as a numpy array here in this line using np.array and passing this entire series. And then in the second step, the most important step of reshaping this input data, I'm using the reshape function on the numpy array to reshape these one-dimensional array into a three-dimensional array with one sample, 10 time steps, and one feature at each time step. That is 1, 10, 1. This is my number of samples, this is my number of time steps, and this is my number of features. The reshape function, when called on an array, takes one argument, which is a tuple defining the new shape of the array. I cannot just pass in any tuple of numbers. The reshape must evenly reorganize the data in the array. So I can only pass compatible number of number as the tuple to the reshape function. And once reshaped, I can print the new shape of the array. Let's run this cell that if indeed this one-dimensional array got reshaped into a three-dimensional array. And it indeed got transformed into the kind that I wanted. That is, it's now a three-dimensional array, and the shape is clearly saying that it's 1 by 10 by 1, which is exactly the format that I wanted. I can indeed also check the whole data by printing the data, the whole data itself in this cell. Let's run this cell. And you can see it's a three-dimensional array like this. So I have got 10 the innermost values, which is my number of time steps. And yeah, so this data is now completely ready to be used as an input or the X value to the LSTM model that I want to run. Let's check out that the exact code for running these LSTM model on this data. So this will be the code. I'm just defining a model to be sequential, then adding an LSTM layer, and input shape is 10, 1, and then I'm adding a model.add 10 so on, and this model is definitely will be compilable. That is, I can then compile this model and then apply the fit function on this. But I'm not running this now because I will be running my LSTM model on the actual Bitcoin data that I have. So now I'll be doing the exact same reshape that we just did on a single series of data in the previous step on my actual data of Bitcoin. So, but first let's check the shape of my train X and train Y. So this is my train X and my train X and test X. Okay, this is what the shape I want to check. Let's run this cell. Okay. Remember these exact thing we did a minute earlier in our previous step here. Yeah, we already have checked these train X, train Y, test X, test Y shapes in our previous steps. And how did we got these train X and train Y is by invoking this function, our dataset generator LSTM. Because remember again, just repeating again, the dataset generator LSTM takes a scale test and scale train, that is the dataset, the whole dataset, and then it restructure this dataset into test and train, like this: train X, train Y, test X. Yeah. So now these final train and test dataset, I have to reshape it to conform to my LSTM input structure. So trainx dot shape gives me this tuple of 2, 1, 3, 1, and 5. And for reshaping, I need my samples to be 2, 1, 3, 1. And to extract that, I can just do like this: trainx dot shape and 0. That will give me 2131, and this is the number I need for my reshape. So in the next cell, this is what I'm going to do: LSTM input trainx and testx must be reshaped into a 3D tensor of samples, time steps, features. I'm repeating this again and again because this is like one of the single most important thing before you feed your LSTM model with your training data. All right, now the code will be here. Yeah, this is my reshaping code. So look at the first line. I'm here in this line, I'm reshaping train X. So to the reshape function, numpy reshape function, I'm passing train X as the first argument, and then I'm passing the whole tuple, that is the exact structure of the reshape that I want. And the first element of the tuple is trainx.shape 0, because we already saw the trainx.shape 0 will give me the number of samples, which is what we need in the first element of the tuple. And the next, I need the time steps, and I already decided that my time step would be 5. And these trainx.shape also gives me the times. The second element of this shape tuple is 5, and so that's why I am giving trainx.shape and 1. That is this element 2131 by 5, because 5 is my time step. So this time step again is the number of look back period. That is, I'm looking back in the time series. I'm looking back 5 periods, which is my input, and the 6th one will be my label or my y value or my predicted value. And this is what the time step is. And then the final number in these reshape is the number of features. And again, we decided that the number of features in my case for this particular project here is 1, because at each time step I have one single value of the Bitcoin price, and that's why I'm just passing here in the number 1. So this was the reshaping for my train X, and exactly the same procedure for test X as well. Here, just instead of train X, I'm passing test X. And let's run this code. Fantastic. I got shape of the train X to be 2131, number of samples. Time steps 1. Always remember this structure, these 3D structures. That is input shape of LSTM needs to be samples, time steps, features. And this is my samples, this is my time steps, and this is my features. Awesome. And now finally, let's take a good look at the whole of train X after this reshaping. Yeah. So this is my whole of train X, and it's a 3D tensor. Just after reshaping, that's what we made it to be. And you can see that the number of sample, each of these is a sample, and each sample has 5 elements in it, because we have 5 time steps. So this is the first sample, and it has got 1, 2, 3, 4, 5 elements. Similarly, this is the second sample, and it has got exactly 5 elements, and so on and so forth. And yeah, and this is the last sample, which also has got 5 elements: 1, 2, 3, 4, 5. Now that my LSTM data input is completely ready to be fed into the model, I am very much ready to run the LSTM model, but before running that, I just want to go through the most important two parameters that I'll be using in this model before compilation, which is input shape and the return sequence. So input shape is one of the arguments or parameters to the LSTM model, and input shape is supposed to be of this form, or of this tuple form, the time steps, and the next one is number of features. To give you an example, if I am observing the amount of rain and the temperature each hour for 24 hours in order to predict the weather, that is whether of 1 is good and 0 is bad, and I do this for 365 days, I will have 365 samples, each of which will have 24 time steps and two variables, one for rain, which is good, and one for temperature. In this case, in this particular form of my input sample or the input data collection, my input data will have a shape of like this: 365 by 24 by 2. This is the number of samples, this is the number of time steps, that is each time step for which a reading was taken, and the number of features, number of labels. This is 2 because I have 2 labels. And the input shape parameter for this input data will be 24 by 2. 24 is the time steps and 2 is the number of features, so the number of labels. And the next one is return sequence equal to true. This is another very important parameter when you stack one LSTM on top of another, that is you use multiple LSTM layer structure. Normally return sequence defaults to false, which is the default value of return sequence. So the reason it is required when you are stacking LSTM, that is the original LSTM model is comprised of a single hidden LSTM layer followed by a standard feed-forward output layer. But in the stacked LSTM structure is an extension of this original LSTM model and has multiple hidden LSTM layers where each layer contains multiple memory cells. And in this case, you must set return sequence equal to true when stacking LSTM layers so that the second LSTM layer has a compatible n-dimensional sequence input. Because to stack LSTM layers, I need to change the configuration of the previous LSTM layer to output a compatible n-dimensional array as input for the subsequent layer. I can do this by setting the return sequence argument on the previous layer to true. This will return one output for each input time step and provide the compatible n-dimensional array. Now the fundamental question is why I increase the depth of an LSTM, or why I add layers or make it a stacked LSTM structure. Simple answer is that it is the depth of a neural network that is generally attributed to the success of the approach on a wide range of challenging prediction problems. The additional hidden layers are understood to recombine the learned representation from prior layers and create new representation at high levels of abstraction. For example, from lines to shapes to objects. And in the case of LSTM, given LSTM operate on sequence data, it means that the addition of layers adds levels of abstraction of input observation over time. In effect, chunking observations over time or representing the problem at different time scales. So stacked LSTMs now has become a stable technique for many challenging sequence prediction problem in the industry. And now finally my final LSTM model. This is the code. So I am first creating a regressor variable with the sequential module of Tensorflow, and then I am adding the first LSTM layer here, this line. And activation function is relu, return sequence true, because I will be stacking LSTM structure, like the second LSTM structure will be below here. Input shape, again, like we discussed, this is the trainx.shape1 and trainx.shape2, because our remember our input shape was time step and number of features. So these first element of this tuple, 1, that is train x dot shape 1 is my time steps, which is 5, and shape 2 is my number of features or number of labels, that is 1. So I'm also adding a dropout with 0.2 to avoid overfitting. And like we discussed again, that this return sequence is true because I'm stacking the next LSTM structure, and to make the number of dimension compatible with the previous structure, I have to make return sequence equal to true, otherwise the default value false will be taken and I will get the dimension did not match kind of error. Yeah, so this is my second LSTM layer in the next line here in this line, and again input shape remains the same. Train x dot shape 1 is 5, which is my number of time steps, and dot shape 2 is number of features, which is 1, and I'm also adding a dropout of 0.2 here after these LSTM layer to avoid overfitting. And note one thing, that here in this layer I'm not adding return sequence equal to true, because after this layer the final dense output will be given. So for this I do not need to specify return sequence equal to true. It may take the default value of false. And lastly, the dense layer, the fully connected dense layer. And then let's check out this whole model by running regressor.summary, which will print the summary version of my model before compilation. So this is what the summary printed. I have my this is the first layer, second layer. Okay, so now I'm ready to compile. Let's do that. Now let's compile and train the model. Here is the code. Let's go for this code line by line. So first I'm importing these from the callback module of Keras. I'm importing model checkpoint and early stopping because I'll be using these to have more control over my model. You normally use model checkpoint and early stopping as a best practice so that you can save the model at various checkpoint or after each epochs. And also the early stopping is for stopping the training when the best loss is reached. So first, my regression function comes from my previous cell, that when I completely structured my model as a last step, regressor.add_dense, and we also printed regressor.summary. And so I'm starting the compilation on this regressor, that is regressor.compile. I'm using the optimizer to be Adam loss as mean squared error because, like we discussed earlier, this is a regression type of problem, and hence I'm using the MAC as my loss metric. Checkpoint path, I am defining it to be a file which is in my in the same folder like in this notebook, and that file name is mybestmodel.hdf5. And then I'm mentioning the various parameter of my checkpoint, which is file path is this, that is checkpoint path. Monitor, I'll be monitoring the loss value, verbose equal to 1, safe best only equal to true, model is minimum. And early stopping, again I am making use of this early stopping callback module. This will stop training when a monitored metric has stopped improving. Fantastic, that's what we want here. And the monitor parameter here is value loss. And otherwise these are kind of almost a standard parameter number, patient sustain, and restore best weights equal to true. And then I'm defining this callbacks array to be checkpoint and early stopping. And then this is the final and the most important line, which is at this line the training will start. And I am making use of these regressor.fit function. I definitely recommend you go over the fit function official documentation in Keras and read through this great well-written documentation. And I'm outputting the entire result to this history variable. And to the fit function, I'm passing train x, train y, because my train x, train y is a train input data that has been reshaped and ready to be trained. Batch size equal to 32. Epochs, I am giving a large number of epochs, pretty much 300. but I definitely suggest before first, when you try this code, run with one epoch and see that the entire thing is running properly, and then you increase your epochs. And otherwise, validation data is my test X and test Y, because remember, we kept 30 samples to be our validation set or test set, and callbacks, I'm passing these to callbacks. That is, we already defined here checkpoint and early stopping within this callback variable. Now let's run this cell, but it will take I think some time. So I just started executing this cell, and you can see that the epochs are going one out of 300, 2 out of 300. It will take a couple of minutes. So the training ran for like 1 minute, and then after 134 epochs, I got this, that val loss did not improve from 0.00808. That means because of my callback function implementation, the early stopping mechanism already checked that at which point I got the best loss, and at which point, after which epochs, the loss did not improve anymore. And that's my 134 epochs. And here the val underscore loss, this particular value actually stands for validation loss. So that's where my training stopped, and now I'll be plotting a graph comparing my training loss and test loss or validation loss. But before that, quickly check the difference between loss and validation loss. So I found this pretty beautiful data science stack exchange answer here, that is Keras difference between validation loss and loss during training. Because to plot my training loss and test loss, I need these two variables, validation loss and loss, which I can get from the result after the training. So quickly check out the great answer that somebody has given here. So this answer is really beautifully explains that a validation loss is a value of cost function for your cross validation data, and loss is the value of cost function for your training data. Remember, during the fit function of my training, let's quickly check out. I actually had to mention these validation data. So my training data was train X and train Y in the regressor.fit function, and in the validation data I clearly gave these validation set in tuple form, which is test X and test Y. And that's what they are saying, that the validation loss is a value of cost function for your cross validation data, and loss is a value of cost function for your training data. On validation data, this is very important, this is really important. On validation data, neurons using dropout do not drop random neurons. The reason is that during training we use dropout in order to add some noise for avoiding overfitting. During calculating cross validation, we are in the recall phase. And not in the training phase. We will use all capabilities of the network, and hence during calculation of cross validation loss, we do not the neurons do not implement any dropout, because the dropout has already been implemented during the training phase. All right, let's go back to our code, and now what I'm going to do is plot the line graph to show loss numbers relative to the epoch. So for this, first remember that the result of our training was saved in a variable called history, that is regressor.fit. This whole training output was saved in this history. So from this I can get the values of val loss and loss, that is validation loss and loss. So the code is for plotting these loss number relative to the epoch is this. So all I'm doing is I'm extracting from the history variable history.history loss and history.history val loss. So this validation loss is my test loss, and the simple loss is against my training data, which is my train loss. And then pretty much I'm just plt.show, and that should plot my graph, and this is my graph. So this blue line is for training set, and this line is for my test set, and obviously the training loss is much lower than the test loss. but test loss continues to go towards a low end as the epochs increases. And now I will be doing the actual prediction from the LSTM model using test X and plotting the line graph against actual test Y. But before that, remember previously we scaled or normalized our dataset using the min-max scaler, which converts the original real values, the real numbers of the price, actual Bitcoin price, into a number which is scaled, that is between 0 and 1. So now I need to transfer this scale to the original data set. That is, I need to convert back the scaled values to the original real values of Bitcoin prices. And for that, I'm going to use a function of scikit-learn called inverse transform. But before applying the inverse transform, first I have to predict the values. That is, I have to invoke the predict function of Keras module to get the predicted values from my test X dataset. So, and now this is an important step. I have two ways to get the predicted values. One is applying the predict function on the regressor variable that we already have defined earlier, that is regressor. We run the fit function on the regressor variable, or we like you remember, we have our checkpoints file saved during the model training because we use a callback function and we implemented checkpoints and early stopping. So the checkpoints have already saved our model, our trained model, in a file, and we can get the that file and apply the predict function on that trained model. So we will do it in both ways, but first check the code for applying the invoke function on the regressor variable. But quickly check what is the regressor variable I'm talking about. So during the training, remember, we ran this regressor.feed on these. So this is a regressor variable that I'm referring here, and that was defined at the top here. Regressor.compile. Okay, here. So initially, at the very first step of this entire model training, we defined this variable regressor, and that was equal to the sequential class of Keras. And then we added all this LSTM, all these layers to that regressor, and then finally ran the fit function on the regressor. So that regressor is our trained variable, so we can now get our predicted Bitcoin price by this line of this line of code, that is regressor.predict, and pass the test X. That's it. So this predicted BTC price test data, these variable, this is actually the predicted Y values. That is the labels, that is the actual price of Bitcoin, because this is the output of the Bitcoin prices. But going back to our discussion just now, that this variable contains a scaled predicted values of Bitcoin, because our original data set before the training was scaled with min-max scaler of scikit-learn. So these predicted values are also scaled, but now before plotting, like I said, I have to reverse this scaling process. I have to unscale these. I have to reverse this scaling, and for that I need to invoke another function called inverse transform of scikit-learn. The code is very simple, just this. So now I'm just making use of this inverse transform, and of course the scalar test as well. And what is scalar test? This scalar test was defined just before applying the min-max scaler. So let's quickly check. So if I go back all the way back to when I applied the min-max scaler, I think that was immediately after the train test split. Yes. So the scalar train and scalar test was defined to be an instance of the min-max scaler, and I defined the feature range to be 0, 1. That is, my entire scale data would be between 0 and 1. So I have got one variable defined scalar train, and I have got another one same way defined a scalar test. And now I'll be using the scalar test because I am predicting the test set, predicting the Bitcoin prices on my test set. So yeah, here the predicted BTC prices is on test X, and that's why I'm going to use scalar test, and then I'm invoking inverse transform, and to the inverse transform function I'm just passing these the same variable that has just been defined here, which contains a scaled predicted values of Bitcoin, and then reshaping it to -1 and 1. Why -1 and 1 is that is because this represent a column, and that axis I need 1 because this is a y value, it's a single vector. Because all these are actually denoting the price, predicted price of Bitcoin, so the column number should be 1, and this axis I'm keeping it at -1 because I want numpy reshape function to decide whatever this axis value should be. All right, and then my actual test values are again these I need to get by applying inverse transform, because the original test y, this test y is actually scaled, and to get the corresponding original actual values of the prices, I have to, in the same way, I have to apply this inverse transform on my scalar test. So then let's run this cell. All right, now yeah, you can actually now check the values of the scalar test, how this is coming. Yeah. So yeah, see my original data set, this is the original values of this test X, because yeah, so, and if you want to predict, if you want to check the predicted values as well, run this cell. Yeah, predicted values are as well in the original form, that is this has been inverse scaled or descaled with the inverse transform function. Awesome, this is what I need. And now let's clear output. Yeah, now I'll be plotting this data, that is my actual test X and my predicted test X. So what I'm doing here, plt.plot, I'm passing predicted BTC price, that is defined here, and I'm also plotting test actual, that is this variable. So now this plot will show me the predicted values of the BTC price after the LSTM training versus the actual test data BTC price. Let's run this. Awesome. So this is the final plot, and this is kind of the whole purpose of this entire exercise. So this red is my predicted test values, and the blue ones are my actual, and you can see they have almost moving in tandem. So my LSTM model that I've used is not too bad, and of course I could make the LSTM more complex by making the original data more stationary, and also including more layers of LSTM. But my LSTM model was pretty simple, and that gave kind of good result of between the predicted test and actual test. Okay, now I'm going to do the same for my actual train values and actual and predicted train values. So all I have to do, I have to make use of exactly same kind of things, but instead of the test y, I will use train y, and instead of test x, I will use train x. But before that, an important point, these calculations were made by making use of this history variable, that is not history, sorry, this regressor variable. But like I said, I also want to do the same calculation by making use of my trained model that was saved as a checkpoint, because in that case you will also learn to make use of the checkpoint, because that's very important in actual work, in professional work. You would almost always make use of checkpoints, because with a huge data and huge training time, you would want more control. And when you, after training, when you want to load that data trained model back, you almost always make load the trained model from the checkpoint that you have saved during the training. So yeah, so let's do that now. So for that, let's comment out this line, because I am not going to use this regressor variable anymore. Rather, I'm going to load my trained model. So first I need to import these tensorflow.keras.models import load model, because with this module, this function, I can load my trained model from the checkpoint. And then I just need to all right, that's it. So now with this load model, I'm loading the model. So model from saved checkpoint. This variable will hold the loaded model, and I'm loading from checkpoint path. And if you remember, checkpoint path was defined just previously here. Here in the training phase, that before applying the checkpoint, you definitely have to define the checkpoint where you want to save your trained model as a checkpoint. So this was defined here. So this is my checkpoint path, and this is the file name, my best model a.hdf5, and that's exactly what I'm loading here now. Yes, here. And now that model is loaded into this variable, that model from saved checkpoint, now I can just apply it in the same way like I applied previously the predict function on regressor. Now I will be applying the predict function on my model from saved checkpoints, and then the rest of the codes will just work fine. So let's run this cell. Perfect. And let's run the, okay, first clear the cell outputs. And let's run the plot again with now the model is being loaded from the checkpoint. Yeah, awesome. So I got the exact same plot after loading the model from the checkpoint. Okay, now let's do the same for train Y. Okay, now I am predicting on the train set. So LSTM prediction using train X and plotting line graph against actual train Y. Okay, and exact same code, no difference. I'm just so this is a code. I'm just replacing the test X with train X. That's all I'm doing here. And predicted BTC price train data, and then I am again inverse transform, using inverse transforms to descale it, reversing the scaling process. And then this is a train actual, and that also need to be inverse transformed. And for the plot, I will use the exact same code like the previous cell, only replacing, this is a code, only replacing my test actual with train actual. So again, in the plt.plot, I'm passing the predicted BTC price train data, and then the next plot, I'm passing train actual. Let's run this. 1 second, let me check the error. What is the error I'm getting? Figure size name predicted BTC train data is not defined. Predicted BTC price train data. Didn't I think I did not run the previous cell. Yes. Awesome. Awesome. So this is my plot for the training set. And obviously, as you can see, the training set, the actual values and the predicted values are much more highly synced because it's a trained data. And as a last step, I definitely want to calculate the RMSE, that is root mean squared error, both on the test prediction, that is prediction on the test data set, and the prediction on the trained data set. So first, let's calculate the RMSE on the test data. This is the code, very simple. I'm just making use of math.square root and mean squared error. This was imported from the scikit library. And mean squared error, I'm passing the test actual and the predicted BTC price, and the whole thing will need to be square rooted, and for which I'm using math.square root. Let's run this. So on the test dataset, I'm getting a RMSE of 2079, which is kind of good, not too bad. And now my train dataset, the exact same code, only I need to change the test dataset to train. Exact same code. I'm using mean squared error from scikit-learn. This is actually their documentation. Mean squared error regression loss. Yeah, and it takes y true and y prediction. So this is my y true train actual, this is my y prediction, predicted BTC price train data, and the whole thing needs to be square rooted because I'm calculating RMSE. Root means squared error, and then run this cell as well. Yeah, obviously the train dataset loss is much less because the whole training and fit function was run on the training dataset. All right, that pretty much wraps up this rather long video. And again, I'll be uploading videos pretty frequently on the subject of machine learning and deep learning. So if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. See you in the next video. Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. So this is the second part of the previous video on applying LSTM, long short-term memory network, on historical Bitcoin prices to predict future prices. But first, the most important part, which is a disclaimer on this video. So this video and the associated code in the notebook is entirely informative. None of the content presented here constitutes a recommendation that any particular security, transaction, or investment strategy is suitable for any specific person. The video is purely for educational purpose. And Bitcoin, crypto trading, futures, stocks, and options trading involves substantial risk of loss and is not suitable for every investor. The valuation of the securities may fluctuate, and as a result, clients may lose more than their original investment. So to summarize again, this video is just for educational purpose and in no way constitutes a professional advice on Bitcoin investment or any other type of investment. First, let's quickly recap what we did in the previous video, and then we'll start off with this one. So in the previous video, this is a GitHub code that I'm referring to that was done in the previous video. So we had the historical Bitcoin prices of from 2015 10/27, that is 27th October 2015 up to 30th October 2021. And so this was the data. We had OHLC data, that is low, high, open, close, volume data, and the corresponding timestamps. So initially we downloaded the entire dataset on a per minute basis. As you can see here that for 10/27 I have one data at 04, then at 03, 02, and so on. But later I actually, okay, then the next step was to convert the time column, which was of object D type to date time D type, and then I converted these per minute data and resampled it on a daily basis. That is, the entire day's per minute data was grouped on a daily basis, and then I implemented few plots to check the correlation between the price and the data, that is on a minute basis, on a hourly basis, on a daily basis. And then the whole data set was for the entire period, and because I had to run my LSTM model on this data set, so I had to split the data set to train and test, because like we discussed in the previous video, we can never, during the training phase can never see the part of the data on which the model will be tested. That is, test data needs to be completely unseen during the training. So here we did the most important part to train, test, to split the data into train and test, and we kept 70% of the data for training and 30% for testing. And then we scaled the data down with the min-max scaling. And for this LSTM, I had the look back period defined to be 5. That is, the most important architecture of this LSTM was that I'm looking back previous 5 days of data, and then I'm predicting the 6th day of data. So the previous 5 days is kind of my X input, and the 6 days data is the Y, or the target variable. And this is kind of a sliding window that will slide for the entire training. That is, for each loop, the LSTM will look at the previous 5 look back period and predict the 6th day. Then the window will slide, and the immediately preceding 5 days again will be looked at, and the 6th day will be predicted. So with the help of a little function called dataset generator LSTM, I change the data set into this kind of shape. That is, the original training data set needed to be split like this: train X, train Y, and then test X, test Y. So the train X is nothing, just like I mentioned, that it's a previous 5 days of look back period. And so this is the shape I had for my train X and test X. And then yeah, so this was one of the most important point, and we discussed this in detail in the previous video, that for LSTM the input data should be reshaped into a three-dimensional tensor of samples, time steps, and features. And that's what we did, because we reshaped our original input data set into this three-dimensional tensor, the samples being the entire length of the data set, timestamps for us was 5, and the features were the number of features. All right, and yeah, so I think after this we pretty much ran the entire LSTM model, and let's check the model architecture that we had. Yes, the final LSTM was a very simple one, that I had one it's a sequential API of Keras, and then I applied the LSTM layer here and the dropout of 0.02, and then another LSTM layer again, and after that another dropout layer. And with that, finally I had a dense layer, and so my model was trained. And then before finally running the model training, I also defined early stopping and checkpoint, and passed these two as a callbacks to the final model training line of code as callbacks. So this was my final training line of code, regressor.feed. And then I think it took a couple of minutes to run the entire model. Let's check what we got after the entire model training was completed. Yes, so after the model was trained, I got for the entire training period of data, that is, I had data from 27th of October 2015 up to 30th October 2021. So for the entire training period, I got the predicted Bitcoin price, and this blue line was my actual ground truth, that is actual trading price of Bitcoin that was observed in the actual market. So this was a plot for my test data, and also I plotted the same graph for my training data. So here in this plot, I plotted the red line here is a predicted price of Bitcoin, and the blue line is the actual ground truth price of Bitcoin. And of course, as you can imagine, that for the training set, the two graphs almost overlaps each other, because the entire training was done on this training set. But for the test data set, it is not so much in sync, which is expected. And at the end, I got RMSE, root mean squared error for test data and train data as well. For the test data, I got an RMSE of 1640.541, and for the train, I got much lesser as expected, RMSE of 937 for the train portion. All right, now that was the entire recap of our previous video. I took a slightly more longer than I thought, but anyway, so on this, now I'm going to do the next part, which is that now that I have the trained LSTM model on the historic data, I am going to predict the future 5 days, that is after 30th. So 30th November 2021 was the last historical price that we had initially. So now I'm going to go beyond 30th October 2021 to predict the future next 5 days of Bitcoin prices, which is ultimately the target of any model training, that I have to predict the future. So let's do that. And most importantly, remember that our look back period has been defined to be 5 days. That is, I am looking back 5 days to predict the 6 days of Bitcoin prices. So here also, when I'm trying to predict the future 5 days, I have to, so for predicting the first of the future days, I will look back the previous 5 days. That is, to predict tomorrow's Bitcoin price, I have to take the historical prices of the immediately preceding last 5 days. And then to predict the, I have actually written the note here, feed into the model the past n, that is a past look back number of days values, and we get tomorrow's value as output. Then similarly, to get the day after tomorrow's value, feed the model the past n minus 1 number of days values along with tomorrow's value, and the model output day after tomorrow's value. So again, this is a sliding window, so we have to run a loop. But first, let's get back. Let's check our actual input data. So just remember that our test X was the last 60 days of historical prices of Bitcoin. So let's check what our test X looks like. Yes, so this is our test X, and it's a three-dimensional array because we have reshaped it accordingly, because LSTM needs the three-dimensional input to be fed into its model. And now check the testx.shape. Okay, so it's 55 by 5 by 1, and so I have to take the last 5 elements from this three-dimensional tensor, and this is the code. So look back period, I'm defining it to be 5, and one second, let's zoom in a little bit. Yep, look back period is defined to be 5 because I'm looking back 5 previous days. And then in the next line, I'm making use of the Python slice notation. That is, we already know that testx.shape 0 is 55. We already checked that here. And from that, I'm deducting minus 5. I'm deducting 5, which is look back period, and then colon. So this expression will give me the last 5 days. That is the starting position from this index, whole length of the test X minus look back period, and up to the end of the array. And if you run this, I should get, yes, 551. That is, this is my input data for the forecast that I'm going to do now. So 5 by 5 by 1. And again, it's a three-dimensional, it's a 3D tensor as required by LSTM. And then in the next, I'm just going to run a loop. Actually, before running the loop, let's check if how my this whole text for the next 5 days looks like, this 3D tensor. So I'm just printing the whole tensor. So as you can see that this is a three-dimensional array, and this is each window. So each window has 5 number of data points, and each of these data points are actually the Bitcoin prices. And of course, they have been scaled down with the min-max scaler, and that's why you are seeing this kind of 0.972, etc. Because the whole prices has been scaled between 0 and 1. So this is a sliding window, and in each window I will have 5 data points or 5 price points, and based on these 5 price points, the next one will be predicted, which is the job of the LSTM model. And similarly, it will run 5 loops. Yeah. So now, basically, what all I have to do, that I already have the trained model, and that model now needs to be run 5 times for these 5 windows, and each window will have 5 immediately preceding days of Bitcoin prices. So this is my code for that. Oops, sorry. So this is a code for predicting the future 5 days. Yeah. So let's go through line by line. It's very simple, super simple code. All I'm doing, I'm just defining a variable to hold the array of the next 5 days of data, and then I'm running a single loop. That loop should run 5 times because I'm predicting future 5 days. And then in the next line, this one, I am just applying the predict function because my model has already been trained, and that trained model was saved with the at this checkpoint, that is model from saved checkpoint. So in the previous part of the notebook, we already have saved this trained model at a checkpoint, and now I'm just on that saved trained model, I'm applying predict function, and predict to that predict function, I'm passing a single input on which the predicted price will be calculated. So these I and I plus 1 with the slice notation, this is a single input data from the test X to the predict function. So the predict function with this line, predict function will give me a single scalar value for the predicted price of Bitcoin for these input data. This is the input data. And then when I get this predicted forecast price test X, that, remember, it was scaled, so I have to scale it back. That's why I'm applying inverse transform. Because initially we applied min max scaler, but now I have to get it back to original actual Bitcoin price scale. Otherwise I cannot compare it with the plot or with the real price of Bitcoin. So that's why I'm applying inverse transform. And finally, this value I'm just appending to this array. And so now this array should hold all the future 5 days, because this loop was run 5 times on this data set that we defined in the previous cell, test x last 5 days. And now this should give me 5 future days of forecasted Bitcoin price data. Let's run this cell. Awesome. And 1 2 3 4, why did I get, no, yeah, I got 5 days. See, it's a 5-dimensional tensor I got. So this is the forecasted price for the 6th day. This is the forecasted price for the 6th day, means the next day. So this is the first day of the forecasted period. This is the 2nd day price of the forecasted period. This is the 3rd day price of the forecasted period, and so on. So with that, my job is pretty much done now, but now I am just going to, for the final representation of data, I'm going to do a plotting with the actual data of the entire ground truth trading period, and also the predicted data for the entire ground truth trading period, and also these 5 forecasted data. So for that, let's first do some little data processing. These predicted 5 days forecasted price test, this is actually, I have to turn it to an np.array for easier calculation. And let's check the shape. Yeah, so as expected, this is a 5 by 1 by 1 data matrix. And remember, this is just for the future 5 days of forecast period, but we also have the entire previous days of a predicted price data of Bitcoin. That is for the entire ground truth period from 2015 till 2021. We have the ground truth actual trading days, actual trading prices, but also we have the predicted prices, and that variable is this one. Predicted BTC price test data. This was a prediction for the entire ground truth trading period. Let's check its shape as well. Yeah, this is 55 by 1, and I have to actually combine both of them together. But before that, let's check their actual form. I think they are in a tensor form, 3D. Yes, they are in a this is a 2-dimensional tensor, and this should be 3-dimensional tensors. Yes, so let's flatten them just to make the calculation a little bit easier. I'm just flattening these predicted 5 days first. Not shape, just print the entire data after flattening. Yes, it got flattened, and I have to do the same for this one as well. Predicted BTC price test data, which was for the entire actual trading days. Awesome. These also got flattened. Fantastic. Now I have to combine them. I'm just defining a variable to hold the combined or concatenated these two arrays. Predicted BTC test concatenated, and I'm using np.concatenate. To this I will pass just this array and also this array. and then I can print this array. Why did it happen? Only integer scalar arrays can be converted to a scalar index. Oh yes, I have to pass the arguments to np.concatenate in a tuple format. Yes, it should work. Run this cell. Awesome. So now they have been concatenated. Let's check their shape. The shape should be 60 number of samples. Predicted BTC price concatenated.shap. Yes. So I have just now 60 scalar values in the array, and now I am ready to plot it. So this will be my code for plotting. Again, just super simple. Defining the figure size, and then I'm plotting the predicted BTC test concatenated, and also test actual. Test actual is my actual ground truth data for the same period. So remember, this test actual will have 5 less number of days because the actual number of trading data ended on 30th October 2021. But predicted BTC test concatenated, this variable has the actual trading days plus the 5 forecasted days. So let's run this cell. Beautiful. So this is the final plot. So the blue line is actual trading days, and the red line is a predicted from the LSTM model, predicted prices of Bitcoin. And up to this day, that is up to 30th October 2021, I have both the predicted test data and the actual test data on the ground, because this is the period for which I have the actual ground truth. Beyond this period, I have only the forecasted price of Bitcoin, but no actual data, because this is a completely forecasted data. We don't have the trading data at all yet during this period. So yeah, that pretty much wraps up this video. And once again, I am going to upload videos on the subject of TensorFlow and PyTorch in my channel pretty frequently. So if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. See you in the next video. Hello, this is Rohan-Paul. Very welcome to my machine learning and deep learning YouTube channel. Let's get started. So today I'll be doing this project in this video of predicting the transaction value of a potential customer of a bank. And for this, we already have a very famous Kaggle competition that was hosted in 2018 named Santander Value Prediction Challenge. And here the competition host is asking data scientists to come up with a number or predicted value of transaction of its potential customers so that the bank can personalize the services to a huge customer base at scale. But before I start, a quick word that in this channel, over the next few months, I'm going to do a lot of full-scale projects in the space of data science and deep learning, especially focusing on Kaggle competition and Kaggle challenges. And also, I'm going to upload videos pretty frequently, 2 times to 3 times each week. So if you have not subscribed yet, do subscribe. And if you like the video at the end, do not forget to hit the like button. All right, with that, let's do the actual work. So let's first get the business problem here that for a bank, one of the paramount problem is predicting the transaction value of a new or potential customer. Because if as a bank, I can predict the number or the transaction value of a potential customer, then I can personalize the bank services accordingly. Now, this is the main Kaggle page of this competition, Santander Value Prediction Challenge, and I am in the overview page. It very clearly says that in this competition, Santander Group is asking Kagglers to help them identify the value of transaction for each potential customer. This is a first step that Santander needs to nail in order to personalize their services at scale. Okay, this is the main target, main motivation of this challenge. And so now if you go to the data tab, this is the most important part for doing our entire work. So we have been given 2 sets of data set, test.csv and train.csv. I'm just clicking on the train.csv. So this is a tabular data set, and
The most important two columns are these ID, which represent each individual or each customer, and this target variable is what we need to predict. So this is train.csv I'm looking at. So I already have the target variable been given, and so for example, for the first row, for this particular ID, this value is a predicted transaction value. And now if you look at the data set, one specialty of this data set is that it's completely anonymous. That is, all the feature names are anonymized. Means, look at these features, like we only know the ID and the target, and the rest all are like this. 48DF8869 is one of feature name, then the next one is like this, and if you go further down, further right actually, see all these feature names, they're just numbers and letters combination, no names, no meaning whatsoever. So what it means is that a feature variable comes with no description whatsoever, and with anonymized names like these, it provides little meaning to us as data scientists. So as a data scientist, when I want to work with these data or predict some numbers for the target variable, I really want to understand all these feature names ideally. That is, they should have a proper definition, proper explanation, so that I can make use of some sophisticated feature engineering technique or similar things like that. But here for this particular challenge, probably I can just guess that these feature names probably, possibly, are aggregated transaction, maybe by day, by week, or by month, or maybe they are individual transaction which could be further grouped by some other financial instrument. For example, maybe they are grouped by debit card or credit card or loans, but I have no clear definition. So in the ideal case, you as a data scientist never want to work with this kind of data, but this is the constraint here. Although we would like to have meaning and definition for these feature names, but we don't have it. So this is the constraint, and we have to predict our model based on this data set itself. Because in this case, even the competition host, the Santander group, can't help much here. And the main reason is that for most companies, especially for financial companies and banks, the data they possess is a valuable asset, and that cannot be compromised. And this is probably the best that Santander can do to make this data available to public for a Kaggle competition or things like this, because otherwise they would never get the approval for their legal or compliance team to make some data available publicly. It would either, the data that they can share with us to the world, it would either be obfuscated data like this or no data at all that can be made publicly available. So hence the overall point is that this competition doesn't seem to offer a lot of room for either sophisticated models or smart feature engineering employing domain knowledge, because all the features are anonymized. But I don't know if there is a data leak or similar kind of property that is there hidden in the data set. But anyway, this is a constraint. So let's start working with this data itself. And another characteristics of this data set is that it is extremely sparse. That is, most values are zero. So if you go all the way right back, I can only see too many zeros all over. So this is an extremely sparse data set. So anyway, this target is our target variable that we have to predict, and these values that this target variable can take, these are continuous values. So the problem here we are dealing with is one of regression, and this is so overall it becomes a regression problem on a very sparse and anonymized data set. Now let's begin. And also the evaluation for this competition is RMSLE and not RMSE. That is, RMSLE stands for root mean squared logarithmic error, which is slightly different than root mean square error. We'll come to that in a second. So this is a formula for RMSLE, and so this is the evaluation matrix for this competition, and you can go there. The definition is also given here clearly. This is just a standard classical definition of RMSLE, where the epsilon, this term, is an error, which is this full expression on the right side, and the n is, that is, this n is a total number of observations or total number of rows that we are given, and p underscore I here is your prediction of target, predicted value of target, and AI is the actual target, and log x is a natural logarithm of x. So we have two logarithms here, one for log pi plus 1 and also for ai plus 1. And it is important to understand the differences between these two loss measures, the RMSLE, which is applicable for this competition, and RMSE. So both of these formulas are here. It's pretty simple, pretty standard formulation here, but let's understand the actual significance between these differences. So I have made this quick presentation slide uh, for the differences between RMSE versus RMSLE. So in the cases of RMSE, the presence of outliers can explode the error term to a very high value. But in the case of RMSLE, the outliers are drastically scaled down, therefore nullifying their effect. Evaluation metric RMSLEs are usually used when you do not want to penalize huge differences in the predicted and the actual values, and when both predicted and the actual values are large numbers. Also, RMSLE explodes in magnitude as soon as it encounters an outlier, which is, of course, coming from the first point. So, but in contrast, even on the introduction of the outlier, the RMSLE error is not affected much. And number two is RMSLE metric only considers a relative error between the predicted and the actual value, and the scale of the error is not significant. On the other hand, RMSE value increases in magnitude if the scale of error increases. So overall, RMSLE is especially useful for business cases where the underestimation of the target variable is not acceptable, but overestimation can be tolerated. And that makes sense for this challenge here, because think about it from the perspective of a bank, that if the predicted value of a customer is underestimated by our machine learning model, that cannot be tolerated, because in that case I will lose out on a potential good customer for which I could have some personalized services. But a little bit of overestimation can be tolerated, because if overestimate means that I will overestimate the transaction value of a customer, and thereby I will provide him with some personalized services which will just go waste, because that actually that was an overestimation of the value that the customer will bring to the bank. And so this really logically and conceptually makes sense to use RMSLE for this challenge. And also remember that here the outlier effect will be there for the target variable, because the target variable varies extremely depending on the customer. So I think I will probably go over the actual range of values in a second, but the target variable can be sometime like $10,000 to up to $17 million. So the outlier is too much in this data set, and so that's another reason to use RMSLE for the loss metric. And this is the overall plan for doing this project now. That so we have been given two datasets, train CSV and test CSV. So first I will do a little bit of data pre-processing before actually employing the model, and with those pre-processing are removing all the duplicate columns, and also I will be removing all the constant variance columns. And then remember, I already discussed it is an extremely sparse data set, so I'm going to remove columns with only sparse data. And then I will split the train.csv into train and test segment using the scikit-learn train test split function. And then I will be using applying three models: LightGBM, CatBoost, and XGBoost, all boosting three famous gradient boosting algorithm. And then finally I will do an ensemble model out of the training from these three models, and that ensemble model is the one that will be my final prediction, which will be applied on the test data set and also finally submitting to the Kaggle competition. So if you want to do the actual coding in the Kaggle kernel itself, you can just go to this competition page and code, and you can click on new notebook, and that will create a new kernel, and in that you can import this data and start coding. But normally what I do for any Kaggle competition or any projects for that matter is I download the full data into my local machine and then start my coding. And finally, when I'm done in the working at my local machine in my local machine, then I upload the kernel in Kaggle. But because this is not a huge data set as such, so I do not need a very powerful GPU. So this is 1.08 GB. But indeed the trained CSV is just 65.16 MB, so it is very reasonable, very small size data set compared to many other Kaggle competition. You can very easily handle this data in your local machine. So what you have to do first, just download the whole data set. You can download individually from here by clicking on this download icon for trained data set, test data set, and simple and sample submission. All three you need indeed. So yeah, so let's go to my VS Code. All right, so this is my VS Code, and so the first cell of these VS Code is just all the regular imports, that is NumPy, Matplotlib, and all the modules of sklearn. Especially, you can imagine all the standard module like train, test, split, etc. And the one thing to note here is that I'll be using LightGBM, XGBoost, and CatBoost in this project, and so I'm importing these three libraries: LightGBM, XGBoost, and CatBoost. And then the next cell, like I said again, that I already have downloaded the data from Kaggle to my local machine, and in this cell I'm just reading them. So this is my path of the two dataset, train CSV and test CSV, and with the read CSV function of pandas, I am just reading and then printing the head of those dataset. So this head prints the 5 rows of the train, and just as you expect that all the feature names are anonymized, and these two feature names, that is ID and target. ID is just represent each individual customer, because each of this row actually represent each potential customer identified by a unique ID, and the target is the predicted transaction value of that particular customer. And the rest, all these headings, all these column names are anonymized. They are our actual feature. And so that was my train. It has got total 4993 columns. So if you deduct ID and target, we are actually meaningful features are 4991. And now that I'm printing the testdf.head, this is my test dataset. And again, this test dataset has only one difference, that it definitely would not have the target as one of the column, because it's test. The target is what we are supposed to predict. So it has one less column compared to the trained dataset. Otherwise, we have IDs here as well, and all the features again. So in the next cell, I'm just printing the shape to check out the shape. So the train has 4,459 rows and 4993. So notice these speciality of this data set, that is, it is wider than it is lengthier. That is, the number of rows are actually less than the number of features. Very special. You don't get to see this kind of this kind of data set pretty often. All right. But anyway, we have to work with this in this case, and the test dataset has a reasonably good structure. We have 49,000 plus rows and 4992 features. Now let's do the pre-processing on our dataset. But before starting the data pre-processing, quickly go over the overall characteristics of our dataset. That we have 4459 rows in train set and 49,340 rows in test set. So our test set is almost 10 times bigger than a train set. And then in the train dataset, the number of column is more than the number of train rows. So our data set is wider than it is tall. So we need to be careful with feature selection and feature engineering, because it's a very special kind of structure that you don't see very often. And then we have an anonymized ID feature together with a numerical target variable. The typical values of this target variable seem to be relatively high, and the remaining 4991 features, that is excluding ID and target, now we are completely given an anonymized data, which is primarily integer or double format. Now you can actually quickly do test, check out the overall information of the dataset by using this function tf.info. Let's see what this prints. Okay, so this test dataset range index 49342, yeah, column 4992 entries like we expected. And D types, data types are mostly float 64, and we also have object. And do the same for my train data set. So in the train as well, I have 4459 entries. D types are distributed among float 64, int 64, and object. Memory usage is much less because it's a much lesser data set, 169.9 MB. All right, I am now going to do a scatter plot on the target variable value so I can check the distribution or the range of the target variables. So this is my code. And a quick note that I'm not going to type the code here, because that will make the video length incredibly long, and that is not a proper use of your time. So I already have coded this notebook in a separate file, and I'm just copying this code from there to here. So this code is pretty simple. I'm just making use of the scatter function of matplotlib and passing the values of the target variable from my train data set. And if I execute this cell, I will get this plot. And from the plot, you can see that the range of the target variable is really high. So now I want to do a histogram of the target variable to check their actual distribution. All right, this is my code for histogram. Again, this is I'm using the SNS hist plot function, and then to hist plot I am passing the entire values of my target variables from the train df, which is my train data set. And executing this code will give me this plot. All right, so now this is my histogram of all the target variables, and as you can see, this plot is actually very much right skewed. Most of the values are in this range, which is a low range, and very small percentage is in the very high value range. So, and that's what we were discussing, that in this competition the value range of target variables is really high. That is, there's the chances of outlier in my predictions, and this is another reason that to use RMSLE as a loss function or the loss metric to evaluate the prediction. So let's now do another histogram with log value of target variables. So to use a log value of the target variable, this is a code. The only difference with the previous code is that here I was passing the train df and then the target dot values, that is actual target values, the absolute values. But here I am making use of the np.log1p to take the logarithm, natural logarithm of the absolute values of target, and then I'll be plotting the histogram. So if I run this code, this is the plot I'm getting. Now this is actually more meaningful because now with the log, the extreme values get normalized a little bit, and I can see a more significant representation of the values of the target. And now the next step, I want to check for null values in the data. And now I just want to check the null values, and for this is my code. That is, I'm pretty simple line of code. Just the first line will give me the total size of the null values in the entire data set. So what I'm basically doing here, that I am first within this part of the code, I am checking the total count of null values in the entire train df. And in my comment, I've already put that to get the total number of null values, you have to use this kind of function application, that is data frame into dataframe.isNull.sum. And but from the total columns of my train df, I only want to extract those columns which has got no null values, and that's what I'm using these condition here, that these is null should not be 0 and only give me those column, and then applying size function to get the size of that many number of columns. And so overall, these entire piece of code will just give me the total number of columns which has null values inside them. and if you run this code, I will get a 0. So that means this entire data frame does not have any nan values or is null values. All right. Now, okay, the next step, I want to discard all the constant variance features. So variance measures particular features range of values, that is how much it is varying from the mean value of that feature. Now, by going by the normal statistical intuition, if a variable has very low variance, sorry, if a feature has very low variance, then that particular feature is very less important in contributing to the model prediction. This is kind of the rule of thumb or the normal statistical intuition, but it always is not absolutely 100% true, or you don't have to follow it blindly always, because in many deep learning models and many gradient boosting model, these issues are already taken care of. But what I'm going to do now is I'm going to only discard only those features who are constant. That is, they have a variance of 0. They don't change at all. That means they are practically constant. That means they have no contribution to the model prediction. So let's do that. And here is my code for that. So basically what I'm doing here is I'm extracting all the column names which are constant, which have 0 variance and 0 standard deviation. That means, and then I will be removing those columns from both train.df and test.df. So quickly understand this code, very simple code here. What I'm doing is just looping through all the column names in my train.df with the first line, and then I am checking that this entire variance calculation is not done on ID and target column, because ID is represent my unique IDs of each customer. So I do not want to definitely I do not want to touch them, even if they are duplicated. In case they are duplicated, even in that case I do not want to touch them for now, for this particular step. And target is obviously my target, so I do not want to run any check on that as well, because they may be duplicated, because two customers may have the same transaction value. So anyway, so and in that I'm just checking that each column, the STD, the standard deviation, should be equal to 0. So make a note of these, that I'm checking only those column names whose entire values are the standard deviation of all the values are exactly equal to 0. Only those columns I want to completely remove from my training data set. And this line is doing that, std equal to 0, and then I am appending that particular column names to these variable const columns to remove, which I have declared at the top. And then with these steps, I will have my, when this loop is done for the entire train.df, I will have my const columns to remove. We'll have the entire all the column names which are constant, which don't change, and then I can just remove them with the drop function, train.df.drop and train.df.drop, and I'm doing that in place. And just to check out that it's working, I'm printing here the constant columns to remove. So let's run this cell. Oops, it did not run properly. Let's check out. Okay, now it ran successfully. All right, now see, I just printed the total number of constant columns to remove, and the length of this actually. So 256 constant columns, that's what this code found. So we had I think total number of features are 4993. Out of that, ID and target you can omit, and so we had 4991 features. Out of that, 256 constant where features were just constant, they were not changing at all. And now that I am removing, so after removing, that is after doing these applying this drop function, the updated shape of my train.df would be 4459 rows, which remains the same, and the number of columns, that is the number of features, reduced by these 256. So this is updated feature number, and this data is, this train and test data is will be my final data set on which I'll be running the training. All right. And now the next step is to remove all the duplicated columns if there is any duplicate columns indeed. So I will be making use of two functions upon this. So one is duplicated and the LOC function. So let's quickly check out how duplicated works before understanding this piece of code. So I have put the detailed comment here. You can just read the comment that pandas duplicated function, that is when you apply it on df.columns.duplicated, it returns a boolean array, that is a true false array. So if the column name is unique, so this duplicated will move through each column name starting at the leftmost position and moving towards right. And if a column name is unique up to that point, then it will return false. And if the column name is duplicated earlier, it will return true. That's what the duplicated function will do. So for example, let's say I have this array alpha, beta, alpha. If I apply df.columns.duplicated on these, that is, for example, this is a column names, and if I apply duplicated on this, it will return me false because this is not duplicated. Then the next one is also not duplicated, and the third one is duplicated earlier, so this will return true. So false, false, true. That will be my return value after applying duplicated function of pandas on this. But in this case, after I find duplicated in this way, then I have to only return unduplicated column names ultimately. So I have to flip this value. That is where this duplicated function returns me false. That means it is actually unduplicated. I have to flip this to true, because then the LOC function of pandas will return me the true valued columns, because pandas allows one to index using boolean values, whereby it selects only the true values. This is, I'm talking about the LOC function. Since we want to keep the unduplicated columns, we need the above boolean array to be flipped, that is true, true, false. That is what I'm saying here is this false, false, true need to be flipped to true, true, false. So let's actually check the code, then it will be all clear. Okay, this is my code, and just look at the first line here. So my new trend df is after removing all the duplicated column names. So first I'm capturing all the duplicated column names and then flipping these with this tilde symbol, and then I'm capturing the totality of this with the LOC function, which uses to index my data frame and return me. So so basically, ultimately, this whole line of code will give me all the unduplicated column names. Now, actually, this line of code will give me the data frame after removing all the duplicated column names. So this new trend df, let's check the shape, run this code so that I can check the shape of this trend df. Remember our before running this code, what was the shape? The shape of trend df was 4459 and 4737. So this is important. This is 4737 were the number of column names or feature names, and now I am removing those duplicated ones. So let's check the new shape. And do you see that 4737 remains constant? So that means there is no duplicated column names indeed. All right. So, okay, we are done with this step. It's good that there is no duplicated column names. So now we can move on to the next one. And in the next step, I'm going to remove all the sparse data from the entire training data frame. Now, there are a couple of different ways to handle sparse data in pandas, and pandas also provides a function like sparse array to handle sparse data set. But for the purpose of this project and this notebook, I'm going to take the simpler approach, which is just to drop the sparse data from the training data set and also from test data set. So this is the function. This is the code here. So what I'm doing here is very simple. I'm defining a function which will take these two data frame. One is train data frame and one is test data frame, and then remove the sparse data from those two data frames. And how it is removing this? First, this variable column list to drop data from. So this is the whole column list which will be checked that if they have sparse data. And again, I'm excluding ID and target, just like in the previous step while checking for constant variance, that I did not include ID and target here as well. For obvious purpose, I'm excluding ID and target for all the column list which will be checked if they have sparse data. And then I'm looping through this column list to drop data from with this code. That is, I'm making use of this numpy.unique function. So basically, I am removing those columns where the unique values of those columns, that is, if you look at a particular column and vertically look at all their values, those unique values, if they are less than 2, that means it's a sparse column. That column has only sparse data. That is, they don't have unique values, that many unique values at all. Basically, their values are just like single value. In this case, it's probably 0. So that I am removing. And so yeah, so after finding those kind of columns which satisfies this condition, that is unique is less than 2, then I'm just removing that column in place with in place equal to true, both from train and test. And then this function returns me the train data frame and the test data frame. So with this function ready, I can just invoke this function and supply it the two arguments, that is my original train df and test df. Let's run it. Yep. All right. Now with this run, that's done. That is all the sparse columns are removed indeed from my train and test. And now that my data pre-processing is done, I am ready to do all the modeling part of the three gradient boosting model that I planned for, that is XGBoost, LightGBM, and CatBoost. But before that, I have to split the training data set. So let's do that. So this is my code. So standard code, pretty simple. I'm just structuring the xtrain and xtest dataset by dropping from the xtrain. I'm dropping ID and target because xtrain has within it included ID and target, but it should not have that because it's only the feature. It should not have the target variable, so I'm dropping them. And ytrain is similarly, I'm just ytrain is just the y target vector. It will have only the target array values, but note that I'm using log1p. I'm actually taking the natural logarithm of the target values because, like we saw in earlier plotting, the target values are extremely right skewed distribution. So a lot of values towards smaller end and very low number of values towards higher end. So taking in this kind of the skewed distribution of target variable, it's better to take a natural logarithm. And if you read the documentation of numpy as log1p, it clearly says that this mathematical function calculates natural logarithmic value of x plus 1, where x belongs to the input array elements. And what is my input array elements? This is my target values, this vector, that is all the values of the target column. These log1p will apply this function, that is log x plus 1, on each element of that vector, of that target column values. And that will be my ytrain. And then the xtest original, again, I'm just dropping the ID from my test data frame. And then I'm applying this train test split function of scikit-learn to split my xtrain into test, xtest, ytest, and xtrain, ytrain. I have named that here as x validation, but it's actually xtest. I just have to give a different name to properly differentiate it from some other names that I have used here. So yeah, I should actually just print the shape of these xtrain and xvalidation, all these things, to check that these splitting was done properly. And I have choose test size as 0.2. That means 20% of my data would be test data and the 80% will be my train data. Okay, I just printed the shape of each of these data arrays after splitting them, and as you can see that xtrain split is kind of expected 4735 features, x validation as well 4735 features. So this these two should be number of features should be equal indeed, and both two y-train, they are single array vector. So that's what I'm getting here. 3567 here as well for xtrain, and ytrain as well 3567, and the other number also matches. X validation, I have total 892 samples, and here as well 892 samples. All right, now my full preparation is ready to run my first model, which is LightGBM. But let's first understand the fundamental need of boosting algorithm, or where they fit in. So a basic question, let's say our first model predicts a data point incorrectly, and so does the second model, and say a whole sequence of model predicts a data point incorrectly. But then if I combine those individual prediction, will the combination works better for the prediction? So boosting answer this kind of question. Basically, boosting works on the principle of sequence and the principle of ensemble, where each subsequent model improves the error of the previous model. And among the three gradient boosting algorithm that I'm going to apply, the first one is going to be LightGBM. So here, before doing the actual code, just a quick word on these LightGBM, that it's a gradient boosting model that makes use of tree-based algorithms and is considered to be a fast processing algorithm. While in other gradient boosting algorithms, trees grow horizontally, in LightGBM, the trees grow vertically, meaning it grows leaf-wise, while the other algorithms grow level-wise. A very important point to note. And LightGBM chooses the leaf with large loss to grow, and it can lower down more loss than a level-wise algorithm when growing in the same leaf. So this is a pictorial representation of that LightGBM actually grows leaf-wise, while other grows level-wise. And now finally the LightGBM model training with my train data that was split in previous step. This step is actually simpler than you think, because here I'm just actually implementing from the LightGBM documentation their parameter and some default and some standard values of LightGBM. So let's check it out. So this is going to be this is the code. So here I'm just defining a function that will run my entire LightGBM model with these parameters, and then ultimately return me the y predicted value on the predicted test values of my target variable. So if you let's quickly move through the actual what they're doing. So these params are just taken from the documentation. You can look over their documentation here. Very well explained, and there are thousands of blogs on explaining these parameters of LightGBM. Because these algorithms are so popular. Anyway, so yeah, so after defining these parameters, and I'm not going in the details of these parameters because the documentation will be the best source for you to read through them, that what these objective is and bagging fraction, etc. So after defining these parameters, I am just passing my train data set and validation dataset. Remember, we already developed this dataset in here after applying the train test split. So I have x train split, x validation, y train split, y validation, and also my x train and y train from the original data. Okay. So yeah, so lgb.dataset, I am passing the train dataset and a validation dataset, and then I am running the train function, which will actually train the LightGBM model on this data set, and using these parameters again, the early stopping rounds 150, and then these are standard the standard numbers I have used here. You can again go through their documentation. It's really recommended. And then finally, after this training, I am ultimately returning from this function. This is the most important return value of this function, the predicted test LightGBM. So this is my predicted y value after doing the entire training. And again, this line I'm using these np.expm1. If you look at the documentation, what this will do is So I just put comments to understand what this EXP-M1 is doing. So let's quickly understand how I'm getting these predicted Y values. So in this step, my training is done. And then after my training is done, then I can apply the model to predict the values of target columns on test dataset. Remember, test dataset did not have any target column, because that's what we are supposed to, that's the whole purpose of doing the entire exercise, that we have to get the target values on our test dataset. So here in this line, that's what I'm doing, that applying this after the model is trained, and applying the predict function on the trained model, and passing this test X, which is my test dataset, and that will give me the target Y values of test dataset. Then that entire target Y values is captured in this expression, but that expression is being passed through these NumPy exp-m1. And what this exp-m1 is doing, it is just an exponential calculation function. So it calculates exponential of all elements, subtracting 1 from all the input array elements. So it's an element-wise operation. And so the output array consists of element-wise exponential value minus 1 corresponding to each input element. And this function, why this function is used, is because this function provides a greater precision than just simply using expx minus 1 for small values of x. So basically, the exp-m1 function avoids a loss of precision involved in the direct evaluation of expx minus 1 for small values of x. All right, so now that I have got my predicted y values, I am ready to return that from the function. And then this is just a definition of this entire function, but now I have not run this function yet. And that's what I'm going to do in the next cell, which is, and the code for actually invoking this function on my actual dataset is this, that I'm running this LightGBM model run that was defined here, and passing all my data that so this first part is all the split dataset, and the last one is X test original. Remember these predicted Y values, these will be calculated based on these X test original that is given in a separate CSV file in the original competition. So I think if I run this, it is going to take a while. 1 second. LGB light. Okay, I have not run this cell, and that's why it is saying that. So let's run this cell first. Okay. And now I'm running this cell. Okay, it has started running. I think it's going to take a while to do the entire LightGBM on these. I think we had a 4,300 rows or samples of data, so it is going to take a while. And once the LGBM training is over, you will get this kind of output. Note one thing: the RMSE error, which is a metric I have chosen during my LGBM function, that is continuously getting reduced. And why RMSE? Because this is a regression problem, and in the parameters you have to assign a metric for your loss function. And so I have chosen here root mean squared error, this RMSE, as my metric, and so that's a metric the whole LGBM is trying to reduce throughout its training. So initially, I look at this, my RMSE it was getting is 1.66, and then continuously after training at the end, towards the end, it was getting 0.79 or something similar. And then actually it started increasing, and that's why it invoked the early stopping technique here, because that was the best iteration or best RMSE it received. Okay, so that was my LGBM training, LightGBM training, and what is important from this training is these particular value that I have to keep saving this particular value, because like we decided that I will be running LightGBM, CatBoost, and XGBoost, and then combine them and do an ensemble of those three algorithm to get my final prediction value to submit to the competition. So after each training, this is my prediction from that particular training, and I have to keep track of them because I have to run my I have to do the ensemble at the end from these variable. So after LightGBM, I'm going to run now XGBoost, and I have already prepared this notebook. Actually, in my notebook, I have put a lot of notes to understand. I definitely will put a link to this notebook in my GitHub and also in my Kaggle, and put that in the description of the video, so you can take a look at that. Because in the notebook, I have put some extra note on the fundamental flow or understanding XGBoost, LightGBM, and CatBoost, and also what is the difference between XGBoost versus LightGBM or LightGBM versus CatBoost. So for now, just move on to XGBoost model training. This is all the notes that is in my notebooks. These maths are nothing to be scared of. You do not really have to implement this math because it's already implemented in this superbly popular XGBoost library that I'm going to use here. And yeah, so let's go to my XGBoost model. And here again, I'm defining a function to do the entire training. And that function will return me the predicted Y values from my test dataset. And then I will be applying this function on the actual dataset. So this is the function. The structure is again similar to LightGBM, that I am first defining all these parameters for which you will get details understanding if you go to XGBoost official documentation. That's really beautiful documentation they have written over there. You will get a lot of explanation on each of these parameters, so I'm not wasting time here to go over them again here. All right, so this is the parameters with which my XGBoost model will run, and then I'm defining the training data and the validation data. And again, this train data is this train X that will be supplied later in the next cell. So my training data and validation data is defined here. And then I am running the model xgb.train. With this, the model will be trained completely, and the output of the training is captured in these variable model underscore xgb. And then again, finally, after training the model, I will get the predicted Y values after the model training, and that Y value is what I will be returning from the function. And again, just like the LightGBM, I'm making use of this expm1 of NumPy. And all right, so now that's my function, and in the next cell, I'm just applying or invoking this function or executing this function indeed, and passing my split dataset and also my X test original, and that will give me this predicted Y test original of XGBM model. And again, we'll be running ensemble at the end, so we have to keep track of these particular variable. The most important, that is a predicted target value. And okay, so that was XGB. Like I said, that it's not the running the actual algorithm on the dataset is relatively easier and simple, because you have the beautiful and optimally coded packages, XGB libraries to help you. And if you just go through the documentation well, you will know exactly all the details, and you need to apply those modules of those libraries. Feature engineering on the data is actually where the difficult part. So again, the note on XGB does not require any introduction. This is one of the clear winner in the history of Kaggle. Many competition, tabular database competition, were won by applying XGBoost. It's really one of the great innovation of the recent years in the machine learning space. All right, now XGB is over. My final model will be CatBoost. In the notebook, I have provided some fundamentals on the CatBoost. You can go over them in the link that I will provide, so I'm not going over them. And I have also put detailed notes on each of the parameters of CatBoost that it takes and what it will represent. So let's now go to the code of running CatBoost. Okay, before moving on to XGBoost, I just want to mention a couple of things on two aspects of XGBoost model that I have used here, because XGBoost is so popular and so useful that in your machine learning career you have to use it so many times and throughout your career. So it's best to understand it in as much detail as possible. So the 2 points I want to talk about is D matrix and watch list. So D matrix is a special type of internal data structure of XGBoost, and it is much more optimized both from memory perspective and also training speed. And creating D matrix can be created from multiple data sources, uh, and it's so easy to convert our normal pandas data frame to D matrix, just like what I did here. That D matrix I just passed train X and train Y. Similarly, for the validation data, I pass validation X and validation Y. And remember, to create a D matrix, you have to pass both the features, that is X value, and also the target, that is Y values, which is what we are doing here. That is train X, train Y, validation X, validation Y. Both you need to pass to D matrix to convert your data frame to D matrix. All right, and the next one is watch list. So watch list is basically it's a named list of D matrix dataset to use for evaluating model performance. And how this model performance is evaluated with this parameter, that is in the original parameter that is passed to the XGBoost model, I am using one particular parameter called eval metric, and in this case it's RMAC, which is root mean squared error. So this RMAC will be computed under the, when I'm using watch list, these RMAC will be computed for each of these data sets during each boosting iteration, and stored in the end as a field named evaluation log in the resulting object. So that means this RMAC will be calculated for each named data matrix that I have, D matrix that I have provided to watch list. So which are the D matrix I have provided? I have provided training data. This is these data matrix, D matrix, and I have also provided validation data. This is these D matrix. So the evaluation will be done based on RMAC on both of these dataset for each iteration of XGB. That's what watchlist will do. And XGB.train, this particular function takes watchlist as one of its parameter. So yeah, so it's beautiful way to do the evaluation through the XGB model. I normally always use watchlist while using XGB model. And now, so finally, XGBoost. This is our third algorithm and the last one that will be used for our final ensemble. And this is a code now in this cell. So here I'm no more using another function. Just to be short and simple here, no particular reason. So I'm directly applying XGBoost regressor, and these are the parameters that I am supplying to it. Again, please go through the XGBoost regressor documentation. It's beautifully written, and then there the detailed definition of each of these parameters is provided. And then I'm applying the fit function, which will train the XGBoost based on this parameter on my dataset. And what is my dataset? That is X train, Y train, and eval set is X validation, Y validation. So these validation set will be used for evaluation of the XGBoost of under each iteration. And when this fit function is done with its work, that is, it is trained, the model is trained, then I'll be predicting my Y test by supplying to the trained model my X test data. And that's what I'm doing in this line. So my model XGBoost is now completely trained after the fit function is done executing, and then I can apply the predict function on the trained model to predict the actual Y test values from these X test feature names. And again, the whole prediction vector, I'm passing it to expm1, like we discussed earlier, to check out, to apply this exp x-1 function calculation on this. All right, so my XGBoost is also done now. And importantly, just like in LGB and XGB from CatBoost as well, we got the most important variable here, which is predicted y-test original CatBoost. So these will hold the entire target vector after applying the CatBoost on our test dataset. So now I'm fully ready to do my ensemble, and this is a final cell, and that's what I'm doing here, ensembling from all the three predictions previously I got from LGB, LightGBM, XGBoost, and CatBoost. So quickly, first, this is the Kaggle page. Just quickly check out the sample submission.csv file that they have given to us. So this is the final submission file that we have to submit to Kaggle to check with their test data. So this sample submission just contains all the unique IDs, unique values of the potential customers, and the target values of the target variable. So this exactly in the same format, we have to submit our submission file as well. And so what I'm doing here, first I'm just doing a pd.readcsv of the original submission file that was given in the competition, that is this sample submission.csv. And remember, I already have downloaded this in my local machine, so here I'm just reading from my local machine. And then I am doing this ensembling here. So first, my the prediction from my LightGBM model. Remember, after running the LightGBM, we got prediction all the vectors containing the full vector containing the target variable values of the LightGBM, and that was held in this variable. After running the XGB, we got a similar variable, which was this, and after the CatBoost, we got this variable, just like we saw right now in the previous cell. That is, after each of the model, we got a final prediction y values, and these are those variables, and from those variables I'm just pulling or extracting the target and putting that into a data frame with the pd.data frame function here. So I have now 3 data frame with the target variable that is predicted y for LightGBM, for XGB, and CatBoost. And finally, my final submission file, that is containing the final target values that I'll be submitting to the competition, which will have all the IDs and the corresponding target values, will be 50% from LGB and 30% from the XGB, and submission CatBoost, the 20% from CatBoost. And how I arrived these 50%, 30%, and 20% is just pretty much by experiments that I ran quite a few number of times, the entire training. And with these particular values, I was kind of getting the best score or the best ranking in the competition. So there is no proper formulas or etc. that I have used here. It is just by trial and error that I have selected this 50%, 30%, and 20% for final submission to Kaggle competition. All right, so this submission final, this is the final data frame that I have to submit, and this will be, and of course I have to submit a CSV file, so I have to convert it to a CSV file, but with this 2 CSV function of pandas. And yeah, so that's pretty much about it. And remember, the final submission file will look exactly like this. That is, it will have the unique IDs of the test and the predicted target values for each of these IDs, and then Kaggle will test these my prediction with their internal test dataset as well, and put me in the give me the ranking in their leaderboard for this competition, or also give me the competition score. So with these, initially I was getting a score of within the top 11% in this competition, which is not super good, but not too bad as well. All right, so that pretty much wraps up this video, and
Before closing, a quick word that I'll be uploading videos on full-scale projects in machine learning and deep learning. So if you have not subscribed yet, do subscribe. And if you like this video, destroy the like button. All right, see you next time.